Calculus 3. Calculus 3 takes a look at some different applications and more advanced uses of derivatives and integrals. The actual calculus part of finding derivatives and finding integrals we're very comfortable with at this point. We know how to do it all. Now we're going to see some uses of it. And chapters 5 and 6 we're going to look at together, and they look at these things called sequences and series. We've got to lay a little bit of foundation with sequence and series first, and then we'll start to see how the calculus plays into these. So first, to start this whole conversation off, we're going to talk about sequences. As we answer the question, how do we work with sequences? And really, what a sequence is an ordered list of numbers. So, for example, 1, 4, 9, 16. We say the first number is 1, the second number is 4, the third number is 9, the fourth number is 16. They're in order. In fact, we usually label them. A sub 1 is the first number. A sub 2 is the second number. A sub 3 is the third number. And A sub 4 is the fourth number, and so on. Well, with calculus, we're often interested in the infinite. So let's take a look at what is called an infinite sequence. The idea of an infinite sequence is the sequence really never ends. It starts with the first term, then you'll see the second term, then you'll see the third term, and we'll keep going on and on and on forever. There's no last term. There's a first term, but no last term. And we'll often express the infinite sequence in one of two ways. We can use what's called an explicit formula, which can define each term. You'll often see a sub n is equal to some function that defines each term at that function. So if we want the fifth term, a sub 5, we would just plug 5 into the function. So for example, in this sequence I have up above, 1, 4, 9, 16, you might notice those are all the perfect squares. So we could express that as a sub n equals n squared. And then when I want a sub 1, that's n, the first term, is 1 squared, or 1. When I want the second term, we plug 2 in. We have 2 squared, which is 4. When I want the third term, we want 3 squared, which is 9. We're just plugging the subscript into the function to find out what that term is. This way we could quickly find the 10th term by plugging 10 in. 10 squared is 100. That's an explicit formula. And we could keep going on and on and on with those. But another way to express them is what's called a recurrence relation. Which can define each term based on a previous term. So for example, we might say, OK, the first term is equal to 1. And then the nth term is equal to the previous term, a sub n minus 1, plus 2n minus 1. So to get the next term, we have to know the previous term. And so we can build this recurrence relation one term at a time based on what happened previously. So here, for example, a sub 1 we already know is 1. So a sub 2, the second term, is the previous term, which is 1, plus 2 times the term number, which is 2, minus 1. This makes the second term 4. If I want the third term, a sub 3, we take the previous term, which was 4, plus 2 times the term number 3 minus 1. And this becomes 4 plus 6 minus 1, which is 9. And what you might notice is we're really building the same sequence. This is the perfect squares, 1, 4, 9. The next one's going to be 16. So there's different ways to represent the same sequence, both explicitly and as a recurrence relation in terms of the previous terms. Now, there are a couple sequences that are very important to us, and so we're going to look at them separately. We're going to look at what's called the arithmetic sequence. And the idea of the arithmetic sequence is we have a common difference added to the previous term. So for example, I might have the number 5, then 8, then 11, then 14, and so on. And what you see is happening in this sequence is we have a common difference of 3 that's being added to each term to get to the next term. 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. We're adding 3 to get each term. And we can represent an arithmetic sequence here with recursion by saying, OK, the first term is equal to 5. So the nth term is equal to the previous term. And as we said above, we're just going to always add 3 to the previous term. Maybe we could generalize this and say the first term is the first term, whatever that is. And the next term is the previous term plus that common difference. Although we also know how to express this with an explicit formula. The explicit formula is going to be that any given term is equal to, what we really have is a linear relationship. We're going by 3 each time. We really have a y equals mx plus b situation, where we can take the common difference as our slope. And we're going to have to say n minus 1 plus the y-intercept, or the starting value of 5. Now, we have to do n minus 1 instead of n with this y equals mx plus b because we don't call the first term the 0th term, but the y-intercept is the 0th term. So we're kind of staggered off by 1 unit. So what we really have is our slope, or common difference, and we have our y-intercept, or our starting number. Often we call that b. So maybe generally we would say a sub n is equal to the common difference times n minus 1 plus the first term. That's the arithmetic sequence. Another important sequence, though, that we work with is called the geometric sequence. If the arithmetic sequence has a common difference that's always added, the geometric sequence has a common ratio that is multiplied. So, for example, we've got 4, negative 12, 36, negative 108, and so on. What you see here is to move from one term to the next term to the next term, we have a common ratio that we're multiplying by. We're multiplying each term by negative 3 to get the next term. 4 times negative 3 is negative 12. Negative 12 times negative 3 is 36, and so on. Well, if I wanted to express this with a recurrence relationship, we again will say, well, the first term is equal to 4. And then to get that, oops, sorry, the first term, not the nth term. The first term is equal to 4. And then to get the nth term, we just take the previous term, n minus 1, and multiply by that common difference of negative 3. Maybe generally we say the first term is the first term, and the nth term is that common ratio times the previous term. But we can also express this with an explicit formula. Here we're multiplying by the same number over and over again. Repeated multiplication, we should know, is an exponential. So we can take our first term times the ratio to the n minus 1 power, telling us we multiply by negative 3 over and over and over again. Here we have to do n minus 1 because the first term, a sub 1, is not multiplied by negative 3. So if we plug 1 in for the n, you'll notice 1 minus 1 is 0. Negative 3 to the 0 is 1. And we're just left with 4 for the first term. So we've got to be careful sometimes with that n minus 1 bit. So kind of generally, an explicit formula for a geometric sequence is the first number times the ratio to the n minus 1 gives us that geometric sequence. We might even label that the 4 is the first term and the 3 is the ratio. OK, so if that's a geometric sequence, we're ready to actually start combining what we know about arithmetic and geometric and also pattern recognition. We're going to see if we can build and find explicit formulas. And as we do this, our general strategy is to just look for patterns and do a little guess and check. Because sometimes you have to try stuff. Is the exponent n? Is it n minus 1? Is it n plus 1? Let's guess and check a few and see how we do. So for example, if I have negative 1/2, comma 2/3, comma negative 3/4, comma 4/5, comma negative 5/6, we're going to break this down and see what we observe. First thing I observe is it's alternating. It's going from negative to positive to negative to positive to negative. And the way we can generate an alternating sequence like this is we just take negative 1 raised to an exponent. Now, I always check the first term. The first term is negative. So if I plug 1 in for n, negative 1 to the first power is negative. If the first term was positive, we'd need to use n plus 1 so that we shift the negative sign down 1. So the first thing we saw is that we're alternating. Second thing I observe here is I just look at the numerators. The numerators are counting 1, 2, 3, 4, 5, and so on. Well, what we see is the first term has a numerator of 1. The second term has a numerator of 2. The third is 3. The fourth is 4. That's just n. The term number is the numerator. 1, 2, 3, 4, 5. When I look at the denominators, they're a little different. The denominators go 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. I see the denominators are kind of a shift of 1. They don't start, the first term doesn't start at 1. The first term starts at 2. It's always 1 more than the term number. It's n plus 1. So the fifth term has a denominator of 6, 1 more than that. And so when I put it all together, what we end up with is that the nth term is alternating, -1 to the n, times the numerator of n divided by the denominator of n plus 1. And this becomes the explicit formula for our series. Let's try another one, see if we can continue finding these patterns. Let's do 3/4, 9/7, 27 over 10, 81 over 13, and so on. If I look just at the numerators again, the numerators are 3, 9, 27, 81. What I see is those are powers of 3. 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and that exponent is always matching the term numbers. So 3 to the n seems to create my numerators. So for the fourth term, 3 to the fourth is 81 in the numerator. In the denominator, we've got 4, 7, 10, 13. 4, 7, 10, 13. What I notice there is we are adding 3 to get the next term. If we're adding 3 to get the next term, what we actually have is an arithmetic sequence. My arithmetic sequence says I can take the common difference of 3 times n minus 1 plus the starting number of 4. Well, let's simplify. If I distribute the 3, 3n minus 3 plus 4, combining like terms, we have 3n plus 1. So when I combine this together, any term, the numerator is 3 to the n. The denominator is 3n plus 1. And we've got an explicit formula for what's going on with this sequence. Let's do another example then. Let's try 2 over 2. I know it's not reduced, but we're going to go with it. -4 over 10, 12 over 50, and -48 over 250. And so on. Again, the first thing that I'll notice on something like this is we're going from positive to negative to positive to negative. We're alternating again. To get an alternating sequence, we take -1 to some exponent. The problem is we've got our first term, second term, third term, fourth term. Notice if we use the term number of 1, plugging 1 in for n, -1 to the first power is -1. Our first term is not negative. Our first term is positive. We've got the wrong signs. We're set up for negative, positive, negative, positive. And this one's positive, negative, positive, negative. So to shift by 1, we just need to add 1 to the exponent. Now when we plug 1 in, we get 1 plus 1 is 2, and -1 squared is a positive 1. And we're set up for a positive-negative alternation. Let's look at the numerators. 2, 4, 12, 48. To go from 2 to 4, You might notice we multiply by 2. But from 4 to 12, we multiply by 3. And from 12 to 48, we multiply by 4. We're multiplying by one more number. To get to 48, we have 4 times 3 times 2. To get to 12, we have 3 times 2. Notice that counting down of multiplication, we should recognize that as a factorial. To get the fifth term, it should be 5 times 4 times 3 times 2 times 1. However, this doesn't quite work because the first term isn't 1. The first term is 2. Plugging 1 in, 1 factorial is 1. How do we get a 2? Well, let's shift by multiplying that by 2. Let's see if that works. Let's test that out on the third term. The third term has a numerator of 12. Well, 3 factorial is 3 times 2 times 1, which is 6, times 2 is 12. And it looks like we've got our numerators figured out. All that's left to look at then is the denominator. The denominators are 2, 10, 50, 250, 2, 10, 50, 250. And what you might see there is we seem to be multiplying by 5 every time. We know that if we're multiplying by 5 every time, that's a geometric sequence where we take our first term times the ratio to the n minus 1. And now if we put all of that together, we can say the nth term is negative 1 to the n plus 1 times 2n factorial over 2 times 5 to the n minus 1. But one thing you might notice, we've got 2's in both the numerator and denominator. We can divide those 2's out. So our reduced formula then becomes negative 1 to the n plus 1 n factorial over 5 to the n minus 1. So that's kind of how we can play and observe patterns in order to find the nth term of any geometric or any sequence, really, whether it's geometric, arithmetic, or neither. But sometimes we're more interested in, as these terms go out, as these terms get to the infinitieth term, kind of what's the last term approaching? We call this the limit of the sequence. Are the terms getting closer and closer to some number? Are they asymptotically getting closer to some value? Or what is the infinitieth term? Well, to do that, we will say if the limit as n goes to infinity of a sub n of all the terms is equal to some limit L, that means the sequence is approaching L as n becomes large. If this happens, if it approaches a specific limit, we say then the sequence is convergent, or the sequence converges to a specific number. Kind of the opposite case then is if the limit as n goes to infinity of the terms does not approach a value L, it is called a divergent sequence. Let's do some examples. Got quite a few of these to look at. Let's take the explicit formula of 1 minus 1/2 raised to the n power. Well, if we take the limit as n goes to infinity of 1 minus 1/2 to the n power, we end up with 1 minus, and 1/2 times 1/2 times 1/2 is getting smaller and smaller and smaller. That's approaching 0. And so 1 minus 0 equals 1. Therefore, as n gets really large, these terms are getting closer and closer to 1. We can say that this series converges. Or the sequence converges, sorry, converges to 1. Let's try the sequence 1 plus 3n. Well, if we take the limit as n goes to infinity of 1 plus 3n, well, we know that becomes 1 plus 3 times, as n gets huge, it becomes infinity. Basically, these numbers are just going to get bigger and bigger, because we're always just adding 3 each time. This sequence diverges, because it goes off to infinity. How about the sequence 3n to the 4th minus 7n squared plus 5 over 6 minus 4n to the 4th? Well, if we took the limit as n goes to infinity of that entire thing, we know from our work with limits that the largest exponent is going to take over. And that largest exponent is the 4th powers. And basically, the 4th powers take over, and we get 3 over negative 4. And this series does converge. I'm sorry, this sequence does converge to negative 3/4. Now, we have a good friend named L'Hopital that can help us with these as well. Let's say we've got a sequence that's 2 to the n power over n squared. We would try and take the limit as n goes to infinity of 2 to the n over n squared to see if it approaches a value. But the numerator goes off to infinity, and the denominator goes off to infinity. So what we can do is we can apply L'Hopital's rule and take the derivative of the numerator and denominator and see what limit that gives us. The derivative of 2 to the n is 2 to the n times the natural log of 2 over the derivative of n squared is 2n. But those still are each going off to infinity. So that doesn't help us. So I guess we'll take another derivative. So we have the limit as n goes to infinity. The derivative of 2 to the n is still 2 to the n natural log of 2 times the constant natural log of 2, all over the derivative of the denominator, which is 2. And now what you see happening is the numerator, natural log of 2 squared, that's just a constant, divided by 2, that's just a constant. But this numerator, 2 to the n, goes off to infinity. We have infinity divided by 2, which is still infinity. So this series, or this sequence, diverges. The sequence diverges because it goes to infinity. Let's do one more with our friend L'Hopital. Let's say the nth term is 5n squared plus 1 over e to the n. Again, the numerator is off to infinity, and the denominator is off to infinity. So we can use L'Hopital's rule to say that the limit as n goes to infinity is the derivative 10n over the derivative e to the n. But as n goes to infinity, these are still both going off to infinity. So we'll do L'Hopital's rule again. The limit as n goes to infinity of 10 over e to the n. And now when we plug infinity in, e to the infinity is infinity. We're taking 10 divided by a very large number. Basically, we end up with 0. This sequence converges. It's a convergent series. Now, sometimes we can't just take the limit very clearly and see what it's approaching. So we need a slightly different strategy. And there is another nice strategy that we can use sometimes, not always, but it works out nice when it does, with what are called bounded sequences. And the idea of a bounded sequence is all the terms are smaller than a constant. That's called bounded above, because they're never going to be bigger than this constant number. And or all the terms are larger than a constant. And that's what we call bounded below. For example, a sub n equals 1 over n is bounded above by 1 and below by 0. What you see is the first term when we plug 1 in is 1 over 1, which is 1. Then it's 1/2, 1/3, 1/4, 1/5. They're going to get smaller and smaller, but they're never going to get to 0. So it's always smaller than 1, bounded above by 1, but always bigger than 0, bounded below by 0. And this idea of being bounded is very useful because of what we call the monotone convergence theorem. If we are bounded above, means I'm never larger than some number, and increasing, so I'm always getting larger, then the sequence converges. Kind of visually, what we're talking about is, let's say we're bounded above by some constant. We'll call it c. And my series is always increasing, but it's never going to get bigger than that constant. You can see it's going to kind of converge to that constant. It's approaching some number. And really, the opposite is also true. If we are bounded below and decreasing, then the sequence converges. And visually, that's almost the same thing. We've got some constant c, and the series is always decreasing. I'm sorry, the sequence is always decreasing, but it's never going to pass that c. It's going to get closer and closer to that c. We see it converges at that point. Let's do one example where we can see this work out. Let's say a sub n is equal to 4 to the n over n factorial. Okay? What we'll do then is we'll look at the next term to see if it's getting smaller or getting bigger. The next term, a sub n plus 1, is equal to 4 to the n plus 1 over n plus 1 factorial. But we can break that up a little bit. 4 to the n plus 1 is really 4 times 4 to the n over, and n plus 1 factorial is really the n factorial, or if we break it out into its terms, the first term is n plus 1. Break it out into its factors, not terms. Times the next term is n, then n minus 1, n minus 2. That's really n factorial. Which means we've broken this up into two fractions. We have 4 over n plus 1 times 4 to the n over n factorial. What we see is we're taking the previous term and multiplying it by 4 over n plus 1. When we multiply by 4 over n plus 1 with large numbers of n, because we're always interested at infinity, if n is large, 4 over n plus 1 we're really multiplying by a really small number. We're multiplying by 4 over infinity. We're not really multiplying by much. It's always going to be positive. 4 over n plus 1 is getting smaller, but never negative. This means we are bounded below by 0 and decreasing. Each term is smaller than the previous term because we multiply by some fraction, 4 over a large number. And it's smaller and smaller and smaller. And it's decreasing, 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 but it's never going to pass 0. So therefore, by the monotone convergence theorem, we know, therefore, the sequence converges. And that's how we can use the monotone convergence theorem. So this is a little introduction to sequences. In our next video, we're going to look at what we can do with sequences in a little bit more of a useful fashion. But today, we're just trying to get familiar with using those sequences, expressing them as an explicit formula, finding out if they converge. So take a look at your homework, practice a few of these, and we'll discuss them more in class. Now, while sequences are very interesting to take a look at, what we're more interested in with calculus is what are called series, specifically infinite series. So our question's going to be, how do we work with infinite series? And first, let's define what exactly we mean by an infinite series. Basically, a series is a sum of a sequence. It is a sum of an infinite number of terms. And we'll write it with this notation. We'll take the sum as our n goes from 1 to infinity of each of the terms a sub n, which basically means we take the first term and add the second term and add the third term and just keep adding all the way up to infinity. Kind of an example of this might be to say that the sum of some number of terms is equal to the sum as n goes from 1 to infinity of maybe n over n plus 1. So if I want the first sum, that's just the sum of the first term. The first term is 1 over 1 plus 1, which is really just saying 1/2. Or, as a decimal, 0.5. The second sum then says take the first term, which was 1/2, and add the second term, which now is putting 2 in for n. 2 over 2 plus 1, or 1/2 plus 2/3, which is equal to about 1.17 and change. So if I want the third sum, that means we're going to add the first 3 terms. The first term was 1/2, plus the second term was 2/3, plus the third term, which is 3 over 3 plus 1, or 1/2 plus 2/3 plus 3/4. Now my sum is equal to about 1.92 and change. And we could keep doing this. But ultimately, what we're interested in is if these are kind of the partial sums, the first sum, the second sum, the third sum, we're interested in kind of what happens with the entire sum. So we've got these things called the kth partial sum. We'll call it S sub k is equal to the sum as n goes from 1 to k instead of infinity of each of the individual terms. Well, if the partial sum diverges, goes to infinity, then the whole series will diverge as well. And if the partial sum converges, then the whole sum, or the whole series, will converge as well. Let's take a look at what that means in an example. We've been talking about the sum as n goes from 1 to infinity of n over n plus 1. And we found out that the sum of the first term was equal to 1/2. The sum of the second term was 1/2 plus 2/3. The sum of the first 3 terms was 1/2 plus 2/3 plus 3/4. And the sum of the fourth term is 1/2 plus 2/3 plus 3/4 plus 4/5, and so on. And what we're interested in is if we kept going, what would we know about the kth sum? Does it converge or diverge to a specific value? Well, what I notice is if I look at each one of these terms, they're either 1/2 or bigger than 1/2. 1/2 or bigger and bigger than 1/2. 1/2 and bigger and bigger and bigger than 1/2. What I could say is that the first term is greater than or equal to 1/2 times the number of terms, which is 1. Therefore, the second one's going to be greater than or equal to 1/2 times the 2 terms, because 2/3 is bigger than the 1/2. And then the third series is 1/2 times 3. We've got 1/2 times the 3 terms, but our answer is going to be bigger. And similarly, we're going to be bigger than 1/2 times the fourth term, which means ultimately the last k is going to be greater than or equal to 1/2 times the k number of terms. But here's the catch with that. If I were to take the limit of this stuff, the limit as that kth term goes to infinity of 1/2 of k, we know that is equal to infinity. Because we're just taking 1/2 times a large number. It's still a large number. Therefore, we can conclude that this series is unbounded and that the sum as n goes from 1 to infinity of n over n plus 1 is just going to keep getting larger and larger and larger. Ultimately, this series diverges because the kth term diverges. But this is not always the case. Let's take a look at another example. Let's take a look at the sum as n goes from 1 to infinity of 1 over n times n plus 1. To get an idea of an example of what's happening, let's take the individual first few sums. The first sum is just the first term, 1 over 1 times 2, which is 1/2. The second sum is equal to that first term of 1/2 plus 1 over 2 times 3, which turns out to be 1/2 plus 1/6, which is equal to 2/3. The third sum is the 2/3, the prior sums, plus the third term, which is 1 over 3 times 4, or 2/3 plus 1/12, which is equal to 3/4. And with this one, you might start to notice a pattern approaching for what each term is equal to. Can you tell what the fourth sum is going to be? 3/4 plus the 1 over 4 times 5 is equal to 3/4 plus 1 over 20, which turns out to be 4/5. Did you catch the pattern? The kth term is going to be equal to, notice our numerators are always equal to the term number, k, over the denominators are one more than the term number, k plus 1. So this time, if I were to take the limit of that stuff as k goes to infinity, as we get to the infinitieth term of k over k plus 1, we know the k's are going to get really large. The plus 1 isn't going to really matter. And this is ultimately going to be 1. Therefore, we know that the sum as n goes from 1 to infinity, not just k, of 1 over n times n plus 1 is equal to 1. Therefore, I know this series converges. Basically, as we get more and more terms added in, we're going to get closer and closer to the number 1. So we converge. It's kind of a really brief introduction to deciding if series converge or diverge. I want to talk about 3 special series that come up quite a bit as we work through series. And the first one is one of the most famous series of calculus. It is called the harmonic series. And the harmonic series is the sum as n goes from 1 to infinity of 1 over n. Basically, it's 1 over 1, or 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, 1 over 6, and so on and so forth. We should recognize this harmonic series quickly as we continue to study in calculus here. Well, let's take a look at what's happening with that harmonic series. First, let's take a look at the first sum. Well, the first sum is 1 over 1. That's just 1. The second sum is 1 plus 1 over 2. The third sum is 1 plus 1/2 plus 1/3. And the fourth sum is 1 plus 1/2 plus 1/3 plus 1/4. And now what I want to do is stop here for a moment and take a look at these last two terms. 1/3 plus 1/4. Notice 1/3 is bigger than 1/4. Each term is bigger than the next term after it, which means this is bigger than 1/4 plus 1/4. If I replace the 1/3 with something smaller, the 1/4, we end up with something smaller. Well, 1/4 plus 1/4 is 1/2. So the sum of the first terms is greater than 1 plus 1/2, and I'm going to say 1/2 times 2 because we've got the first 1/2, and then the next one's bigger than another 1/2. Similarly, if I kept going all the way down to the 8th sum, the 8th sum is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And we've already established that 1/3 plus 1/4, that part is greater than 1/2. But what's interesting is if I looked at all the other terms, the next 4 terms, what I have is that the 1/5 plus 1/6 plus 1/7 plus 1/8, 1/8 being the smallest, meaning all 4 of those are bigger than if they had all been replaced with 1/8 plus 1/8 plus 1/8 plus 1/8. And 4/8 adds up to 1/2. So the 8th sum is greater than 1 plus 1/2 times 3. Because we've got a half, another half, and the next 4 terms add up to a half. And in fact, in general, if we were to continue this pattern out, s sub 2 to the n power. It has to be a power of 2. Notice the ones we played with were the 4th power and the 8th power. The next 1/2 would come off of the 16th power. But it will always be greater than 1 plus 1/2 times whatever that exponent is on the 2. So for example, with the 8th sum, 8 is 2 to the 3rd. We had 3 1/2s multiplied together, which means on the 16th, there'll be 4 1/2s added to the 1. We said, though, if we can take the limit as n goes to infinity of the sum, which is 1 plus 1/2 of n, this one gets there really slowly. But as the n gets larger and larger and larger, half of infinity is still infinity. And if you add 1, you still get infinity. So therefore, the partial sums diverge to infinity, which means the big idea, in fact, let's change colors. We'll do this in brown. Therefore, the harmonic series also diverges to infinity. The sum as n goes from 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4, and so on, is going to equal to infinity. The harmonic series diverges. This is one of the most important series of calculus, and we should recognize that whenever we have the sum of 1 over n, it will always go to infinity. Very slowly, but it still diverges. So that's the first important series, the harmonic series. The second of 3 important series I want you to see today are what is called the geometric series. And it comes from the geometric sequence. The geometric sequence was some number, then some number times the ratio, then some number times the ratio squared, because we kept multiplying by that ratio. And so the geometric series says we're going to add those all together. A plus a times r plus a times r squared plus a times r cubed. In other words, we're taking the sum as n goes from 1 to infinity of a times r to the n minus 1. It turns out, and the proof is a lot more involved, but it turns out that this geometric series will diverge. Actually, I'll write the series again here because we're going to highlight this as very important. The sum as n goes from 1 to infinity of a times r to the n minus 1. It will diverge if the absolute value of r, the common ratio, is greater than or equal to 1. And if the absolute value of the ratio is less than 1, it converges to whatever a divided by 1 minus r is. So the geometric series, which we should recognize, diverges if our ratio is greater than or equal to 1, and it converges if the ratio is less than 1. Let's take a look at some examples. Let's take a look at the sum as n goes from 1 to infinity of negative 3 to the n plus 1 over 4 to the n minus 1. Now, we have to be careful here because this isn't quite a geometric series yet. Let's take a look at what this series is doing and see if we can convert it into the right form of the geometric series. So starting when n is 1, we end up with negative 3 squared over 4 to the 0 power. Plus, when n is 2, we have negative 3 cubed over 4 to the first power. Plus, we've got negative 3 to the 4th over 4 to the second power, and so on and so forth. Which means what we really have, 4 to the 0 is just 1. So this is really just saying negative 3 squared plus negative 3. That negative 3 squared gets multiplied by another negative 3 over 4. Plus, then that negative 3 squared is multiplied this time by a negative 3 over 4 twice, giving us a total of 4 in the numerator and 2 in the denominator. And so on. Which means really what we have is positive 9 plus 9 times negative 3/4 plus 9 times negative 3/4 squared plus, and so on. And what we see is the starting value for this series is 9. And the ratio that we're being multiplied by is negative 3/4, then negative 3/4 squared, then negative 3/4 cubed, and so on. Because that ratio is smaller than 1, the absolute value is smaller than 1, we know it converges to the starting value over 1 plus or actually 1 minus, the ratio, which is negative 3/4. Well, let's clean up that fraction by multiplying by 4 all the way across, and we get 36 over 4 plus 3, or 36 over 7. So this series, as it gets closer and closer to infinity, is ultimately going to converge to 36/7, getting closer and closer, because the ratio is smaller than 1, or the absolute value of the ratio. Let's compare that to the sum as n goes from 1 to infinity of e to the 2n. Now, I could rewrite this, because that e to the 2n is really e squared to the n power, as the sum as n goes from 1 to infinity of e squared raised to the n power. What we see here is we're multiplying. Each term gets multiplied by e squared, and then e squared, and then times an e squared. What we're really doing is we've got a ratio of e squared being multiplied over and over again. The problem is e squared is greater than 1. Whenever the ratio is greater than 1, we know the entire series diverges to infinity. So that's the geometric series. It diverges if the absolute value of the ratio is greater than 1, and it converges if the absolute value of the ratio is less than 1. One last series I want to talk about. It's called the telescoping series. This one doesn't come up much, but when it does, it's really nice. It is a series where most terms subtract out. What I mean is, in general, we've got the sum as n goes from 1 to infinity of one term minus the next term that comes after it. In other words, what you end up with is the first term minus the second term. And then when n is 2, we get plus the second term minus the third term. And then when n is 3, we do plus the third term minus the fourth term. And so on and so forth, all the way up to basically infinity. And what you see happening is the second subtracts out with the next, and then the next one subtracts out with the next one, and so on until we end up with the kth partial sum is equal to the first term minus the last term. Well, if the limit as k goes to infinity of b sub k converges, in other words, that last term is approaching a specific number, not infinity or negative infinity, then the partial sum also converges. So if I have a telescoping series where we're subtracting out the next term, it's going to basically come out to the first term minus the last term, if the limit converges. So for example, if we're working with the sum as n goes from 1 to infinity of the cosine of 1 over n minus the cosine of 1 over n plus 1. If I recognize we've got a telescoping series that we're subtracting the cosine of the next term, every two terms is going to subtract out all the way down to the kth term, which is the cosine of the first term, 1 over 1, which is 1, minus the cosine of the last term, which is 1 over k plus 1. Well, if I think about the limit as k goes to infinity of the cosine of 1 over k plus 1, ultimately, as k gets huge, we have 1 divided by a huge number, which is 0. And the cosine of 0 is 1. So, overall, this series converges to the cosine of 1 minus the very last term at infinity is going to be 1. And we found the sum of this telescoping series. Let's do one more. Let's do the sum as n goes from 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1. Notice we are subtracting the next term, n plus 1. So then I know the kth partial sum is e to the 1 over 1, or e to the first power. Everything else subtracts out all the way down to the last one of e to the 1 over k plus 1. So what we think about is, what is the limit as k goes to infinity of the last term, e to the 1 over k plus 1? Well, again, 1 over k plus 1 ends up going to 1 over infinity, which becomes 0. And e to the 0 is 1. And so what we find out is if that converges, then the entire sum converges. The sum is equal to e minus the last term here is approaching 1. And that gives us our telescoping series. So we've taken a look at these infinite series and begun to play with them. We talked about the harmonic series, geometric series, and telescoping series, 3 important series as we continue moving forward. And we're playing with this idea of when does it converge and when does it diverge. In our future lessons, we're going to talk about some tests we can do to get a better idea about when it's converging and diverging. But for now, take a look at your homework assignment, practice those, and come to class with questions. As we're working with series, the big question we're really interested in is, does this series go to infinity, or does this series add up to a finite number? So that's going to be our question that drives us today. How do we know if a series converges, meaning goes to a specific number, or diverges, meaning goes to infinity? And actually, this is the question that's going to keep with us throughout this entire unit. Does the series converge, or does the series diverge? We're actually more interested in whether or not it converges or diverges than what it actually adds up to. So the first way we can do this, and this is really the first test we should always do when trying to decide if a series converges or diverges, it's called the divergence test. It's a quick test that will tell us if a series diverges or if we're not sure. What we do is we consider the sum as n goes from 1 to infinity of a sub n. We're looking at some series, sum. If the limit as n goes to infinity of those individual terms is not equal to 0, basically what that means is as we get up to infinity, are we adding numbers, or are we adding 0? If we're adding 0, it may or may not converge. But if we're adding anything else but 0, it's definitely not going to converge because it's always going to be getting bigger and bigger. In fact, that also works if the limit does not exist or if the limit is infinity. Then the sum as n goes from 1 to infinity of a sub n diverges. So if the terms aren't ultimately going to 0, then the series is not going to converge. Let's take a look at some examples. Let's first try the sum as n goes from 1 to infinity of n over 3n minus 1. Well, to use the divergence test to see what's happening, we can take the limit as n goes to infinity of n over 3n minus 1. And we know that the higher powers, the n over 3n, are going to take over, and that's going to ultimately equal 1/3, which is definitely not equal to 0. In other words, once we get out to enough terms, we're basically doing plus 1/3, plus 1/3, plus 1/3, plus 1/3, and that's going to keep getting bigger and bigger. So because that does not equal 0, therefore we will say this series will diverge. Anytime the limit as n goes to infinity of the individual terms is not 0, it will diverge. So if we tried to find the sum as n goes from 1 to infinity of the cosine of 1 over n squared, we can do the same thing. We'll take the limit as n goes to infinity of the individual terms, cosine of 1 over n squared. Well, if n gets huge, this becomes 1 over a huge number, which basically means we're taking the cosine of 0, and we know the cosine of 0 is equal to 1, which again is not equal to 0. So eventually we're just doing plus 1, plus 1, plus 1, plus 1, plus 1. That's never going to settle out at a number. Therefore, this series diverges as well. Let's try one more example. Let's take the sum as n goes from 1 to infinity of n plus 1 over n squared minus 3n plus 1. Well, again, our strategy for the divergence test is we're going to see what happens if the limit as n goes to infinity of n plus 1 over n squared minus 3n plus 1. Here you'll notice the n squared has the highest exponent, so it's going to take over, which means the denominator is going to become huge, and we'll have a small number divided by a huge number, which is 0. So now in the end, this one is eventually doing plus 0, plus 0, plus 0. But here's the catch about the divergence test. If the limit equals 0, that does not mean it converges, because sometimes it will converge and sometimes it will diverge. So when the limit equals 0, we say the test is inconclusive. When we're inconclusive, we're going to have to do some other testing, and that's really what the rest of this chapter is going to be about. But for now, we're just going to say inconclusive. So that's the divergence test. If the limit as n goes to infinity of the individual terms goes to anything but 0, we know it diverges. If it equals 0, we don't really know anything. So we have another option to test, and this is what is called the integral test. By the way, the integral test only works if all the terms are positive. If we have negative terms, the integral test will not work. So alternating series don't work. Even if there's one term that's negative, the integral test won't work. But if all the terms are positive, and we're looking at the sum as n goes from 1 to infinity of some series, what we'll do is we will let the function f of n be equal to the individual terms. And we will take the integral from some number, any number we want, up to infinity of f of n dn. This integral and the original sum will either both converge or both diverge. So if we can take the integral, they will both do the same thing. So if the integral equals infinity, the sum equals infinity. If the integral equals a number, the sum also equals a number, but they are not necessarily the same number. It just means that they both converge to a number. So let's take a look at some examples. Let's take a look at the sum as n goes from 1 to infinity of 1 over n to the 4th. If we use the divergence test on this, the limit as n goes to infinity we see is 0, so that's inconclusive. So what we'll do instead is we will use the integral test to see if it tells us something. We'll take the integral from, let's go from the first term 1 to infinity. And we don't like to integrate fractions, so I'm going to write this as n to the negative 4 dn, which we know is equal to n to the negative 3 divided by negative 3, which we know, let's simplify that a little bit further. We'll bring the n to the bottom. So we've got negative 3 n to the 3rd, and we're integrating from 1 to infinity. Well, if we plug infinity in, we get 1 divided by a huge number, which is 0. Minus, if we plug 1 in, we get a negative 1/3. And minus a negative 1/3 is positive 1/3, and it equals 1/3. The number doesn't matter so much as the fact that it equals a number. It doesn't equal infinity. Because the integral converges, the sum also converges. Because both the integral and the sum are going to do the same thing. Let's take a look at one more of these examples. Let's take the sum as n goes from 1 to infinity of n over 3n squared plus 1. Again, the divergence test says that this is going to 0, so it's inconclusive. So let's try the integral test. Let's take the integral from 1, because that's the lower limit, to infinity of n over 3n squared plus 1. Well, we're kind of set up for a u substitution, where u is 3n squared plus 1, du is 6n. So, oops, I forgot the dn. So we'll multiply by 6, and we will multiply by 1/6. And so that's going to give us 1/6 times the integral. And let's go ahead and plug the limits in. 3 times 1 squared plus 1 is 4 to infinity of 1 over u du, which is equal to 1/6 natural log of u, integrated from 4 to infinity. But when we plug the infinity into the natural log always gets bigger and bigger. We end up with infinity. So the integral diverges to infinity. And because both the integral and the series do the same thing, if the integral diverges, then the sum will also diverge. And so what we see here is a great example of how the divergence test is inconclusive, because both of these, the limit was 0. So we had to use a different test to decide one converged and the other diverged. Before we wrap up here, though, I want to talk about one special series. And this is a series, when we see it, we're going to just recognize whether or not it converges or diverges. It is called the p-series. A p-series is a series of the form as the sum going from 1 to infinity of 1 over n to the p power. If we were to do the integral test on this, we would take the integral from 1 to infinity of 1 over n to the p dn, or the integral from 1 to infinity of n to the negative p dn. And the exponent property says we increase that exponent by 1, and we divide by the new exponent, negative p plus 1. And if that's the case, we're integrating from 1 to infinity. When we plug that in, what we really end up with is, and this is going to be kind of loose notation here, not quite correct. We should be doing the limit as n goes to infinity, but I'm just going to write infinity in for the n. We get infinity raised to the negative p plus 1 over negative p plus 1 minus, then when you plug 1 in, 1 to any power is 1 over negative p plus 1. But the important thing to note here is infinity has an exponent of negative p plus 1. If this is in the numerator, then the whole thing goes off to infinity. But if that infinity ends up in the denominator, the whole thing goes to 0 and it converges. So this means it will diverge if the exponent, negative p plus 1, is greater than 0. Because if we have a positive exponent, then it will diverge. And if we solve this by subtracting 1 and dividing by negative 1, if p is less than 1, or really or equal to 1, because it is the harmonic series, if it's equal to 1. We already know the harmonic series. 1 over n diverges very slowly, but it diverges. And then the opposite is true, that it converges if the exponent, negative p plus 1, is negative, which moves the infinity to the denominator. Or if we add 1 and divide by negative 1, if p is greater than 1. So this is kind of the important idea, that the p series will diverge if p is less than 1 or equal to 1. Let's go ahead and write the or equal to in there. And it will converge if the exponent is greater than 1. And that can save us doing all the tests. We just have to look at the exponent if we're actually working with a p series. Let's try some examples really quick to wrap up this video. First, let's consider the sum as n goes from 1 to infinity of 1 over n to the 5/3. Well, this is a p series because it's 1 over n to some exponent, and that 5/3 is greater than 1. Because it's greater than 1, we know it converges. Similarly, we can look at the sum as n goes from 1 to infinity of 1 over n to the 2/5 power. Well, looking at that exponent, 2/5 is less than 1. Because it's less than 1, this p series diverges. So this will be an important series to add to our other series that we're familiar with, the harmonic series, the geometric series, the p series. These are ones we should recognize really quickly when they converge and when they diverge. So we're going to wrap up here, give you a chance to practice some of these, trying to decide using the divergence test and the integral test, or recognizing a p series, does this series converge to a number? We don't really care what number. Or does it diverge to infinity? Take a look at the practice, and we will see you in class to discuss it further. When working with series and trying to decide if they converge or diverge, we have the divergence test to see if it diverges. And if that's inconclusive, we can try the integral test. However, the integral test only works if all the terms are positive and if we can take the integral. Some integrals are difficult or impossible to take, and so we need another method to try and determine if series converge or diverge if one of those first two fail. And so one idea that might come up is to use a series we know to establish something about a series we don't know. The question here is going to be, can known series help determine convergence of an unknown series? And obviously the answer is yes, because that's what we're taking a look at. So let's see about this first one called the comparison test. The idea of the comparison test is if I know a series converges, so we'll say if the sum as n goes from 1 to infinity of maybe the series B converges, and I've got some other series where each term is smaller than the B term, but still positive, still greater than 1, then, well, if every term of A is smaller than B, and B converges, then the series A must also converge. To something smaller than whatever the B converges to. But again, the important question is, does it converge or not? And we can kind of take the opposite logic as well. Let's say we've got a series that diverges. The series that we know diverges. Maybe it's the harmonic series or something like that. And every term of this series, A sub n, is bigger than every term of the series B, which we know already goes to infinity, which is also bigger than 0. That's important. These actually should have or equal to on them. Then, well, if series A is bigger than series B, which is infinity, series A must also diverge as well. Let's take a look at some examples where we can use this logic. Number 3. Let's consider the sum as n goes from 1 to infinity of 1 over n to the 4th plus 3n squared plus 2. And with the divergence test, this clearly goes to 0. But the integral of this is going to be very difficult to take. So let's see if we can compare it to something we know. We know something about the sum as n goes from 1 to infinity of 1 over n to the 4th. That's a power series where the exponent is bigger than 1, so it converges. Sometimes reciprocals are harder to think about, so first I'll look at the fact that if I take n to the 4th and I add something to it and add something more to it, that's going to be bigger than just the n to the 4th by itself. Well, if we took the reciprocal of this inequality, it's going to switch the direction of the inequality. Just going to show what we did there off to the side here on the left. 10 is bigger than 2. If we took the reciprocals 1/10, that would be smaller than the reciprocal 1/2. When we take reciprocals, the inequality switches direction. So what we've shown is our series is smaller than a known series. We know that known series converges. And so then our series, being smaller, must also converge, because it can't go to infinity if it's smaller than a convergent series. Let's try one more example. Let's consider the sum as n goes from 1 to infinity of 1 over the natural log of n. Again, as n goes to infinity, this goes to 0. And so what I might try and say is the natural log of n compared to some either an n or an n squared or some other p series that we know. Well, how does the natural log of n compare to n? If I think briefly about the graphs, natural log comes up and moves slowly. But n is a straight line that's going to grow much faster. The n is bigger than the natural log of n. Well, if I took the reciprocals, 1 over the natural log of n then must be bigger than 1 over n. And 1 over n, we know that's the harmonic series, so it's going to diverge. But if we've got something bigger than infinity, it must also go to infinity. It must also diverge as well. So if we can find a series that is bigger than our series that converges, we must also converge. If we find a series that's smaller than our series that diverges, we must also diverge. The order is important because if I found something bigger that diverges, that doesn't necessarily mean I diverge. And if I find something smaller that converges, that doesn't necessarily mean I converge. So we need to make sure the order is right to make this comparison test work. And sometimes it's not so clear from our comparison test exactly how the pieces come together. So maybe a more powerful test will be what we call the limit comparison test. And the limit comparison test says, consider a sub n and b sub n are greater than 0 for all n. In other words, we've got all positive terms. If we were to divide them, if we took the limit as n goes to infinity of their quotient, a sub n divided by b sub n, and that actually equals a limit, but not 0. Maybe it equals 4 or 2 or 1/3, 1/2. If it equals a specific limit that's not 0, then both converge or both diverge. They both do the same thing if the limit equals a number besides 0. If the limit equals 0, though, then we only know something if the denominator converges. If the denominator converges, that tells us the numerator also converges. If the denominator diverges and we equal 0, we don't know anything. It's inconclusive. Similarly, if the limit of the quotient is equal to infinity, and we add to that b sub n, the denominator, diverges, then the numerator will also do the same thing. Then a sub n diverges as well. So what we can do is take a known series and divide by the known series and take the limit as n goes to infinity. What we hope happens is that it equals a constant that's not equal to 0. If that's the case, they will both do the same thing, whether it's converge or diverge. If it does equal to 0, we hope that denominator converges, because then our numerator also converges. If it goes to infinity, we hope the denominator diverges, because the numerator also diverges. But if we don't get that second half, then the test also is inconclusive, and you have to use another test. But let's see how we can use this test with some examples. Let's find the sum as n goes from 1 to infinity of 3 over the square root of n minus 2. Now, I see that square root of the n in the denominator, so I think, OK, let's compare it with 1 over the square root of n, or 1 over n to the 1/2. That's a p-series. It diverges because the exponent is smaller than 1. Let's see what happens when we take the limit as n goes to infinity of our unknown series, 3 over the square root of n minus 2, divided by our known series, 1 over the square root of n. Well, let's simplify that by multiplying by the square root of n on top and bottom. When we do, the square roots of n's divide out, and we get the limit as n goes to infinity of 3 root n over the square root of n minus 2. And that's really nice, because those square roots of n, being the highest exponent, are going to take over, and we end up with 3 over 1, or just 3. Because that 3 is not equal to 0, they are going to both do the same thing. So we said our comparison diverges. Therefore, the sum as n goes from 1 to infinity of 3 over the square root of n minus 2, doing the same thing, also diverges. When we equal a number not equal to 0, they both do the same thing. Let's try another example. Let's consider the sum as n goes from 1 to infinity of 5 to the n plus 2 over 6 to the n. Divergence test, the 6 to the n takes over. It equals 0. The integral is difficult to take, so let's try a comparison test. Let's try to compare it with kind of a simple form of the 5 to the n over 6 to the n, which is 5/6 to the n. Plus 2 is probably not going to matter when we get off to infinity, so it's probably going to behave similar to the 5/6. Well, 5/6 to the n is a geometric series where the r is less than 1, multiplied by 5/6 over and over and over again. When the r is less than 1, we know that it converges. So let's see what happens when we take the limit as n goes to infinity of what we don't know, 5 to the n plus 2 over 6 to the n, divided by what we do know, 5 to the n over 6 to the n. Well, we're dividing fractions. So dividing fractions means we multiply by the reciprocal. So we get 5 to the n plus 2 over 6 to the n times 6 to the n over 5 to the n. 6 to the n's will reduce out, and we get the limit as n goes to infinity of 5 to the n plus 2 over 5 to the n. And as the n's get huge, we see those 5 to the n's are going to take over. Ultimately, the plus 2 is going to make very little difference, and this will equal 1, which is not 0. Because it equals a number that's not 0, they both, numerator and denominator, will do the same thing. Well, we said it converges in the denominator, so therefore our unknown sum of 5 to the n plus 2 over 6 to the n also converges. Because our limit equals a number, they both do the same thing. Let's try one more example. Let's take the sum as n goes from 1 to infinity of the natural log of n divided by n squared. Well, the natural log of n is smaller than n. So if I pick something bigger, we'd be thinking like n over n squared, which is 1 over n. So let's try that. 1 over n, let's compare it to 1 over n. 1 over n is the harmonic series. It diverges. So let's see what happens when we take the limit as n goes to infinity of the natural log of n over n squared divided by the known series 1 over n. Multiplying by the reciprocal, we get the natural log of n over n squared times n. The n divides out with the n squared. And so we get the limit as n goes to infinity of the natural log of n divided by n. Well, both of those go off to infinity. So let's try to L'Hopital it to see if that can help us figure out what the limit as n goes to infinity. The derivative of natural log of n is 1 over n. The derivative of n is 1. And now if n goes to infinity, we got 1 divided by a large number, which is 0, divided by 1, which is 0. So remember our rule about 0. If we equal 0, we need the denominator to converge. Uh-oh, our denominator diverges. So that is inconclusive. That doesn't actually tell us anything. So let's try a plan B. 1 over n did not work. So let's compare it maybe with 1 over n squared. We know 1 over n squared converges because it's a p-series where the p is greater than 1. So let's take the limit as n goes to infinity of the unknown natural log of n divided by n squared divided by 1 over n squared. Well, this one's going to simplify quite nicely when we multiply by the reciprocal. The natural log of n over n squared times n squared over 1. The n squareds divide out, and we're left with the limit as n goes to infinity of the natural log of n, which is infinity. So we go up to our rule. And if it equals infinity, that's only useful if the denominator diverges. Well, our denominator converges. So this tells us nothing. Back to the drawing board. So squared made us diverge. First power made us converge. Let's go somewhere in the middle between 1 and 2. So we might try 1 over n to the 3 halves. That's right in the middle. It's still bigger than 1 as an exponent, so it's a piece series that converges. So let's take, I didn't cross off the last one. That one was bad. Let's take the limit as n goes to infinity of the unknown series, the natural log of n divided by n squared, over the known series, 1 over n to the 3/2. Well, if we multiply by the reciprocal, we get the natural log of n over n squared times n to the 3/2 over 1. Now when we reduce, we're going to end up with a half left in the denominator. So we have the limit as n goes to infinity of the natural log of n over n to the 1/2. As you plug infinity in, you'll notice the numerator is going to infinity and the denominator is going to infinity. So we'll use L'Hopital's rule, which allows us to take the derivative of the numerator and denominator. The derivative of natural log of n, I'm just going to come down here to the next row. Limit as n goes to infinity. The derivative of natural log of n is 1 over n. The derivative of n to the 1/2, pull out the 1/2, and then subtract 1 from the exponent. You get n to the negative 1/2. That sticks it in the denominator. And so we'll multiply by the reciprocal again. 1 over n times 2n to the 1/2 all over 1. Subtracting the exponents, we get the limit as n goes to infinity of 2 over n to the 1/2. Reducing the exponents. And now as n gets really, really huge in that denominator, we get 2 divided by a large number, which is 0. So we go back to our rule. If it equals 0, we're happy if the denominator converges. Here, the denominator we used converges, and so we finally have a solution. Because the denominator converges and we equal 0, therefore the natural log of n over n squared also converges. So we're not as flexible when the limit equals 0 or infinity. When it equals 0 or infinity, it either needs to converge or diverge, depending on the direction we're at. But if it equals any other number, it's really convenient to use the limit comparison test. Because if it equals a number other than 0, they both converge or both diverge. Working with these takes a little bit of practice, identifying which series to use in the denominator. So practice a few of these. Take a look at the homework assignment. We'll discuss them more and practice more in class. Up to this point, we've been mainly working with series where the terms are all positive. But when the terms are negative, we have what's called an alternating series, where we have positive and negative terms bouncing back and forth. There's another strategy we can use to determine the convergence of an alternating series. So our question for the day is, how do we determine the convergence of an alternating series? And first, we'll just really define the alternating series a little clearer. Alternating series. There's two types, and they're almost identical. If we have the sum as n goes from 1 to infinity of negative 1 to the n plus 1 times some other series, basically what that does is when n is 1, we get 1 plus 1, which is 2, and negative 1 squared is a positive 1. So we just end up with the first b term.
But then when we go to the next one, we end up with an odd exponent, so we end up subtracting the second b, adding the third b, subtracting the fourth b, and so on and so forth, alternating between positive and negative. The other type, and it's really the same idea, the difference is that the negative one just has an n power. And what that does is it allows the first term to start out negative, and then we add the second term, subtract the third term, add the fourth term, and so on. Those are alternating series. And an interesting question that can kind of come up out of this introduction of alternating series, we've talked about the harmonic series, which diverges to infinity. What if we made the harmonic series into an alternating harmonic series? In other words, we were going to take a look at the sum as n goes from 1 to infinity of -1 to the n plus 1 over n. Because if we look graphically at what this does, if we call this 1 over to the right, the first term is going to be a positive 1, so we'll add 1. The second term is a -1/2, so we subtract 1/2. Then the next term adds 1/3. And then we end up subtracting 1/4. And what you see is happening is we keep going back and forth, but we don't go quite as far as we did last time. And it looks like we're actually converging down to a point on the line. And in fact, it does. The alternating harmonic series turns out to converge at the natural log of 2. And we can look at that a little more closely in class because there's some interesting stuff that happens there. But for now, what I want to point out, if we change a divergent series like the harmonic into an alternating series, sometimes it could turn out to be a series that actually converges. But this is not always the case. So we need some better rules to test the convergence of an alternating series. And so we have what is called the alternating series test. And the alternating series test says that an alternating series such as the sum as n goes from 1 to infinity of -1 to the n plus 1 times some b sub n terms converges if two things are true. First, each b sub n is positive, and the n plus 1 term is smaller than the nth term. In other words, every term we go to next is smaller than the one before it. And that's what happened with the alternating harmonic. We didn't quite go back as far, and then we didn't quite go back as far, and we didn't quite go back as far, and eventually that's going to pull us down to a point on the line. So each term needs to be smaller than the one before it. And the other thing that's important, and it's just the divergence test, that the limit as n goes to infinity of b sub n has to equal 0. We have to pass the divergence test with the b sub n without the alternating part. If that's true, if each term is getting smaller, and the divergence test works on the non-alternating part, then the series will converge. So let's take a look at some examples where we can use this alternating series test. Let's take a look at the sum as n goes from 1 to infinity of -1 to the n plus 1 over n cubed. Well, to do that, we will consider n plus 1 and n. Ignoring the alternating part, the negative 1 to the n plus 1. If we ignore the alternating part, we end up with 1 over n plus 1 cubed and 1 over n cubed. Well, if I think about the fact that n plus 1 cubed is going to be bigger than just n cubed, because we've added 1, we've got a bigger number we're cubing. The reciprocals then, 1 over n plus 1 cubed, must be smaller than 1 over n cubed. In other words, we've shown that the next term is smaller than the first term. If that's the case, the terms are getting smaller. Therefore, we can say this series converges. Let's try another one. Let's try the sum as n goes from 1 to infinity of negative 1 to the n times n over 2 to the n. To use the alternating series test, we consider the n plus 1 and the n to see if n plus 1 is smaller. Ignoring the alternating part, we just have n plus 1 over 2 to the n plus 1 and just n over 2 to the n. What I notice here is n does not grow nearly as fast as the denominators. The denominators grow faster. 2 to the 5th is a lot bigger than 5. 2 to the 12th is a whole lot bigger than 12. The denominators are growing much larger, so they're going to kind of take over. So when we compare those denominators, 2 to the n plus 1 is going to be bigger than just 2 to the n, because we've added 1 to the exponent, making it bigger. So the reciprocals, 1 over 2 to the n plus 1, must be less than 1 over 2 to the n. Therefore, multiplying both top and bottom by n, or n plus 1, they're basically the same amount, we can conclude that n plus 1 over 2 to the n plus 1 is less than n over 2 to the n. So what we found out is that the next term is smaller than the first term. And when that happens, we know that we will ultimately converge with our alternating series. So now that we've got some idea of this work with convergence and divergence with alternating series, we're ready to talk about what's called absolute convergence versus what's called conditional convergence. The idea behind absolute convergence is that the sum, as n goes from 1 to infinity, of your terms exhibits absolute convergence if the sum as n goes from 1 to infinity of the absolute value converges. However, we have conditional convergence if the sum, as n goes from 1 to infinity of your terms, exhibits conditional convergence if the sum as n goes from 1 to infinity of the original series converges, but the sum as n goes from 1 to infinity of the absolute value diverges. An example of number 2 here would be the harmonic series. When the harmonic series is positive, it diverges. But when the harmonic series is alternating, where we've got negatives and positives, it does converge. So we have conditional convergence with that example. Conditional convergence isn't very exciting to us because we're forced to use the alternating series test. But what's really interesting is the fact that absolute convergence if the positive form, in other words, ignoring the alternating part, if that converges, it implies convergence. In other words, if the sum as n goes from 1 to infinity of the absolute value of a series converges, then we know for sure that the sum as n goes from 1 to infinity of all the terms, positive or negative, also converges. Notice the opposite isn't true. If the original converges, does that mean the absolute value converges? Not necessarily. The alternating harmonic is a great example of that. But if the absolute value converges, then we know the entire thing converges. Well, what that means is if we can prove the absolute value converges, we can then work with alternating series by using the other convergence test. Looking for absolute convergence. So if we have maybe the sum as n goes from 1 to infinity of the alternating negative 1 to the n over 4n minus 1, we're going to take a look at the absolute value version of it, which means we're going to really see if the sum as n goes from 1 to infinity of 1 over 4n minus 1 converges. Well, I notice 1 over 4n minus 1 is really similar to 1 over n, which diverges. That's the harmonic series. So let's use the limit comparison test to see what happens when we divide these and take the limit as n goes to infinity. We take the unknown one, 1 over 4n minus 1, over the known one, 1 over 4n. Multiplying by the reciprocal, we have the limit as n goes to infinity of n over 4n minus 1. We know from experience the n's take over, and we get 1/4, which is not 0 or infinity. Therefore, we conclude that they both do the same thing. So because our 1 over n diverges, therefore, this one diverges absolutely. Which doesn't really tell us much. We like it when it converges absolutely, because then the original one converges. But this one does not converge absolutely. But it might converge conditionally. So now we go to the alternating series test. We will consider n plus 1 and n. When we use n plus 1, we get 1 over 4 times n plus 1 minus 1, and 1 over 4 n minus 1. which, if we simplify these, that becomes 1 over 4n plus 4 minus 1 is plus 3, and 1 over 4n minus 1. Well, if we were to compare these denominators, 4n and 4n are the same. So if I add 3 to one and subtract 1 from the other, the one we added 3 to is going to be bigger. So then the reciprocals, 1 over 4n plus 3, must be less than 1 over 4n minus 1. And so what we've shown is that the next term is smaller than the first term. If that's the case, the alternating series will converge. Therefore, it converges. Not absolutely, because when we did the absolute value thing, we diverged absolutely. But we do converge conditionally. Similar to the harmonic series, if it alternates, it converges. If it doesn't alternate, it diverges. So we've got conditional convergence here. Let's do another one. Example number 2, we're going to do the sum as n goes from 1 to infinity of the sine of n over n cubed. This doesn't look like an alternating series at first, but if you think about sine of n goes from positive to negative to positive to negative, oscillating between 1 and negative 1. So we're really going to end up with alternating signs here. So what we'll do is we're going to compare it by getting rid of the negative part. The sine is what makes it oscillate between 1 and negative 1. We can compare it with 1 over n cubed. And that we know converges because it's a p-series where the exponent is bigger than 1. All right, let's compare it to the absolute value of the sine of n over n cubed. Because the absolute value forces everything to become positive. We're looking for absolute convergence. Well, if we do that, compare it to having n cubed in the denominator, the absolute value of sine is never going to be bigger than 1, which means our series, every term is going to be less than or equal to 1 over n cubed. So we've got a smaller series than a known converging series. Therefore, our series, by the comparison test that we saw in the previous video, the sum as n goes from 1 to infinity of the absolute value of the sine of n over n cubed must converge. If the absolute value converges, then we have absolute convergence. And the original series without the absolute value also converges. So if we can prove the absolute value converges with either the integral test, the comparison test, the limit comparison test, or another test, then we have absolute convergence and the alternating series converges. If the absolute value diverges, then we check for conditional convergence by using the alternating series test. So that's how we can work with alternating series. Take a look at practicing these. Again, series take lots of practice to get comfortable with. So practice, practice, practice. Come to class with questions, and we'll talk about it more at that time. As we wrap up Chapter 5, we're going to ask kind of the last question, which is, what other test do we have that can be used for convergence?
That's kind of been the theme of Chapter 5. We started with the divergence test to see if the limit goes to anything but 0, then it definitely diverges. But if it goes to 0, it's inconclusive. So we could use the integral test. If we could take the integral easily, we could use a comparison test to see what's happening compared to a known series, whether by dividing or being smaller or bigger than that known series. We then looked at if we have an alternating series, what we can do in terms of converging absolutely, or if it doesn't converge absolutely, does it converge conditionally because the terms are getting smaller each time. And then to wrap it up, we've got 2 more tests that I want to look at here today. The first one is called the ratio test. And the ratio test is particularly helpful with factorials. If we have factorials in the problem, you can pretty much bet the best way to get at convergence is by doing the ratio test. And here's what the ratio test says. We're going to let the sum as n goes from 1 to infinity of all of our terms be the series that we want to see if it converges or diverges. And we're going to define Greek letter rho. It kind of looks like a P, but it's a Greek letter rho. Rho is equal to the limit as n goes to infinity of the absolute value of the n plus 1 term divided by the n term. And this is going to be useful because when we take that limit, one of 3 things is going to happen. If 0 is less than or equal to rho, which is less than, not equal to, just less than 1. If we get a number that's less than 1 for rho, then the sum as n goes from 1 to infinity of the entire series converges absolutely. Positive or negative, it will converge if rho is less than 1. If rho ends up being bigger than 1, then the series as n goes from 1 to infinity diverges. This is because if we're dividing and the next term is bigger, dividing will result in a bigger number than 1. However, there's a problem that comes out of this test, and that is if rho equals 1, we get no information. It doesn't happen often, but that's kind of the worst case scenario. If rho ends up equaling 1, we need another test. So let's see if we can do some examples with the ratio test and see how it works out. Let's start by doing the sum as n goes from 1 to infinity of 3 to the n over n factorial. I mentioned that this test is best with factorials. So we define our rho as the limit as n goes to infinity of, in the numerator, we replace n with n plus 1. We have 3 to the n plus 1. Actually, let's do it this way. Over n plus 1 factorial. And then the denominator is just the a sub n term, which is 3 to the n divided by n factorial. Well, if we simplify this by multiplying by the reciprocal, we get rho is equal to the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 factorial times n factorial over 3 to the n, which is very interesting because n plus 1 factorial represents n plus 1 times n minus 1. Factorial multiplies by everything below it. Specifically, I could write n plus 1 times everything below it, which is n factorial. Which is nice because then the n factorials would divide out, leaving behind an n plus 1. With the 3's, 3 to the n plus 1 over 3 to the n, we can subtract the exponents, and the 3 to the n divide out, and we're just left with 3. So we have now the limit as n goes to infinity of 3
over n plus 1. And we know as n gets huge, this becomes 3 divided by a huge number, which is 0. Well, if rho is 0, our ratio test tells us in letter A up there that if rho is greater than or equal to 0, therefore, the sum as n goes from 1 to infinity of 3 to the n over n factorial converges absolutely. Actually, we could probably just say converges because there's no negative terms in this case. But we did determine from the ratio test that this first series converges. Let's do another example. Let's look at the sum as n goes from 1 to infinity. Let's take n to the n power over n factorial. Let's see what happens there. Well, now rho is equal to the limit as n goes to infinity of the numerator's the n plus 1 terms, so it's n plus 1 to the n plus 1 power over n plus 1 factorial divided by the regular series, n to the n power divided by n factorial. Well, if we multiply by the reciprocal, and I'm going to even break this up, the n plus 1 factorial, we're going to write that as n times n, we're going to write that as n plus 1 times n factorial. That way it's going to match down there. And the n plus 1 to the n plus 1 power, I'm going to rewrite that as n plus 1 to the n times n plus 1. That way, when you add the exponents, you get that n plus 1. So now multiplying by the reciprocal, we have n plus 1 to the n times n plus 1 over n plus 1 times n factorial times n factorial over n to the n power. And that's nice because one of the n plus 1s can divide out with the denominator. The n factorials can divide out. And we're just left with n plus 1 to the n, limit as n goes to infinity, n plus 1 to the n over n to the n power, which if we play with this, we get n to the infinity. Both of those are to the n power, so we have n plus 1 over n to the n power, which is equal to the limit as n goes to infinity. If I divide both terms by n, we get 1 plus 1 over n raised to the n power. But this guy, the limit as n goes to infinity of 1 plus 1 over n to the n power, should look familiar. Way back when we talked about limits, we found out that the limit as n goes to infinity of 1 plus 1 over n to the n power, that goes to e. That's one way that we can define e, is that limit right there. So the whole thing's equal to e, which is definitely greater than 1. It's almost 3, a little less than 3. And we know from the ratio test that if we're greater than 1, the series has to diverge. So therefore, the sum as n goes from 1 to infinity of n to the n over n factorial diverges to infinity. So a lot of these we massage algebraically to reduce so we can figure out the limit. Let's do one that's an alternating series before we step away from the ratio test. Let's consider the sum as n goes from 1 to infinity of negative 1 to the n times n factorial squared over 2n factorial. Well, rho, technically rho, we've been leaving it off on the past two, but technically rho says it's the absolute value of the quotient. So because it's the absolute value of the quotient, we don't really need to worry about the -1 to the n part, because the absolute value will just always make it positive. So really, our numerator, we've just got n plus 1 factorial squared over 2 times n plus 1 factorial all over n factorial squared divided by 2n factorial. Well, as I simplify this, the 2 times n plus 1 is really 2n plus 2 factorial. So if we break that up, counting down so that it'll divide out with a 2n factorial, that's really 2n plus 2 times 2n plus 1 times 2n factorial as it counts down. Similarly, the n plus 1 factorial squared is an n plus 1 squared times n factorial squared, just counting down and putting the squared on both parts because the whole thing's squared. So when we multiply by the reciprocal, oops, I forgot the limit as n goes to infinity. The limit as n goes to infinity of, we have n plus 1 squared times n factorial squared divided by n factorial squared. Oops, I'm getting ahead of myself. Finish out the first fraction. Divided by 2n plus 2 times 2n plus 1 times 2n factorial. And then multiply by the reciprocal, which is 2n factorial over n factorial squared. And let's see what we can divide out here. The n factorial squareds are gone. The 2n factorials are gone. And that's it. So we've got the limit as n goes to infinity of, and let's go ahead and multiply out that numerator. Becomes n squared plus 2n plus 1. Multiplying out the denominator, 2n plus 2 times 2n plus 1 is 4n squared plus 6n plus 2. And we know that the larger exponents are going to take over, so it's going to become 1/4, which is less than 1. And so the ratio test tells us that if we're less than 1, it's going to converge absolutely. And we know if it converges absolutely, it also converges for the actual series. So the sum as n goes from 1 to infinity of -1 to the n times n factorial squared over 2n factorial converges absolutely. So that is the ratio test. Really helpful with factorials because it allows us generally to reduce out the factorials by just breaking up maybe the n plus 1 from the n factorial. Maybe we have to do a couple terms. And then if our row is less than 1, it converges absolutely. If it's greater than 1, it diverges, and we hope it doesn't equal 1 because then we have no information and we need another test. A second test that's useful as we wrap up the chapter, though, is what's called the root test. And the root test is really helpful with powers of n. The reason it's helpful with powers of n is because it ultimately is going to take the nth root and get rid of that power of n. So let's let the sum as n goes from 1 to infinity of a sub n be what we're looking for, trying to decide does it converge or diverge. And we're going to also define a row in this case. But here, rho is going to be equal to the limit as n goes to infinity. It's a terrible infinity. As n goes to infinity of the nth root of the absolute value of the a sub n term. If rho equals that, one of three things will happen. Very similar to the ratio test. If 0 is less than or equal to rho, which is less than 1, then the series converges absolutely. And if that rho is greater than 1, then the series diverges. And just like last time, if rho is equal to 1, we have no information. So we'll have to use some other test to decide if it converges or diverges. Again, this root test is really helpful with powers of n. So let's take a look at a couple of examples. Starting with taking the sum as n goes from 1 to infinity of 3n cubed minus 7n squared plus 1 raised to the n power all over 4n cubed plus 2n squared minus 1 all raised to the n power. Well, when I see those powers of n, we're going to use the root test with rho equal to the limit as n goes to infinity of the nth root of our terms, 3n cubed minus 7n squared plus 1 to the n over 4n cubed plus 2n squared minus 1 to the n. And what's nice about that is the nth root takes care of those nth exponents as we take the nth root of the numerator and denominator. So we're left with the limit of 3n cubed minus 7n squared plus 1 over 4n cubed plus 2n squared minus 1. And we know the largest exponents take over, which is going to leave this with just 3/4. 3/4, which is less than 1. And the root test, just like the ratio test, tells us that if we end up with a limit, a rho that is less than 1, the whole series converges absolutely. So therefore, the sum as n goes from 1 to infinity of 3n cubed minus 7n squared plus 1 to the n over 4n cubed plus 2n squared minus 1 to the n converges absolutely. Whether positive or negative, it converges. Let's try one more example of the root test. Let's take the sum as n goes from 1 to infinity of n to the n power over the log, or let's do the natural log. The natural log of n raised to the n power. Again, rho is going to be equal to the limit as n goes to infinity. Because we have n powers, we're thinking the root test, where we take the nth root of n to the n over the natural log of n to the n power. Well, the nth root and the nth exponents will be inverses of each other, leaving us with just the limit as n goes to infinity of n over the natural log of n. The problem here is that as n goes to infinity, the numerator goes to infinity, and the denominator also goes to infinity. So what we'll have to do is use L'Hopital's rule, which says we can take the derivative of the top and bottom. The derivative of n is 1. The derivative of natural log of n is 1 over n, which means we have the limit as n goes to infinity, multiplying by the reciprocal is just n. And as n goes to infinity, n goes to infinity, which is much larger than 1. And so the root test, just like the ratio test, tells us if rho is greater than 1, then the series, as n goes from 1 to infinity of n to the n over the natural log of n to the n power, diverges. So we have 2 tests today to wrap up our work with sequences and series, trying to decide if series converge or diverge. We have the root test, which is good for powers of n, where rho is the limit as n goes to infinity of the nth root of the absolute value. And we have the ratio test, where rho is the limit as n goes to infinity of the n plus 1 over the nth term. And that one's helpful with factorials. Once we do that and calculate our rho, the process is the same. If rho is less than 1, we converge absolutely. If rho is greater than 1, we diverge. If rho equals 1, we have no information. Take a look at the homework assignment and try a few of these, and we'll discuss them in class further and answer any questions that you might have.
Now that we've gotten comfortable with various series and deciding if a series converges or diverges, we're going to look at some specific series that have some important properties that actually make calculus a lot easier to work with when the equations are complex. Our question's going to be, when does a power series converge? So first, we got to make sure we understand what we're talking about when I say power series. A power series is a very special series. It can be either centered at 0 or any other value. So first, kind of the simple version of a power series is a power series centered at x equals 0 is of the form the sum as n goes from 0 to infinity of some constant, and that constant varies based on the term, times x to the n power. In other words, if I wrote it out, it's basically a polynomial. The first constant plus another constant times x plus another constant times x squared plus another constant times x cubed, and so on and so on. And this is when the power series is centered at 0. We can shift it and actually do a power series centered at x equals a, some other number, which is of the form the sum as n goes from 0 to infinity of those same constants. But now instead of x, it's going to be x minus a to the n power. Which means if we were to write this out, when n is 0, the x part goes away. And so we get the first constant, or c sub 0, plus c1 times x minus a to the first power, plus the next constant times x minus a to the second power, plus the next constant times x minus a to the third power, and so on and so forth. And so let's take a look at some examples of power series so we can get an idea of what we're talking about. An example of a power series would be something like 1 plus x plus x squared plus x cubed and so on and so forth. That's a power series because we're looking at all the different powers of x. We could even write that as equal to the sum as n goes from 0 to infinity of x to the n power. In fact, we can make our power series as interesting as we want. Maybe we could make it 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on, where we're dividing by the exponent factorial. You can kind of see the first one we're dividing by 1 factorial and 0 factorial as well. But both those are equal to 1, so we don't need that. So this power series then is really the sum as n goes from 0 to infinity of x to an exponent, and then we divide by that exponent factorial. Let's look at one more example of a power series. We're going to do 1 plus the x minus 2 divided by 2 times 3 plus x minus 2 squared divided by 3 times 3 squared plus x minus 2 cubed divided by 4 times 3 cubed, and so on and so forth. This is also a power series because we see that x minus 2 squared, cubed, fourth power, and so on. So what we end up with is the sum as n goes from 0 to infinity of the x minus 2 raised to the n power divided by, and what we notice is if we look in the denominators, we've got 2, which is 1 more than the exponent of 1, 3, which is 1 more than the exponent of 2, 4, which is 1 more than the exponent of 3. So we're really dealing with x plus 1 times 3 to the, and you notice the exponent is always 1. No, the exponent's always exactly the exponent. So the exponent on 3 is the same as the exponent on the numerator. And so we end up with this power series. In fact, we could go one step further to classify these power series. You notice the first two don't have that x minus a property. The first two are centered at 0, while the last power series, because it's x minus 2, is centered at 2. So that's what a power series is. Now that we've defined what a power series is, the real question is, when does that power series converge? We're going to take a look at the convergence of a power series. And as it turns out, the power series the sum as n goes from 0 to infinity of those constants times x minus a raised to an exponent will always satisfy one of the following. It will either A, converge only when x equals a, or only where it's centered. Or B, it will converge for all real numbers x. Maybe it converges everywhere. Or C, and this one's a little more involved, it will converge if the absolute value of x minus a is less than some value r. For some r that represents the radius of convergence. I'll underline that term because we're going to use that a lot today. And what's really interesting, though, is while when x minus a, the absolute value is less than r, what we don't know is when the absolute value of x minus a equals r, it may or may not converge. Kind of to visually see these three options, option A, if I've got a number line of all possible values for x, and right in the middle is a, it could converge only on that value a, and then diverge everywhere else. So that's the case where it converges only at a. Or, same number line, we might have a value a in the middle where it's centered, and it really converges everywhere. It converges for all real numbers. Or C, that same number line. And then off to the right, we're going to add the radius, and off to the left, we subtract the radius. And what that does is give us a range of values where it converges. And outside of those values, it diverges. But what's important to note in this case where we have a radius of convergence, it is not immediately clear what happens at those edges. It may converge and it may diverge. So we'll have to test those edges to get an idea of exactly what's happened. But only converges on the radius of convergence, where the absolute value of x minus a is less than r. And then we have to really decide what happens exactly at r. So if these are the three cases for x when the whole series will converge or diverge, what we're ultimately interested in finding then is what is the radius of convergence? On what interval does the series converge and diverge? To find the interval and radius of convergence, the easiest thing to do probably is to use the ratio test, which we know if rho is less than 1, it converges. So let's take a look at an example of a power series and see if we can determine where it converges or where it diverges. We're going to look at the power series as n goes from 0 to infinity of x to the n over n factorial, and see if it converges. Using the ratio test, then, we're looking for rho, which is equal to the limit as n goes to infinity. Careful not to confuse your variables. We're always taking n to infinity. Of the absolute value of the next term, x to the n plus 1 divided by n plus 1 factorial, divided by the current term, x to the n over n factorial. So if we simplify that, we get the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial we know is n plus 1 times n factorial times the reciprocal n factorial over x to the n, which is nice because it reduces with the n factorials dividing out. The x to the n divides out with the x to the n, so we're left with the limit as n goes to infinity of x to the first power over n plus 1. And really, it doesn't matter what x equals. As n gets huge, we're taking x divided by a huge number, which means this is going to equal 0. In other words, rho is equal to 0, which is less than 1 for all real numbers for x. Whatever number I pick for x, rho will always be less than 1. It's always going to be 0. So in this case, what that tells us is the sum as n goes from 0 to infinity of x to the n over n factorial, this power series converges for all x. In other words, the radius of convergence is infinity. It will converge no matter what x equals. If I wanted to express it as an interval, it converges from negative infinity all the way up to positive infinity. Because rho is always less than 1. This power series will always converge. But that doesn't always happen. Let's take a look at the power series. The sum as n goes from 0 to infinity of n factorial times x to the n. Let's run through the same process with this and see when it converges. Well, we have rho is equal to the limit as n goes to infinity of the next term, which is n plus 1 factorial, times x to the n plus 1, divided by the current term, n factorial, x to the n, using our ratio test. And we simplify that. We get the limit as n goes to infinity of n plus 1 is n plus 1 times n factorial, x to the n plus 1 over n factorial x to the n. Which is nice because the n factorials divide out, the x to the n divides out, and we're just left with the limit as n goes to infinity of n plus 1 times our x. Well, in this case, regardless of what x is actually equal to, when n goes to infinity, this whole thing is going to be infinity times our x, and it comes out to be infinity. To converge, we need this to be less than 1, but it is never less than 1. Because we're never less than 1, we don't really have a radius of convergence. In other words, what we can conclude, therefore, the sum as n goes from 0 to infinity of the power series n factorial times x to the n, it will diverge everywhere except one place. Recall that we always converge at least on the center, at least when x is equal to a. Well, this power series is centered at 0 because we're not doing x minus anything. So it diverges for all x not equal to 0. In other words, the radius of convergence, because we're only on one point, the radius is 0. And the interval of convergence, there's not really an interval. It's just the value at the center, which happens to also be 0. So that's the second case where it diverges everywhere except the center, which in this case happens to be 0. So when do we end up with an actual radius of convergence? Well, let's try that other series we played with earlier. Let's try the power series as n goes from 0 to infinity of x minus 2 to the n divided by n plus 1 times 3 to the n. Using the ratio test, rho is equal to the limit as n goes to infinity of the next term, which is x minus 2 to the n plus 1, divided by n plus 1 is n plus 2 times 3 to the n plus 1, divided by the current term, which is x minus 2 to the n, divided by n plus 1 times 3 to the n. And when I multiply by the reciprocal, we get x plus 2 to the n plus 1 divided by n plus 2, 3 to the n plus 1 times the reciprocal n plus 1 times 3 to the n. Oops, I put x plus 2. That should be x minus 2. Careful not to change the signs. X minus 2 to the n in the denominator. Reducing here, things become really nice. The x minus 2 to the n divides out with the n, leaving 1 behind. The 3 to the n divides out with the n, leaving 1 3 behind. And so what's left is the limit as n goes to infinity of an x minus 2 times an n plus 1 over a 3 times n plus 2. Not forgetting the absolute values that are around everything, because that's important here. Well, as n goes to infinity, we know the n term is going to take over, but notice it's the same n on numerator and denominator, which means we're going to end up with the coefficients of n, which is the absolute value of x minus 2 divided by the absolute value of 3, which is just 3. Well, that's interesting, because the first time when we took the limit, we ended up with a value that was always smaller than 1, so we said it was all real numbers. The second time we took the limit, in example number 2, we ended up with a value that's never less than 1, so we said it basically has no radius. But here we got x minus 2's absolute value over 3, which we want to be less than 1, which means what we've ended up with is an equation that we can solve for x. We've got the absolute value of x minus 2 over 3 is less than 1. Multiplying both sides by 3, the absolute value of x minus 2 is less than 3. Remove the absolute values, puts x minus 2 between negative 3 and positive 3. And adding 2 to both sides puts x between 5 and negative 1. What we have is a radius of convergence. The radius is what the absolute value is less than. It's less than 3, which means it's going to have a radius of convergence of 3 wide, 3 to the left and 3 to the right from the center. And it will converge on the interval from negative 1 to 5. However, we don't know what happens at negative 1 and at 5. Recall, we have to actually check those values. So let's go back and check those values. Specifically, let's see what happens at -1. Actually, I'll say at x equals -1. When x is equal to -1, our original series, we're going back to the beginning here, this original series that we're working with, if I plug -1 in for x, I get the sum as n goes from 0 to infinity of -3 to the n over n plus 1 times 3 to the n. Which is nice because the 3 to the n divide out, leaving behind a -1 to the n. And so we have the sum as n goes from 0 to infinity of -1 to the n divided by n plus 1. Notice those denominators are just counting up. When n is 0, it starts at 1, 2, 3, 4. We have 1/2, 1/3, 1/4, 1/5, 1/6. We should recognize that as the harmonic series. But because we have -1 to the n in the numerator, this is actually the alternating harmonic, which we know converges. So on our interval, when x equals -1, we can put a square bracket because we know the alternating harmonic series, which we end up with at -1, does converge. But we still need to see what happens at x equals 5, the other edge. If x equals 5, we have the sum as n goes from 0 to infinity of 5 minus 2, which is 3 to the n, over n plus 1 times 3 to the n, which, when the 3 to the n's divide out, leaving 1 in the numerator, is the sum as n goes from 0 to infinity of 1 over n plus 1. And so when we start plugging in values of n, we get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. We should recognize that as the harmonic series. And the harmonic series, which is not alternating, we've shown diverges. So at 5, it actually diverges. So we're going to do a curved bracket, which means we have a power series with a radius of convergence of 3, meaning x can be 3 away from its center. The whole series will converge when x ranges from -1, including -1, to 5, excluding the 5. So that's how we can decide if a power series converges. We'll use the ratio test and find out, does it converge only at the center for all real numbers or within some radius of convergence? And we can figure out what that radius is and exactly what interval works for x so that the series converges. But why are power series important? Power series are important to us because quite often we can represent functions as power series. And usually the power series is easier to do calculus with than the original function. So if we can represent the function as a power series, we'll do the calculus on the power series and save us a lot of grief. For example, we know the sum as n goes from 0 to infinity of a times r to the n. That's the geometric series. The geometric series is equal to the starting value a divided by 1 minus the ratio, given the ratio is less than 1. Because if the ratio is greater than 1, it ends up diverging. So if I have the function f of x equals 1 over 1 plus x cubed, I could represent that as a power series if I can make it look like a over 1 minus r. Well, we're not too far away from a over 1 minus r, because we've already got a 1 over 1. But instead of plus, if I make it a minus, and I think, what could I subtract that would be the same as adding x cubed? Well, if we subtract a negative x cubed, then we're in the same form, where r is equal to the negative x cubed. So we can go to our power series as n goes from 0 to infinity of a. A is the numerator, the starting value of 1, times r, which is what we're subtracting, which is negative x cubed, to the n power. Or cleaning that up, we have the sum as n goes from 0 to infinity. 1 times anything is just that. And I'm going to separate out the negative sign so we can see it's an alternating series, negative 1 to the n times x to the 3n. This power series then comes out to be the same value as 1 over 1 plus x cubed. Or we could write it out as the individual terms. When n is 1, everything comes out to just a positive 1. Minus, because we're alternating. I'm sorry, starting out when n is 0. Now when n is 1, we get a negative x to the third. Plus, when n is 2, we get x to the sixth. Minus, when x is 3, we get x to the ninth. Plus, and so on. I want to take a look visually at this function coming together. All right, what I've done here on Desmos is I've graphed the function we were working with, 1 over 1 plus x cubed. And then I'm going to start to build the power series that we found. The power series that we found was 1 minus x cubed is the first two terms. And notice that the blue line starts to kind of follow the red line. Now look what happens when we add x to the sixth. It gets a little closer. Minus x to the ninth. It gets a little closer. Plus x to the 12th. It gets a little closer. Minus x to the 15th. It gets closer. And as I continue to work through this power series, the graph will start to get closer and closer to the graph of 1 over 1 plus x cubed, eventually leveling out at exactly the right value. So that's how we can find a power series that gives us the exact same graph. Let's do one more example before we wrap up. Let's look at f of x equals x squared over 4 minus x squared. Now, if we want to be in power series form, we're OK with the numerator, but we do need a 1 minus. Right now, we have a 4 minus. So what I'm going to do is I'm going to factor that 4 out of the denominator, leaving behind a 1 minus, and now it's x squared over 4. But we don't like to have a constant in front of the denominator, so I'm going to pop that up to the numerator, which is going to give us x squared over 4 in the numerator, divided by 1 minus another x squared over 4. Now we're in power series form of a geometric series, where we've got the sum as n goes from 0 to infinity of the first term, which is the numerator, x squared over 4, times r, which is what's subtracted in the denominator, x squared over 4, raised to the n power. Well, if I want to clean that up a little bit, we'll have the sum as n goes from 0 to infinity of, if I multiply the exponents, we've got x to the 2n times x squared. Adding those exponents, we get x to the 2 plus 2n over 4 to the, we've got 1, 4, and putting the n on the denominator as well, 4 to the 1 plus n power. And we end up with a power series that's equal to the original function. So we looked at several things today in this video. We defined a power series. We're going to continue to work with them over the next couple videos. And then we looked at when the power series converges by identifying the radius of convergence and the interval where it converges. It'll either converge at the center, everywhere, or over a specific interval. And we used the ratio test to decide when that is. And then we concluded at looking at why power series are important by converting a known function into a power series, specifically looking at the geometric series. Later, we'll look at other series that aren't in the geometric series form that we can still convert into power series. But this is where we're going to start with for now. So take a look at the homework, practice a few of these, and we will see you in class. Now that we've taken a look at what a power series is and how to work with a power series, we're ready to actually do some calculus with power series. The question's going to be, how can power series make derivatives and integrals easier? And the brief answer to this is that often calculus is easier with a series than the function. For example, if the function f of x is equal to some power series from n to 0 to infinity of the constants times x minus its center a raised to the n power, then we know that the derivative of the function would be equal to the derivative of the power series. Well, what's nice about a power series is it's a sum of many terms that have the exact same form. So we can take the derivative term by term, or really we can take the derivative of the entire sum as n goes from 0 to infinity. And this c sub n is a constant. And the exponent we know comes out front. And then x minus a stays the same. And then the exponent is decreased by 1. Just using our exponent property, we've taken the derivative term by term. And we can do the same thing with the integral. The integral of f of x dx is equal to the integral of the power series. Well, going to the original power series as n goes from 0 to infinity. This time, we keep the same constant out front. And we know that we increase the exponent by 1 and divide by the new exponent. Now, there's a couple adjustments that we need to make to these definitions, though. First, let's look at the blue one, the derivative. When we take a derivative, remember the first term in a power series is a constant. And the derivative of a constant is always 0. So actually, it doesn't go from 0 to infinity. It actually goes from 1 to infinity, because that first term's derivative is 0. So we don't need to include it in our derivative. With the integral, we make up for that first term by having an extra constant. Now I'm going to add the constant before the sum because I don't want that constant to look like it's part of the sum. But the power series antiderivative does have a constant plus the sum of the antiderivative. And that kind of sticks that extra term back in there. So minor adjustments to the intuitive formula, just a couple things to be aware of. So if that's true, that we can just take the derivative term by term and the antiderivative term by term, what we can do is we can use what we know to find derivatives and antiderivatives. We know that for the function f of x equals 1 over 1 minus x, we know that's a geometric series sum as n goes from 0 to infinity, where the first term is 1, and we take the x to the n power. Based on what we know, we're going to find a power series for the function g of x equals 1 over 1 minus x squared, which is really equal to 1 minus x to the negative 2. Well, you might notice that that's very similar to the function that we know that we started with at the beginning. So we know that the function f of x is equal to 1 minus x to the negative 1. And if I take the derivative of f prime of x, we would bring the exponent out front, bring the exponent down by 1, times the derivative of the inside. The derivative of negative 1 is positive 1. I'm sorry, the derivative of negative x is negative 1. A negative and a negative makes a positive, which means our derivative is 1 over 1 minus x squared, which is what we're trying to find a power series for. So we know the power series for the first original function is the sum as n goes from 0 to infinity of x to the n. And we know the second function is its derivative. So we'll take the derivative term by term. Remember, we have to have n equals 1 because the first term goes to 0, to infinity. Bring the n out front, and we have x to the n minus 1. And we have just found a power series for an unknown function because it's the derivative of a known function. So if we can make that connection with something we know, we can use calculus to find the new power series. Here's another one. What if we want to find a power series for h of x equals the negative natural log of 1 minus x? Well, again, the function we know is 1 over 1 minus x. We also know that the antiderivative of f of x dx would be the natural log of the stuff, 1 minus x. And then we have to divide by the derivative of the inside, which is negative 1. And so the antiderivative of our known function is the negative natural log of 1 minus x. Well, if we know the power series for the original function is the sum as n goes from 0 to infinity of x to the n, we're just going to integrate that to get our new power series. Don't forget we need a constant plus the sum as n goes from 0 to infinity of x to the n plus 1 divided by n plus 1. One little thing that remains, though, is what is that constant c, so we make sure we're equal to the original function. Well, to figure out what's going on with that constant, we'll take the 0th term and see how much it is off by. So if we plug 0 in for our x, we get negative natural log of 1 minus 0, which is the negative natural log of 1, which is just 0. So our constant in this case is equal to 0. So we don't need the constant here. It's equal to 0. We're just going to say it's equal to the sum as n goes from 0 to infinity of x to the n plus 1 over n plus 1. And actually, all that n plus 1 stuff kind of seems silly to me, that we're shifting 1 over in the numerator and shifting 1 over to the denominator. Instead of shifting 1 over in the formula, let's shift one of our n's over, starting with n equals 1 to infinity. And now it becomes just x to the n over n. So that's how we can use calculus to move from a known series to a power series for an unknown series. If we can connect the known series to a derivative or antiderivative of the known series, we can just take the derivatives term by term, and we end up with our new power series. Another place that calculus comes in handy is with partial fractions and power series. So let's take a look at that really quick. Partial fractions and power series. And we're actually not going to take the antiderivative, but we're going to use the idea behind partial fractions to build an unknown power series. Let's say f of x is equal to 1 over 1 minus x times x minus 2. And we want to build a power series for this. Well, if we were to break it up into two fractions, a over 1 minus x plus b over x minus 2, we could use what we know about the form of a geometric series to change these into two geometric series. But first, we have to figure out what a and b is. So if we multiply across, we get 1 equals a times x minus 2 plus b times 1 minus x. If we let x equal 2, we end up with 1 equals b times negative 1. So b is negative 1. If we let x equal 1, we end up with 1 equals negative 1 times a. So a also equals negative 1. And so what we end up with then is that f of x is negative 1 over 1 minus x plus negative 1 over x minus 2. OK, let's see if we can massage these to get them in the right format where we have a geometric series form. Remember, a geometric series form is going to be a over 1 minus the ratio. The first one is actually already there. The second one, we're going to have to do a little bit of work with. One thing we can do on the second one is we're going to switch the order. So we have negative 2 plus x. That way the variable is on the right side. And then like before, we can divide out a negative 2 so that we just have 1 minus x over 2. And then that negative 2 needs to move up to the numerator so that we're in power series form. So what we finally end up with is negative 1 over 1 minus x plus negative 1 over negative 2 is 1/2 over 1 minus x over 2. Which means we're dealing with a power series, two power series added together. We've got the sum as n goes from 0 to infinity of the first term is the numerator, so that's the negative 1, times the ratio, which we're just subtracting x in the denominator, so the ratio must just be x to the n, plus the second power series, which has a first term of 1/2 because it's in the numerator, times what's subtracted in the denominator, x over 2, to the n power. And maybe I want to clean that up a bit. We've got the sum as n goes from 0 to infinity. I want to factor out ultimately an x to the n. So I'm putting that in onto both top and bottom, because it's not a power series unless we're multiplying by x to the n. Everything else becomes that constant out front. And so when we factored out that x to the n, we're left with -1 plus a 1 over, and in the denominator, we've got a 2 and a 2 to the n. So combine that together, we get 2 to the n plus 1 is our coefficient. And now we ended up with a power series that represents this function. We were able to do that because our partial fractions allowed us to break it into two geometric series looking parts. And we could make each part into a geometric series and factor out the x to the n to end up with our final partial fraction power series. One last point then to wrap up this video. Let's take a look at how we can take a power series and find a function. Doing the exact opposite process we were doing before. Before, we started with the function and we worked to find the power series. Now we're going to start with the function, which is the sum as n goes from 1 to infinity of 1 over x plus 4 to the 2n minus 1. And we're going to see if we can build this into a function that's equal to the sum. Well, one thing I notice is if we're trying to make it into a geometric, geometrics like to start at n equals 0. So what we're going to do is we're going to shift this power series down to n equals 0, which means we need to account for an extra n, if you will. So where we see the n, we're going to call it n plus 1. And that'll shift the 0 over 1. So if we replace that n with n plus 1, we get 1 over x minus 4 to the 2 times n plus 1 minus 1. And a little bit of algebra in that exponent gives us 1 over x minus 4 to the 2n plus 2 minus 1 gives us a plus 1. Well, I'm going to keep trying to massage this as we work to figure out where our geometric series form might be. When we see that addition inside an exponent, we can break that into a product. So let's see what that gives us. The sum as n goes from 0 to infinity of 1 over, and I'm going to do the first power first, x minus 4 times 1 over x minus 4 to the 2n. Well, notice we're getting really, really close. Oops, it's a plus 4, isn't it? I've been writing this wrong. Make sure we're not changing our signs halfway through the problem. Sorry about that. We're getting really close to that geometric form, because the geometric form says we've got our first term times our second term, which needs to be raised to the n power. So if we could write that second part as something to the n power, we'd be in business. And if we go as n goes from 0 to infinity of 1 over x plus 4 times, what's nice about a numerator of 1 is it can be written as 1 to the n. So if I pull out an n power, we're left with x plus 4 squared in the denominator. In fact, we could even write that as 1 over x plus 4, the entire thing squared, because the 1 squared doesn't matter. And now what we've got is we've got our first term, which becomes the numerator, and the ratio which is subtracted in the denominator. Recall that the sum as n goes from 0 to infinity of a times r to the n is equal to the numerator a over 1 minus the r. So in our case, the numerator a is the 1 over x plus 4. Over the denominator, 1 minus the ratio that's multiplied is 1 over x plus 4 squared. But this is really an ugly format. So to get rid of the fractions and fractions, remember we've got x plus 4 squared in the denominator. So we're going to multiply by x plus 4 squared on top and bottom. It's going to distribute through. And so what we'll end up with is a single x plus 4 in the numerator. And x plus 4 squared minus, and the x plus 4's divide out, so it's just minus 1. And we end up with this final function that is equal to the original sum that we started with. So sometimes we can kind of parse this power series apart to find the pieces of the geometric sum, if we are in fact in a geometric form. If it's not a geometric series, we're going to need a new game plan. And that's what we're going to take a look at in our next video. But for now, take a look at how we can take derivatives and antiderivatives of known power series and unknown power series, and then also how the partial fractions can help us find power series, and break up a power series to find a function. Good luck, and we will see you in class. Thus far, we've focused our attention of power series on geometric series. Everything relates to a geometric series and can be written in the form of a geometric series. But that's actually not the case. In fact, most functions cannot be written in the form of a geometric series. So the question that we're going to try and address today is, how do we find a power series for other functions? And the answer to that is what are called a Taylor series and maclaurin series. And Taylor and maclaurin developed these processes independent of each other, and there's a slight difference between the two of them. Taylor's is probably the most well-known because it's the most versatile. Taylor said a series for a function at the point A is the function at A plus the first derivative at a divided by 1 factorial times x minus a to the first power plus the second derivative at a over 2 factorial times x minus a to the second power plus the third derivative, and we'll just put a little 3, at a divided by 3 factorial times x minus a to the third power, and so on and so forth. Ultimately, we're adding the nth derivative at a divided by n factorial times x minus a to the nth power, on and on and on to infinity. In other words, it is the sum as n goes from 0 to infinity of the nth derivative at a divided by n factorial times x minus a to the n. This is what is called a Taylor series. Now, maclaurin wasn't quite as versatile when he came up with his version of this same result. Maclaurin said basically the same thing, a series at, but Maclaurin kept it at a equals 0 and didn't expand it to any a. So if we plug 0 in for all the a's, we basically get what's called a Maclaurin series, which is f of 0 plus the first derivative at 0 divided by 1 factorial times x to the first, plus the second derivative at 0 divided by 2 factorial times x to the second, plus the third derivative at 0 divided by 3 factorial times x to the third, and so on and so forth. And so what you see is we're ultimately taking the nth derivative at 0, dividing by n factorial times x to the n, and we keep going all the way up to infinity. In other words, it can be summarized as the sum as n goes from 0 to infinity of f to the n at 0 divided by n factorial times x to the n, and we get a Maclaurin series. And really, a Maclaurin series is a special case of the Taylor series because it's just when a equals 0. Turns out the algebra is a lot nicer when a is 0 for a Maclaurin series. But the process is exactly the same. The idea is if we can identify the generic form of all of the derivatives at the point, we can write it as a Maclaurin or Taylor series. Let's take a look at how we can write any function as a power series. We're going to find either the, well, let's start with Maclaurin, actually. Let's start with the Maclaurin series. Sometimes they're called Maclaurin polynomials. A Maclaurin polynomial is not infinite. It stops at a certain point. But if we make it into a series going all the way to infinity, we can find a Maclaurin series, for example, for f of x equals e to the x. And so we're going to start to look for a pattern that's going to occur with the derivatives. So f of x, actually, let's start with f of x. We know f of x is e to the x. The first derivative is also e to the x. The second derivative is also e to the x. And so we can see pretty quick that any derivative is just e to the x. And since this is a Maclaurin series, we're actually going to plug 0 into all of these. Well, e to the 0 is 1. The first derivative at 0 is also 1. The second derivative at 0 is also 1. And so on and so forth. We see that any derivative at 0 is e to the 0, which is equal to 1. So we can build this Maclaurin series by saying, OK, e to the x is equal to, first, the function at 0, which is 1, plus the first derivative, which is 1, over 1 factorial times x to the first, plus the second derivative, which is 1, over 2 factorial times x squared, plus, and so on, continuing with this pattern until we have the nth derivative, which is 1, over n factorial times x to that n power, and so on. Well, if we've seen this pattern building, essentially we have the sum as n goes from 0 to infinity of all of the x to the n's divided by n factorial. This series, then, is equal to the e to the x function. In fact, in certain contexts, as we continue our study of mathematics, it's more convenient, instead of working with e to the x, to work with the power series, the sum of x to the n over n factorial. This one wasn't too interesting, though, because all of the 0 points ended up being equal to 1. So let's see if we can find a Maclaurin series for something a little more interesting. How about f of x equals the sine of x? Well, if we start building our derivatives, f of x is the sine of x. f prime, the derivative of sine is cosine. The second derivative is negative sine. The third derivative is negative cosine. And the fourth derivative then becomes positive sine. And so we're starting to cycle back through sine, cosine, negative cosine. OK, let's plug 0 in, because that's what Maclaurin wants us to do. The sine of 0 is equal to 0. The first derivative at 0 is the cosine of 0, which is 1. The second derivative at 0 is the negative sine. Well, negative sine of 0 is 0. The third derivative at 0 is negative cosine, which is 1, so negative 1. And then the fourth derivative at 0 is going to start to cycle back through our answers. And so we end up with coefficients of 0, 1, 0, negative 1, 0, 1, 0, negative 1, which means all of the odd terms, the first term, the third term, the fifth term, and so on, are all going to be 0 because we're multiplying by that derivative. So we don't really have any odd terms. The first term is 0, or the 0th term is 0. And now for the first term, we'll take x to the first power divided by 1 factorial times the derivative of 1. The second derivative is 0, so we have 0. When we do the third derivatives, the third derivative is negative 1 times x to the third over that 3 factorial. The fourth derivative is 0, but the fifth goes back to x to the fifth over 5 factorial. Then we're going to do minus, and you start to see the pattern forming. The 6th power goes to 0, but the 7th power is negative x to the 7th over 7 factorial, and so on. So we need a way to represent this pattern so we can convert it into a series. Well, one thing that I notice is we are alternating positive, negative, positive, negative. So we've got a negative 1 to the n to give us that alternating series. Notice when n is 1, actually, we're going to start at 0. So when n is 0, negative 1 to the 0 is a positive 1, which matches our first term. So that's good. Then we've got x raised to an exponent. But the exponents on x are all the odd numbers. So we can't just say n. What we can say, though, if 2n is the odd numbers, 2n plus 1, I'm sorry, 2n is the even numbers. Adding 1, 2n plus 1, becomes all the odd numbers. So as you can see, when n is 0, the first term has x to the first. When n is 1, plugging 1 in, we end up with x to the third. When n is 2, the second term, remember that we're starting at 0, 0, 1, 2, we end up with 2 times 2 plus 1, which is 5. So those exponents work out, and we're dividing by that same exponent, 2n plus 1 factorial. And that's going to continue forever as we end up taking the sum as n goes from 0 to infinity of that exact thing we just found. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This is our Maclaurin series, our power series, that is exactly the same as the sine of x. I want to take a look at this on Desmos, because I really think this is amazing when you see the graph work out. OK, what I've done on here is I've graphed sine of x. We know sine of x starting at 0, going up and down, period of 2 pi, amplitude of 1. That's not very exciting. But what we've just found out is that the Maclaurin series, which starts with x over 1 factorial, and then it's going to be alternating with the odd exponents, should be exactly the same as this graph. And this is really neat to watch it build. When we subtract x cubed over 3 factorial, it starts to bend with the graph. Then we add x to the 5th over 5 factorial, and it continues to bend with the graph. Subtract x to the 7th over 7 factorial, and it gets even better. Add x to the 9th over 9 factorial, and it gets even better. And if we keep going, we're going to get more and more of the graph building up as it stretches out and out. And eventually, when you get to an infinite number of terms, you've got the entire sine x curve from this power series. So what we've done is we've changed the sine of x into a polynomial. Polynomials are much easier to work with as we get to more complex operations. So that's how we can build a Maclaurin series. We find all the derivatives, we plug 0 into all the derivatives, and we look for patterns in this Maclaurin series format, where we're taking the first term, then times x over 1 factorial times x squared over 2 factorial times x cubed over 3 factorial, all the way up. And ultimately, we're just trying to find that generic form so that we can change it into a series. That's Maclaurin. Let's take a look at Taylor, because Taylor's a little bit more versatile. We're going to find some Taylor polynomials. And series. A polynomial is finite, a certain number of terms. A series goes off to infinity. And we're going to start simply with f of x equals 1 over x. And we're going to find this Taylor series at a equals 1. We're going to plug 1 into all the derivatives. And then we're going to have x minus 1 squared, cubed, 4th power, 5th power, and so on. So first, f of x, our function, is 1 over x. Or let's actually write it as x to the negative 1. We can convert it so that we can see what it is. Our first derivative, then, is negative x to the negative 2, or negative 1 over x squared. Our second derivative is positive 2x to the negative 3, so 2 over x cubed. And our third derivative, notice if we pull the negative 3 out, we end up with negative 3 times 2 times x to the negative 4. Or negative 3 times 2 over x to the 4th. And the reason I write it like that is you can sort of start to see a factorial forming in this numerator. You can see next time it's going to be 4 times 3 times 2. Then 5 times 4 times 3 times 2. It's going to count down. So we're ending up with those factorials in the numerator. That's going to be really helpful to us as we come up with a generic form. All right, we're doing it at 1. So we're going to plug 1 into each of these. 1 divided by 1 is 1. The derivative at 1 is negative 1 over 1, which is 1. The second derivative at 1, well, the denominator is just 1, so we end up with 2. The third derivative at 1 gives us negative 3 times 2. And you can kind of see we're building towards the nth derivative at 1 is going to have an n factorial, as we said. Next time it's going to be 4 times 3 times 2 times 1. We just have to worry about the fact that it's an alternating series. We want it to start out positive on the 0th term, on the 0th derivative. So we'll just do the n power. And in much the same way, we can use the Taylor formula to start building, then, that 1 over x is equal to, and let's see if we can jump right to the generic form, the sum as n goes from 0 to infinity of the derivative pattern. Notice our derivative pattern was negative 1 to the n times n factorial. Then we divide by an n factorial times x minus our a, which is 1, raised to the n power. But this one's really interesting because the n factorials actually divide out. So what we really have is the sum as n goes from 0 to infinity of negative 1 to the n times x minus 1 to the n power. And we have ended up with a power series that is equal to the function 1 over x. Let's try one more. Finding another Taylor series. We did cosine last time. We did sine last time. Let's do cosine this time. And let's do it at a is equal to pi. Pi is a nice number to stick into cosine. And so in much the same way, we're going to run through the derivatives. The 0th derivative is cosine x. That's the regular function. First derivative is negative sine x. Second derivative is negative cosine x. The third derivative is positive sine x. And the fourth derivative, we start to see it cycling back to cosine. This time, because it's a Taylor series, though, we're not plugging 0 in, we're plugging pi in. Well, the cosine at pi is negative 1. Negative sine at pi, the first derivative, is 0. The second derivative, negative cosine. Well, cosine at pi is negative 1. The opposite of negative 1 is positive 1. And then the third derivative at pi is also 0. And then you can start to see at the fourth derivative, it's going to start to cycle around. Might be a little trickier to see the pattern of the derivatives off the bat here. So we're going to go ahead and build a couple terms and see if that helps us see the pattern. The first term is, or the 0th term, I should say, is negative 1. So cosine x equals negative 1. Then our first derivative is going to be a 0. So that all goes to 0. For the second derivative, we end up with 1 times the x minus pi to the second power divided by 2 factorial. Then a 0. Then another negative 1, x minus pi. This is now the fourth derivative, fourth power divided by 4 factorial. And you start to see the pattern. This time it's the even exponents times x minus pi. The next one's going to be to the 6th power over 6 factorial, and so on. So can we come up with a generic formula? Well, it's an alternating series. But this time, the first term is negative. So we need to stagger. Negative 1 to the n will make the first term positive. Negative 1 to the 0 is positive 1. So if we do n plus 1, that'll stagger us by 1. And then all we have left is the x minus pi to the, what power now? This time we ended up with the 0th term, the second term, the fourth term, the 6th term. This time we have the even exponents, the even terms. So to get even numbers, we'll do 2 times n, and we'll divide by that 2n factorial as it keeps going. So what we end up with is that the cosine of x is really equal to the Taylor series as n goes from 0 to infinity of negative 1 to the n plus 1 times x minus pi to the 2n over the 2n factorial. We should have that 2n in parentheses. And this one is centered at pi because we did at pi at a equals pi. What does that mean, centered at pi, as opposed to the maclaurin series, which was centered at 0? Well, let's go back to the graph to discuss that. Notice when we started to build the sine of x as a maclaurin series, it was centered at 0. And if I start deleting these terms off, you see ultimately where the function started building was from the center of 0. But if I do a cosine x, I'm going to have to move the graph over a bit. And now if I start building negative 1 plus x minus pi squared over 2, you start to see where it's building is right at pi. If I do x equals pi and put a line here, that's the center. And now if I go minus x minus pi to the 4th power over 4 factorial, that 2 should be factorial as well, but that doesn't really make a difference. You see it's starting to build that cosine, but it starts building from the center of pi. And if we keep going, we'll get closer and closer to the actual function. Over 8 factorial, and we've almost got a full period now. And if we keep going off to infinity, you can see how we'd end up eventually with the entire graph forming from a center of pi. So Taylor allows us to start building the graph from any point. Maclaurin always builds the graph from 0. But let's give you a chance to look at the homework assignment, try and build some of these Taylor and Maclaurin series, get comfortable with what they are and how they work, and then we will see you in class to discuss them more. After looking at the conic sections, what we realize is that we have non-functions that are relationships between x and y that we use quite often. It would be nice if there was a better way to express those relationships that are not functions. And so what we're going to take a look at in the next couple sections is some different ways to express relationships between our variables. We're answering the question, is there a better way? To describe relations that are not functions. We're used to this whole x-y relationship, and x determines y, and that's what allows us to graph our points and our function to represent all the solutions. However, there might be another way to represent functions. What if instead of just having x dependent on y, what if x and y were both defined to be dependent on another variable? And this is where we get what are called parametric equations. And the idea of a parametric equation is the x value comes from some function x of t, and the y value comes from some function y of t, where t now is the independent variable. And what's really important is that independent variable moves over an interval. In other words, we're graphing x and y with relationship to time. As time passes, we have this movement of our x and y values. And so the time can quickly determine the graph. Let's take a look at an example. Let's say we have a relationship where x of t is equal to 3t plus 2. Sometimes you just see x equals. And y of t is equal to t squared minus 1. And negative 3 is the lowest value for t, and 2 is the highest value for t. What if we wanted to graph this parametric equation? Well, what we can do is we can make a table of values for our t values going from negative 3 to 2. Negative 3, negative 2, negative 1, 0, 1, and 2. And we can look at what happens to our x and y values so that we can graph what happens at each of these moments in time as the time progresses. So when t is negative 3, we plug negative 3 into the x equation. And so we end up with 3 times negative 3, which is negative 9, plus 2 is negative 7. Then we plug negative 3 into the y function. When we plug negative 3 into the y function, we get negative 3 squared, which is 9, minus 1 is 8. Then we plug the negative 2 in. 3 times negative 2 plus 2 is negative 4. Negative 2 squared minus 1 is 3. Plug in the negative 1 in. 3 times negative 1 plus 2 is negative 1. Negative 1 squared is 1. Minus 1 is 0. Plugging 0 in, we get 2 and negative 1. Plugging 1 in, we get 5 and 0. And plugging 2 in, we get 8 and 3. And so what this does is give us the coordinate points that we can graph to see our function. Popping up some graph paper to help us graph this. X starts at negative 7, comma 8. Then it's negative 4, 3. Then it's negative 1, 0. Then it's 2, negative 1. Then it's 5, 0. And then it's 8, 3. And what we end up with is this graph. Turns out what we have is the forming of a parabola. But what's really important to note is that the graph also has direction. And that's something that's unique about parametric curves, is you end up with direction to your graphs. So this is our function. X of t is 3t plus 2. Y of t is t squared minus 1. Now, sometimes it might be useful to convert our parametric equation and eliminate the parameter. So that we can see the relationship between x and y a little more straightforward. And really, the way we can eliminate the parameter is we can solve one equation for the variable for the parameter t and substitute into the other function. So let's take a look at some examples. Starting with x is equal to 2 plus 3 over t, and y is equal to t minus 1. What would this look like as a regular function? Well, the y equation is really easy to solve for t by adding 1 to both sides. And then we can take that y plus 1 and replace the t with that y plus 1. When we do, we end up with x equals 2 plus 3 over the y plus 1. And then we might want to solve this for y, because we're used to seeing functions solved for y. So if we subtract 2 from both sides, we can multiply both sides by y plus 1 and divide both sides by x minus 2 and subtract 1 from both sides to get y is equal to 3 over x minus 2 minus 1. And this would give us the exact same function, but with the parameter eliminated. Let's take a look at a little bit more of an interesting function. Let's look at the parametric equation. X equals 4 plus 2 cosine of t. And y equals negative 1 minus 3 sine of t. This is actually a very familiar graph to us. Let's see what happens when we work to solve it if it becomes something more familiar. We can start by working with the x equation. I'm going to subtract 4 from both sides and then divide by 2. So we've solved for the cosine of t. And the same thing with the y. I'm going to solve it for the sine of t by adding 1 and dividing by negative 3. One way we could attack this is to take the cosine inverse and then plug it into the sine. That's going to be a lot more work than we need to do, though, because we know that sine squared of t plus cosine squared of t equals 1. So let's do that. We're going to take the sine of t, which is y plus 1, over negative 3 squared, plus the cosine of t, which is the x minus 4 over 2 squared, must equal 1. And if we put that squared on top and bottom, we end up with y plus 1 squared over 9 plus x minus 4 squared over 4 equals 1. And we should recognize that function. That is an ellipse that is centered at 4 comma negative 1 with a vertical major axis equal to the square root of 9 is 3, double that at 6, and a horizontal minor axis equal to the square root of 4 is 2, and double that, we get 4. So this is an ellipse centered at 4, negative 1, with a vertical major axis of 6 and a horizontal minor axis of 4. That is what the graph looks like. But what we've done, because this is a parametric equation, is x and y depend on t, the independent variable. Now the ellipse is defined as a function of t. This is one advantage of parametric equations, is we can start working with non-functions and define them in terms of this parametric variable, this parameter, t. Today's assignment is designed to have you get familiar with parametric graphs and converting between parametric and rectangular coordinates with the x's and y's. Take a look at practicing those, and then in our next video, we'll look at how we can do calculus when we're working with parametric equations. Now that we've taken a look at parametric curves and how to work with parametrized equations, we're ready to take that up to the level of calculus and ask ourselves the question, how do we do calculus with parametric equations? And really, calculus is very similar in parametric as it is in rectangular coordinates. But there are a few adjustments that we're going to make. First, we're going to take a look at derivatives with parametric equations. And the big thing with derivatives is normally when we find a derivative, we call it dy dx. Well, dy and dx are now separate equations. So we have to take their derivatives separately. So we'll take the derivative of the y equation with respect to t and divide it by the derivative of the x equation with respect to t. In other words, we're taking y prime of t divided by x prime of t to get dy dt. So some examples of doing this would include if x of t is equal to t squared minus 3, and y of t equals 2t minus 1. So if we want to find the derivative of this, the derivative is dy over dx. So first we need to find dy. Well, y prime, the derivative of the y function with respect to t, we know is 2 over the derivative of x with respect to t. Well, x prime of t is equal to 2t. So our denominator is 2t. And when we simplify by reducing out the 2's, we get the derivative dy dx being 1 over t. And this becomes the function of the slope of the tangent line at any point on this parametric curve with respect to t. Let's do one more example. Let's try x of t equals 5 cosine squared of t. And y of t is equal to 5 sine squared of t. Well, again, we need the individual derivatives. First, we need y's derivative, which we know is 5 times, bring the 2 out front, sine of t, times the derivative of the sine, which is the cosine of t, using the chain rule there. So really, that's 10 sine cosine. And now the derivative of x with respect to t is we have the 5 times, bring the 2 out front, 2 cosine of t, times the derivative of the inside, which is negative sine of t. And so if we clean that up, we get negative 10 cosine t sine t. And so when we want to find the derivative, which is dy dx, we simply plug those in. The derivative of y was 10 sine t cosine t over the derivative of x with respect to t, which was negative 10 cosine t sine t. And this time we get a lot of reducing that happens, leaving just the negative in the denominator. Really, we have 1 over negative 1, which is just negative 1, which means the slope of this function is negative 1. Now, when we were back in Calculus 1, we didn't just want to find the derivatives, because the derivative was the slope of the tangent line, but we actually wanted to find that tangent line quite often through a given point. So let's see if we can do that as well. Let's find the tangent line, which you remember is y minus y1 equals m times x minus x1, where m is equal to the slope dy dx at the point x1 comma y1. So if we have the function x of t is equal to t squared minus 4t, and y of t equals 2t cubed minus 6t, and we want the equation of the tangent line at the point t equals 5, we can build this in much the same way. First, we're going to find the slope. Y prime of t is equal to 6t squared minus 6. And x prime at t is equal to 2t minus 4. And then the derivative, dy over dx, is equal to the y, 6t squared minus 6, over the x, 2t minus 4. And this represents the slope of the tangent line to any point. We're specifically interested in the slope at t equals 5. So if we plug 5 into that, we have 6 times 5 squared minus 6 over 2 times 5 minus 4. 6 times 25 minus 6 is 144 over 6. And dividing, we get exactly 24. Now we've got the slope of our tangent line. We still need to go back and find what point that is actually the slope at. So if we go back to our x of t equation and find out what's happening at x of 5, we'll have 5 squared minus 5 times 4, or 4 times 5, same thing, which is 25 minus 20, which is 5. And y at that point of 5 is 2 times 5 cubed minus 6 times 5, which is 125 times 2 is 250 minus 30 is 220. So we also have this point then of 5 comma 220. Now we have a point and we have a slope. We're ready to make the equation of our tangent line, which is y minus the y-coordinate of 220 equals the slope of 24 times x minus the x-coordinate of 5. And we now have the equation of the tangent line through this curve when time is equal to 5. Let's do one more example. Let's say x of t is equal to the sine of t, and y of t is equal to the cosine of t. And we want the tangent line at t equals pi over 3. Well, the derivative of y with respect to time is negative sine of t. And the derivative of x with respect to t is cosine of t. So our derivative, dy dx, is equal to the negative sine of t over the cosine of t, which we should recognize sine over cosine is tangents. So we get the negative tangent of t. And we want to know specifically what happens with that slope at t equals pi over 3. So what we're really working on is negative tangent of pi over 3. And the tangent of pi over 3 is the square root of 3. So we have negative square root of 3 is the slope of our tangent line at pi over 3. Now we just need our point. If we plug pi over 3 into the x equation, careful, not the derivative in the equation, x is equal to sine of t. So we have the sine of pi over 3. And the sine of pi over 3 is 1/2. Plugging pi over 3 into the y function, y is going to be cosine of pi over 3, which is root 3 over 2. Which gives us the point 1/2 comma root 3 over 2 to go with our slope of negative root 3 and make our tangent line, which is y minus 1/2, the y-coordinate, equals the slope, negative square root of 3, times x minus the x-coordinate, square root of 3 over 2. And we found the equation of our tangent line. So it's kind of a brief overview of doing derivatives with parametric equations. We can also do antiderivatives with parametric equations, and they just need a little bit of a tweak to what we've done before. So let's take a look at the antiderivatives. These would be our integrals. And remember, with antiderivatives or integrals, the fundamental theorem of calculus told us what we're really finding is the area under a curve. And it turns out that if we want to find the area under a curve in parametric equations, we still take the integral from a to b. But we need to account for the fact that our dx's is split up into an x function and a y function with respect to t. So we've got the y function that we're going to integrate with. But when we use the chain rule with the dx, we end up with an x prime of t dt. Also, it's important to note that a is the left endpoint. Because sometimes with parametric equations, the graph ends up being graphed from right to left, in which case we need to switch the order of the integration or just take the opposite of the final integral. We'll take a look at what that means when it comes up. But for now, we'll say if we want the area under the curve, we take the antiderivative from a to b, the integral from a to b of the y function times the derivative of the x function dt. Here's an example of what that looks like. If x of t is equal to 2 cosine of t plus the cosine of 2t, and y of t is equal to 2 sine of t minus the sine of 2t, we're going to find the area under the curve between 0 and pi. Well, the first thing we need to know if we're going to use this function, this operation to find the area under the curve, is we need to know the derivative of the x function. So first, the x derivative. The antiderivative of 2 cosine is negative 2 sine t. And the antiderivative of cosine of 2t, using the chain rule, is negative 2 sine of 2t. So when we plug that into our integral function, the area under the curve from 0 to pi of the y function, which is 2 sine t minus the sine of 2t, times the derivative of the x function, which is negative 2 sine t minus 2 sine of 2t, dt. And then all we have to do is evaluate that integral to find the area under that curve. This integral is going to take a little bit of work to work out. So let's give ourselves a little bit more space to work with. And let's see what happens. First thing I'd notice is that I've got a GCF of negative 2 inside this last factor. I can factor out that negative 2 and pull it all the way out of the integral. So let's do that. Negative 2 times the integral from 0 to pi of 2 sine t minus the sine of 2t times, now it's positive sine t plus the sine of 2t dt. And then, to keep integrating, let's FOIL this out. Yeah, let's FOIL this all out. So we've got 2 sine squared of t plus 2 sine of t times the sine of 2t minus the sine of t times the sine of 2t minus the sine squared of 2t dt. Now let's go ahead and combine the like terms in the middle. So we have negative 2 times the integral from 0 to pi of 2 sine squared of t plus sine of t sine of 2t minus the sine squared of 2t dt. Couple things that I notice here. Each piece of this integral we need to do some work with using some trig formulas in order to simplify. We see the sine squared of t, and we remember that the sine squared of t is equal to 1/2 times, or minus 1/2 times the cosine of double the angle, 2t. So we're going to replace that sine squared with this property. And what's nice, when that 2 distributes through, it's going to clear out those 1/2s. So we end up with negative 2 times the integral from 0 to pi. When the 2 distributes through, we have 1 minus the cosine of 2t plus Another thing I noticed is we've got a sine of 2t. We have a formula from trig that says the sine of 2t is equal to 2 sine of t cosine of t. And when we multiply that by the sine, we'll end up with 2 sine squared of t times the cosine of t. And that's set up now for a nice, easy substitution where u is sine and du is cosine. Minus, and again, we see the sine squared. So we'll use the sine squared formula again to say 1/2 plus, because we have to distribute the negative through, 1/2 cosine, and when we double the angle, we get 4t dt. Let's go ahead and combine. There's not much for like terms, but we do have 1 minus 1/2. So now we have -2 times the integral from 0 to pi of 1/2 minus the cosine of 2t plus 2 sine squared t cosine t plus 1/2 cosine of 4t dt. And after all that algebra, we finally have something we can integrate. We have -2 times 1/2 of t minus the antiderivative of cosine is sine of 2t. But we need a 1/2 to take care of the 2 on the inside. Plus sine squared comes from a sine cubed. But we need to divide by 3 to take care of that. And then using the chain rule gives us the cosine. You can check that using substitution. Plus antiderivative of cosine is sine of 4t. But we need to divide by a 4, which means we have a total of divide by 1/8. And we're integrating this whole thing from 0 to pi. What's nice is when we plug pi into sine, pi or 0, both pi and 0 of sine go to 0, which means all the terms go away except for the very first one. So we end up with -2 times 1/2 of pi minus 0, because when we plug in half of 0 is 0. And then when we multiply this together, -2 times pi over 2 is -pi. But wait, why is it negative? We made a small error at the beginning in that we didn't take the time to notice if a was a left endpoint or a right endpoint. If we start integrating at 0, we're claiming that 0 is the left endpoint. Let's take a look at this graph really quick. What I've done here is I've asked Desmos to graph this parametric curve for us as t grows from 0 to some value a. And a is going to be a video that's going to scroll from 0 up to pi. And I want to notice when this graph is drawn, it's going to start here at 3, 0. And as a gets bigger, it goes off to the left. This curve is actually drawn backwards until our time is equal to pi. And this then becomes the curve that we're trying to find the area underneath down to the x-axis. But because it was drawn from right to left, the leftmost endpoint was actually pi, not 0, which means we should have integrated not from 0 to pi, but from pi to 0 to make it integrate from left to right. That way our dt is positive. Well, we could fix that easily at the end, because if we switch the order of integration, that would have stuck a negative out front. Well, let's just make that adjustment at the end and say this is drawn backwards, which means the area under the curve is actually equal to a positive pi. So if it's drawn backwards, you'll end up with a negative area. And that should be your hint. Oh, this is probably drawn from right to left. We need to take the absolute value and say it's equal to the positive value, because area can never be negative. I want to take a look at one more use of integration of calculus with parametric curves. We've talked about the area under a curve, but let's actually talk about another interesting thing, and that is, I think this is number 2, arc length. Arc length was generally one of the most difficult formulas to work with in rectangular coordinates, and there are some situations where arc length is actually easier to work with in parametric equations. We just need a slightly different formula to account for the fact that we have an x and a y function. To find the arc length, it's going to be the integral from a to b of the square root of, and instead of 1 plus the derivative squared, it's going to be dx dt squared plus dy dt squared. It really comes from the Pythagorean theorem, the change in the x plus the change in the y squared dt. One thing we need to be careful of as we use this formula, and it's a property from pre-calculus that we don't spend a lot of time on, but it does become important here, is when we take the square root of something that's been squared, it's not actually equal to that something. It's actually equal to the absolute value of that something. And so sometimes if you get a weird answer, we might need to go back and say, let's take the absolute value of what was under the square root instead of what we ended up with. It doesn't become an issue often, but when you get a weird answer like an arc length of 0, something like that, that's probably what happened. All right, let's try an example. Let's say x of t is equal to 3t squared, and y of t is equal to 2t cubed. And we're going to find the arc length as t runs from 1 to 3. Well, to use the formula, we need to take both derivatives and square them. So let's take the derivative of x, which is 6t. And when we square the derivative of x, we get 36t squared. With the y's, the derivative of y is 6t squared. And when we take that derivative and square it, we'll get 36t to the 4th. So using our formula, we're going to take the integral as t runs from 1 to 3 of the square root of the x derivative squared, which was 36t squared, plus the y derivative squared, which is 36t to the 4th dt. And if we can integrate this guy, we'll end up with our arc length from 1 to 3. Let's do a little simplifying with this. We've got a common factor of 36t squared that can come out. That's going to leave behind 1 plus t squared dt. And we can take the square root of 36t squared. It's 6t times the square root of 1 plus t squared dt. And we're set up then for a nice substitution where u is equal to 1 plus t squared, du is equal to 2t dt. Well, to get that 6 to be a 2, we're going to divide it by 3. So we'll divide by 3 inside and multiply by 3 outside. So we end up with 3 times the integral. Make sure we plug our limits of integration into the u. 1 plus 1 squared is 2. 1 plus 3 squared is 10. And we're left with just the square root of u, or u to the 1/2, du, which is equal to 3 times u to the 3/2 times the reciprocal, which is 2/3, integrated from 2 to 10. The 3's divide out, and so we're just left with 2 times u, which we'll start by plugging in 10 to the 3/2, minus, plug the 2 in, 2 to the 3/2. And that's not going to be any pretty numbers, so let's just leave our arc length as that value, 2 times 10 to the 3/2 minus 2 to the 3/2. And that's how we can find arc length in parametric curves. So we've taken a look at both derivatives and antiderivatives. specifically in the context of tangent lines and arc lengths and area under curves. Take a look at the homework assignment to practice a few of these, and we will talk about them more in class. See you then. Now that we've taken a look at parametric equations as an alternate way to graph x and y coordinates using two different functions, we're going to look at another option for graphing in a completely different graphing system. The question's going to be, what other graphing systems can we use? Normally, when we've graphed a point up to now, we've said we're going to graph a point really with an xy coordinate, where x is how far we go to the right, and y is how far we go up. However, we could graph using a different version of reference points. And this leads to what are called polar coordinates. The idea behind polar coordinates is we've got the coordinate system. And instead of giving an xy coordinate, what we're going to do is we're going to have some distance, which we will call r, that is going to be some angle theta away from the polar axes, or what we traditionally have called the x-axis, to get to our point. So a point is now made up of an ordered pair of r comma theta, where r represents the radius, or distance from the center, and theta represents the angle that we open up to. Now, what's interesting about polar coordinates, then, is unlike the xy coordinate system, where there's only one way to get to the point 4, 7, with polar coordinates, there are multiple ways to get to the same point. They are not unique coordinates to represent the same point. Let's say we wanted to look at a point over here. And if I were to draw it out, let's say that radius has a distance of 2, and the angle is a distance of pi over 4, a 45-degree angle. If that's the case, then our radius is 2, and our angle is pi over 4, and that's going to represent that point. But that's not the only way to get to that point. I could have taken my angle and gone around a full circle and a little bit more. 2 pi plus another pi over 4 would be 9 pi over 4. And so we end up with the same radius of 2, but an angle of 9 pi over 4, representing the exact same point. In fact, there's a third way to represent that exact same point, and that is to take an angle that goes around to the distance exactly opposite it. That angle would be 5 pi over 4. But then our radius is going to come out the other direction. And to show the radius coming the other direction, we'll say the radius is negative. And so we end up with this point negative 2, 5 pi over 4. And we've got 3 ways to represent the exact same point. In fact, there are an infinite number of ways that we could represent this exact same point, including negative angles and angles that are several times around the entire unit circle. So polar coordinates are not unique, but they do provide a way to do a lot of graphs in a much more convenient way. But before we do that, let's take a look at how we can do conversions between polar and rectangular coordinates. And to set these conversions up, let's take a look at a point that is drawn by some radius r and some angle theta. And if we were to drop a triangle on that, we end up with an x distance to the right and a y distance up. Well, we know that the cosine of theta, the cosine of the angle, is the adjacent x over r. And multiplying by r tells us that the x-coordinate is equal to r cosine theta. Similarly, if we took the sine of the angle, it would be the opposite over r, or y over r. And multiplying both sides by r, we get r sine theta is equal to the y-coordinate. We also have ways to convert the other direction. We know from the Pythagorean theorem on this exact triangle that x squared plus y squared is equal to r squared. And so if we know x and y, we should be able to calculate r. Also, if we know x and y, we can use the tangent of theta to equal the opposite over the adjacent, or y over x. And so tangent of theta is equal to the ratio of our coordinates. Let's see if we can use these conversion properties to help us convert maybe the point 3, -4 to polar coordinates. Well, we've got the x and y, so we know that r squared is equal to x squared plus y squared. So r squared is equal to 3 squared, which is 9, plus 4 squared, which is 16. So r squared is 25, and our radius must be 5. We also know that the tangent of the angle is equal to the ratio of y over x, -4/3. And if we take the tangent inverse of both sides, it's not a pretty number, but we get -0.9273, approximately. And so we end up with the polar coordinate of 5, -9273 for our polar coordinate that's equal to 3, -4. Let's go the other direction. Let's convert the polar coordinate 4, 2 pi over 3 to a rectangular point. Well, to do that, we know x is equal to r cosine theta. And we know that y is equal to r sine theta from our formulas up above. So now we just have to plug in what we know, that x is equal to the radius of 4 times the cosine of 2 pi over 3. Or x is equal to 4 times the cosine of 2 pi over 3 is -1/2. So the x-coordinate is -2. For the y-coordinate, y is equal to the radius of 4 times the sine of 2 pi over 3. So y is equal to 4 times the sine of 2 pi over 3 is √3/2, which reduces down to √2. And we end up with the rectangular coordinate of -2, 2 √2 being the exact same as the polar point 4, 2 pi over 3. Now that we've taken a look at how we can convert between rectangular and polar coordinates, we're ready for our next task, which is to see if we can actually plot points. And we're going to plot 2 points on this graph. We're going to plot the point 4, 5 pi over 3. And we're going to plot the point -3, -3 pi over 2. Now, when we're graphing in polar coordinates, we can convert them to rectangular coordinates and figure out where they should be. Or we can just graph them using our angles in what's called a polar grid. This here is our polar grid, and each circle represents a radius of 1. So we can kind of count out, just like we count out on our x-axis, of 1, 2, 3, 4, 5, and so on. And we can see the growing radii coming out of the center. Here on this polar grid, every pi over 6 has been labeled. So we've got 0, pi over 6, 2 pi over 6, which is pi over 3. Then we end up with pi over 2, then 2 pi over 3, and 5 pi over 6, and then pi, and then 7 pi over 6, and then 4 pi over 3, and then 2 pi, or 3 pi over 2, and then 5 pi over 3, and 11 pi over 6, and then we're back around to 2 pi. And so you can see you're working yourself around. This one does not label the pi over 4s, but those would be just kind of in the middle. So if you needed a pi over 4, you could stick it right up in the middle, and you could label the pi over 4s in this graph as well. It's just kind of like a unit circle, but with a different radius established for each coordinate point. So when we want to plot point A as 4 comma 5 pi over 3, I'll go over to an angle of 5 pi over 3, and I'll count out 4 radii. 1, 2, 3, 4. And that fourth radius out from 5 pi over 3 is point A. Similarly, with -3, -3 pi over 2, negative angles count backwards. So we're going to go the opposite direction. I'll do this one in green because we did the first one in blue. Going the opposite direction, we've got -3 pi over 2. If you count 1, 2, 3, -3 pi over 2 is up here at the top. But instead of coming vertically up towards -3 pi over 2, because the radius is negative, we're going to count backwards to 3 points. And that gives us a -3 radius, because we're going backwards away from the -3 pi over 2. And there becomes point B. So if that's how we plot points, then we're one step away from being able to actually graph polar equations. Let's take a look at that. Let's take a look at polar graphs. The first polar graph we're going to look at is r equals 4 plus 4 cosine of theta. And to set this up, we're going to take a bit of time with this so we can get good comfort with how these polar graphs work. We're going to look at all the common angles theta and see what radius they give us and see if we can graph what shape this is going to give us. Our common angles that we're going to look at is we're going to count every pi over 6. It does skip the pi over 4s, and we could include the pi over 4s if we wanted to. But for the sake of time, I'm just going to do 0, 1 pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 11 pi over 6. And then 2 pi would be coming back around to the same point. So I'm going to use my calculator to take a look at these. So let's pull up our calculator. On your calculator, in order to graph polar equations, we need to change the mode that we're in. If we click Mode, down a couple spots, you see Function is highlighted. Next to Function is Par. That's for parametric equations, if you wanted to use your calculator for those. And the next is the polar equations. Let's go down to polar equations and hit Enter to highlight polar equations. And now when I hit the y equals, instead of saying y equals, it's actually going to say r equals. And we want r to equal 4 plus 4 cosine of theta. And now when we hit the x button, the xt theta in, we're going to end up with a theta for our variable. And then I'm going to hit Second Table. And I'm going to delete all of these values out that I don't want. And now I can start entering in my values. I enter in 0, and I see that the radius should be 8. If I enter in pi over 6, we see the radius should be 7.5 approximately. And then I can enter in pi over 3, and I see the radius should be approximately 6. And so I can go down and finish filling in to figure out what values I want to fill into my table. So when the angle is 0, the radius ends up being 8. Pi over 6 is approximately 7.5. Pi over 3 is approximately 6. Pi over 2 is 4. 2 pi over 3 comes out to 2. 5 pi over 6 comes out to 0.5. Pi is 0. 7 pi over 6 is 0.5. 4 pi over 3 is 2. 3 pi over 2 is 4. You start to see it's kind of looking symmetrical. 5 pi over 3 is 6. And 11 pi over 6 is 7.5. And you can see it's going to go to 8 next. So let's see what this graph looks like. When the angle is 0, the radius is 8. So I'll count out 1, 2, 3, 4, 5, 6, 7, 8 on a 0 radius. Then at pi over 6, that's the first line, it's 7.5. Pi over 3, it's 6. Pi over 2 is 4. 2 pi over 3 is 2. 5 pi over 6 is 1/2. And then at pi, it actually comes down and hits 0. And then 1/2 and 2 and 4. And then 5 pi over 3, it goes out to 6. And 11 pi over 3, it comes out to 7.5. And then you can see it's going to go back around to 8. And so what we end up with is this interesting little curve that comes in. It almost looks like a squished heart. Actually, I'm going to make that line a little bit thicker so we can get a real good see on what that graph looks like here. It curves in and then bounces out. And that's our polar graph. That is the function r equals 4 plus 4 cosine of theta. And actually, we can end up with some pretty gnarly looking graphs in polar coordinates. To save us some time, we're going to cheat, and we're going to look at some graphs on Desmos and kind of graph what these things look like. First, we're going to graph theta equals pi over 3. Actually, this pi over 3 option, let's see if we can kind of talk through what it's going to do. Pi over 3 means the angle is going to stay consistent at pi over 3 regardless of what the radius is equal to. Theta equals pi over 3 is just a line. So let's see if we can find something a little more interesting than that. Let's do r equals 2 cosine theta minus 3 sine of theta. When we graph that, r equals 2 cosine theta minus 3 sine theta, what we end up with is a kind of off-centered circle. This is the equation of a circle. Kind of was off-centered, but it was a circle nonetheless. Let's take a look at another equation. This one's kind of gnarly. Let's take a look at r equals theta over 3. R equals theta over 3 gives you a gnarly spiral. And as you scroll out, you see this only goes up to 12 pi. Yeah. The spiral only stops here because theta's been programmed to only go to 12 pi. But if theta keeps going, the spiral is going to keep going out and out and out. So theta equals pi over 3 is actually equal to a graph of a spiral, which is kind of cool. How about this one? R equals 3 plus 3 cosine of theta. R equals 3 plus 3 cosine theta. That's kind of similar to the one that we saw earlier. It looks like a squished heart. Something like that. How about this graph? R equals 2 plus 4 sine of theta. This one's interesting because it ends up with a little squiggly in the center. A little tiny circle on the inside. So that one's kind of neat in that it comes around and then it loops around before it finishes in the center. Kind of the classic polar graph is what's called the rose. R equals 3 sine of 2 theta. Let's take a look at this graph. This one gives us a nice little rose with 4 petals on it. Well, we can actually play with the number of petals by changing what's in front of theta. Turns out if the number's even, you end up with twice as many petals. So if I do 6 theta, I've got a 12-petal rose. But if it's odd, we end up with exactly that many petals. So if I do 5 theta, we get a 5-petal rose. So you can play with that and get some gnarly looking graphs in polar coordinates. Now, it might be useful, though, to change a polar graph into a more familiar rectangular coordinates, and that takes a little bit of creative spark. So let's take a look at how we can do one last thing, and that is letter C, to transform polar to rectangular functions. Let's start by doing theta is equal to pi over 3. Well, we know this is probably going to be a line based on our little experiment with functions up above in Desmos, where we said if that angle is going to stay constant and the radius is going to change, you're just going to end up with a straight line. But to find out what that line is, what we know about theta is that the tangent of theta is equal to y over x by definition. So we can take the tangent of the angle pi over 3, and that must be equal to y over x. And the tangent of pi over 3 is the square root of 3, equal to y over x. And so if we multiply both sides by x, we end up with x square root of 3 equals y. And that's a line through the origin with a slope of the square root of 3. That one's not too exciting. Let's try another one. Let's do r equals 3. Well, if the radius is going to stay consistent and the angle is going to change, you might expect this to be a circle because we keep the same radius and go all the way around the unit circle. We also know we've got a property that x squared plus y squared equals r squared. So plugging in what we know, x squared plus y squared equals 3 squared, or 9. And that really doesn't need any simplifying. We recognize that from our conic sections as a circle with radius of 3. So let's try a more interesting graph than just r equals or theta equals. Let's try r equals 6 cosine theta minus 8 sine of theta. Now this one we're going to have to be a little more creative with. A nice little trick that can help us quite often is we're going to multiply both sides by r. And when I do that, we end up with r squared equals, and when I distribute the r, 6r cosine theta minus 8r sine of theta. And the reason that's nice is we know that r cosine theta is equal to x. And we know that r sine of theta is equal to y. And we know that r squared is equal to x squared plus y squared. And so if we put that all together, we get x squared plus y squared equals 6x minus 8y. Now, it might not be clear what shape this is exactly, so let's move all the x and y's to the same side. So we have x squared minus 6x plus y squared plus 8y equals 0. And then if I try and complete the square on the x's by adding 9, half of 6 squared, and adding 16, half of 8 squared, to both sides, the x's are a perfect square, x minus 3 squared, plus the y's are a perfect square, y plus 4 squared, equals 0 plus 9 plus 16 is 25. You'll recognize this as a conic section as well. It is a circle centered at 3, -4, with a radius of 5. Let's do one last function. Let's consider r equals secant theta tangent theta. Well, we don't really have any formulas with secant and tangent. But we do know that secant is 1 over the cosine, and tangent is sine over cosine. And if I multiply both sides of this equation by the cosine squared of theta to clear out the denominators, we get r cosine theta squared equals the sine of theta. And where this gets interesting is if we multiply both sides by r, that's kind of our favorite trick of polar coordinates, to multiply both sides by r, we get r squared cosine theta equals r sine theta. And we should recognize that r sine theta is just y. And r cosine theta is x. And if it's all squared, that must be x squared. So what we really have is x squared equals y is the same function as r equals secant theta times tangent theta. This is a parabola. So this video was a quick introduction to this new coordinate system of polar coordinates, where we can graph things using a radius and an angle theta. Take a look at the homework assignment to practice some of these, and good luck to you. Let me know if you have any questions, and we will see you in class. Now that we've taken a look at using polar coordinates, we're ready to do some calculus with polar coordinates as we answer the question, how do we find areas in polar coordinates? Or polar curves would be more accurate. Before we actually get to working with area in polar coordinates, I want to go over some tips on how we can use the TI-83 or 84 calculator to help us with finding the correct areas in the polar curves, because it's really easy to find the incorrect area, the wrong part of the graph. So the first thing that we want to do is we need to make sure that the mode is set to polar. So you'll hit the mode button and make sure polar is selected. And what's nice about that, as we found out in our previous video, is now when you hit the y equals button, it will give us r equals equations. When we're going to graph these, though, a little tip is when you graph a polar graph, I would not recommend that you do not hit the graph button. Actually, it's a button. For the first drawing.
because some of these polar graphs are too large or too small. You're not going to see much in hitting just the graph button. So we're going to say rather, we're going to hit the zoom button and select zoom fit. And what zoom fit will do is it will center the graph as large as possible on the screen. So we'll use zoom fit to get a good view. Now sometimes it skews this graph when we do this. Maybe the x's will count by 2's and the y's will count by 7's, and so we end up with a significant skew. But it does provide us a really good view of what the graph looks like. Something else to be aware of is the window button, because the window button not only gives you a chance to set the minimum and maximum values for x and y's, the window buttons will also allow you to select a range for theta for the angles. And then if you adjust that to reset it, we will use 0 to 2 pi. That's kind of the default. So whenever we change it, we need to remember to change it back to 0 to 2 pi. Otherwise, some weird things might happen. So let's take a look to see if we can correctly use the calculator to graph one petal of r equals 3 sine of 2 theta. 3 sine 2 theta is your typical rows. We're going to graph it first. So I'll pull up my calculator here. First, we'll go to mode to check to see if it is in polar coordinates, which it's not right now. So I'm going to scroll over and select polar coordinates. Second click to go back home. Now when I hit the y equals button, I have r equals equations. Let's delete out the old equation. And we want to graph 3 sine of 2 theta. 3 sine of 2 theta. And when we close the parentheses, that'll give us the graph. But instead of just hitting graph, because I'm probably going to get a bad view of it, this first time I draw it, I'm going to click the zoom button. And I will scroll down to find zoom fit. It's number 0 on my calculator. Depending on the version of your calculator, it might be a different number. So if you hit zoom and then that number, it'll automatically zoom. You don't have to scroll. So it might be worth memorizing what number it is on your calculator. So I can hit enter. And it'll quickly graph. It's 4 petaled rows. Our task is to try and graph only one petal. Let's try and graph this first petal. What I notice is it starts and ends at the origin. At that point, regardless of the angle, the radius I know is 0. That's what pulls it in towards the center. So we need to figure out what angles give us a radius of 0 so we can just graph one petal. Well, to do that, we'll go back to our equation and we'll set that radius to 0 equals 3 sine of 2 theta. And solving this for theta will tell me what angles give me that center point. Dividing by 3 gives me 0 equals the sine of 2 theta. And I know from my unit circle that the sine is equal to 0 at the left and right points. So 2 theta is equal to maybe 0, 1 pi, 2 pi, 3 pi, and so on and so forth. Dividing everything by 2 then, my theta, my angles are equal to 0, pi over 2, pi, 3 pi over 2, and so on and so forth. We just want one petal, so let's just connect from 0 to pi over 2. We're going to take theta and stick it in between those two values. And hopefully that will give us exactly 1 petal of the rose. When I hit window, I see the x-min, or the theta min and the theta max. These are our range for our thetas. We're going to go from 0, enter, to pi over 2. And if I type in pi and divide by 2 and hit enter, it's going to give me a decimal approximation for that. And now I can hit graph because it's already been graphed for me. And what I notice is that does give me exactly 1 petal of my rose, like we were hoping for. So all that to give you kind of an orientation to how to get what we want on the calculator. Let's see now if we can use that to help us actually do what we wanted to do, which was to find areas. To find an area in polar coordinates is similar to rectangular coordinates in that we're going to take an integral from a to b. But a slight difference is we're going to take half the integral from a to b of the radius squared d theta. That is going to be the big formula for today. Half the integral from a to b of r squared d theta. So going back to the example we were just looking at, let's see if we can find the area of 1 petal of r equals 3 sine of 2 theta. Well, to do that, we'll take 1/2 times the integral. And we need to usually do some work to find our a to b. However, we just found out in our previous example that that theta is going to go from 0 to pi over 2 to give us 1 petal of the radius squared. So 3 squared is 9. Sine squared of 2 theta d theta. This integral then should give us the entire area of 1 petal. I'm going to pull that 9 out because it's a constant. Gives us 9/2 times the integral from 0 to pi over 2. Then we're integrating sine squared. And we know we can't really integrate sine squared. But we have a nice property that says that's 1/2 minus 1/2 of the cosine of double the angle, 4 theta d theta. And now I can integrate that to get 9/2 times half of a theta minus the antiderivative of cosine is sine. But we have to divide by that 4, so we actually end up with 1/8 sine of 4 theta. And that's going to be integrated from 0 to pi over 2. So we have 9/2 times 1/2 of theta, which is pi over 2, minus 1/8 of the sine of 4 times theta. 4 times pi over 2 is 2 pi, minus 1/2 times 0 plus 1/8 times the sine of 4 times 0, which is 0. And when we simplify all that, we get 9/2 times pi over 4. And all the rest of the pieces actually go to 0. So for our final area of 1 petal, we get 9 pi over 8. So that's how we can find area with these polar coordinates. Let's do one more example to make sure we've got it. Let's find the area inside r equals 1 minus the cosine of theta. Well, first, to get an idea of what's going on, we'll go back to our calculator. We'll clear out the old function. We're doing 1 minus the cosine of theta. Under window, remember we've got to reset our min and max, otherwise weird things happen. We want to go from 0 to 2 pi as a default. And then we'll zoom. On my calculator, hitting 0 will give me a zoom fit. Your calculator might have a different number. And this is kind of the shape we're trying to find the area inside of. Well, what we see is it seems to start and end again where the radius is 0. So again, we're going to figure out when that radius is 0. So 0 equals 1 minus cosine of theta. If I add cosine of theta to both sides, we want to know where the cosine is equal to 1. And if I think about my unit circle, cosine is equal to 1 over here on the right. So theta is equal to 0, 2 pi, 4 pi, and so on. But we just want to get one loop of it, which goes from 0 to 2 pi. So we want theta to range from 0 to 2 pi. And that's where we set the default, so we don't need to adjust it at all. We're ready now to go to our formula that says the area is 1/2 times the integral from a to b, which we just found out was 0 to 2 pi, of the radius squared. 1 minus cosine theta squared d theta. And it might be worth on this one to go ahead and square that out. 1 minus 2 cosine theta plus cosine squared of theta d theta. We recognize that cosine squared. We should be really familiar with what to do with that one. From 0 to 2 pi of 1 minus 2 cosine theta plus, let's break this up to 1/2 plus 1/2 cosine of 2 theta d theta. We could combine like terms if we wanted to, but there's not much combining that happens. So let's go ahead and take the antiderivative, which is going to be 1/2 times a theta minus 2 sine theta plus 1/2 of a theta plus the antiderivative of cosine is sine of 2 theta. But to account for that 2 theta, we have to divide by 2, which gives us 1/4. And we're integrating from 0 to 2 pi. Plugging that in then, we get 1/2 times theta, which is 2 pi. Notice when we plug 2 pi into sine, we'll get 0. Actually, I shouldn't cross it off, just in case we get something on the subtraction step. So we have 2 pi plus 1/2 of theta. 1/2 of 2 pi is just 1 pi. And 1/4 sine of 2 times 2 pi, which is the sine of 4 pi, which is also 0. And then when we plug 0 in, everything goes off to 0. The sine of 0 is 0. Theta is 0. Half of 0 is 0. So we end up with a total of 3 pi over 2 is the area inside that curve 1 minus the cosine of theta. So as long as we've got this important formula down, 1/2 integral from a to b of r squared d theta, the integrals, the area inside these polar curves is not too difficult to find. We can do one twist on it, though, and instead find the area between curves. And just like we found the area between curves with rectangular coordinates by subtracting the top from the bottom, we're going to do much the same thing to find the area between curves. We want to find the area outside of r equals 2 plus 2 sine theta, and inside r equals 6 sine theta. Well, first we need to get an idea of what shape we're looking at. So we're going to use the calculator to help us with that. Clear out the old function. The first function that we want to be outside of is 2 plus 2 sine of theta. And we want to be inside 6 sine of theta. As I graph this, I'm going to take very careful note of which graph graphs first, because I want to be outside of the 2 plus 2 sine theta. I want to be outside of the first curve and inside the second curve, the 6 sine theta. So as it graphs, I need to be very aware of outside the first, inside the second. Let's go ahead and hit zoom fit, which is 0 on my operating system. Outside that first one, inside the second one. So I want to be outside the first curve and inside the second one. It's kind of this sideways half moon on top is what I want to be inside of. Let's kind of draw a quick picture of it. So one function was this half circle. The other function was kind of this upside down heart looking thing. But the top function, the blue function, is the 6 sine theta. I want to be inside that one and outside the 2 plus 2 sine theta, which means the area we're finding is this kind of sideways half moon on top, which means we really need to know what are the 2 points of intersection so I know where to integrate from and to. Well, those lines intersect where the radii are equal. So we'll set the two functions equal. The first is 2 plus 2 sine theta. The second is 6 sine theta. Subtract 2 sine theta from both sides to get 4 sine theta. Divide by 4 and 1/2 equals the sine of theta. If I think about my unit circle, sine, the y-coordinate, is 1/2 at pi over 6 and 5 pi over 6. So theta is equal to pi over 6 and 5 pi over 6. To test that, let's set our minimum and maximum on our calculators. Hitting window, we're going to go from pi over 6 to 5 pi over 6. And now when it graphs, it's going to graph the exact shape that we want to find the area of. We're ready to integrate. We know that the area is found by taking 1/2 times the integral from our limits of pi over 6 to 5 pi over 6. And we know from our prior study that we take the outside function minus the inside function. So the outside function is 6 sine theta. But remember, in polar coordinates, we have to square them. So we have 36 sine squared of theta. And we'll subtract the other function, which is 2 plus 2 sine of theta squared d theta. We now have the integral that we can use to find the area between these curves. A little simplifying as we square out the binomial. So 1/2 from pi over 6 to 5 pi over 6 of 36 sine squared theta minus, that minus has to distribute through, 2 squared is 4, minus 8 sine theta minus 4 sine squared of theta d theta. I'm going to combine like terms. So we have 1/2 times the integral of pi over 6 to 5 pi over 6. 36 minus 4 is 32 sine squared of theta minus 4 minus 8 sine of theta d theta. Noticing here that all my terms in that integral are even, I'm going to go ahead and distribute that 1/2 through the integral, so I don't have to worry about it anymore. Pi over 6 to 5 pi over 6 of 16 sine squared theta minus 2 minus 4 sine theta d theta. Now I'm going to break up that sine squared. And we're going to multiply by 16. So when we have the 1/2, 16 times 1/2 is 8. Minus 16 times 1/2 is 8. Cosine of 2 theta. Minus 2 minus 4 sine theta d theta. I'm going to combine like terms again. Pi over 6 to 5 pi over 6. 8 minus 2 is 6. Minus 8 cosine of 2 theta minus 4 sine of theta d theta. And now we're finally ready to integrate. We end up with 6 theta minus the antiderivative of cosine is sine of 2 theta. But when we divide by 2, we get 4. Minus the antiderivative of sine is negative cosine. So we have 4 cosine theta integrated from pi over 6 to 5 pi over 6. So let's plug it all in. We have 6 times the 5 pi over 6 minus 4 sine of 2 theta, which is 5 pi over 3. Plus 4 cosine of theta, which is 5 pi over 6, minus 6 times the pi over 6, plus 4 times the sine of 2 times pi over 6, which makes it pi over 3, minus 4 times the cosine of pi over 3. Oops, sorry, pi over 6. So to help us out, we might want to think about our unit circle. We need to know a 5 pi over 3, which is going to be down in the 4th quadrant. This is 5 pi over 3. It has coordinates of 1/2 comma negative root 3 over 2. We're also going to need to know about 5 pi over 6, which is over here. 5 pi over 6. That has coordinates of negative root 3 over 2 comma 1/2. We need to know about pi over 3, which has coordinates of 1/2 comma root 3 over 2. And pi over 6 is another one we need. A lot of them on here. That one's pi over 6, has coordinates of root 3 over 2 comma 1/2. All right, plugging it all in then, we have the, let's switch colors, 6's divide out. So we have 5 pi minus 4 times the sine of 5 pi over 3. Sine's the y coordinate, which is negative, making it positive, root 3 over 2. Plus 4 times the cosine of 5 pi over 6. Cosine's the x coordinate, making it negative, root 3 over 2. Minus the 6's divide out, just pi. Plus 4 times the sine of pi over 3, sine being the y coordinate, root 3 over 2. Minus 4 times the cosine of pi over 6, cosine being the x coordinate, root 3 over 2. And this simplifies quite nicely because we've got a couple opposites in there. 4 root 3 over 2 and negative 4 root 3 over 2 is 0. 4 root 3 over 2 and negative 4 root 3 over 2 is 0. So we're just left with 5 pi minus pi, leaves us with 4 pi, the area that we're looking for on that curve beneath the 6 sine theta and above the 2 plus 2 sine theta. Area there is 4 pi. Let's do one last example. Make sure we've got a really good grip on this. Number 2, we're going to find the area inside the curve r equals 4 cosine theta and outside the curve r equals 2. Let's take a look at our calculator. All right, first thing we need to do is plug this formula in. So let's delete out these old formulas from the previous problem. Our first one is 4 cosine theta, which means the first graph we want to be inside of. So we'll take note of the first graph. The second graph of 2 we want to be outside of. For our window, we have to reset it to 0 to 2 pi. And then I'll zoom fit so we get a good picture. We want to be inside this first curve on the right, outside the second curve on the left. So we're really looking for the right area here shaded. So if we draw a quick picture of what we're working with, the first function was the circle on the right. The second function was the circle in the center. And if you can excuse my crude drawing, you see we want the area, the right part of that. Which means, again, so we know our limits of integration, we need to find where those points intersect. That's where our functions are equal. So we will say 4 cosine theta equals 2. Divide by 2. Cosine theta is 1/2. So if I think about my unit circle, where is the cosine 1/2? The x-coordinate is 1/2 up on top and near the bottom. That happens at pi over 3 and 5 pi over 3. So we're going to say theta is probably going to go from pi over 3 to 5 pi over 3. But just to make sure, we'll go back to our calculator and check to make sure that's going to give us the area on the right that we're looking for. We'll click Window. For the minimum, we want to go from pi over 3 to a maximum of 5 pi over 3. And when we hit Graph, what you notice is something unexpected happens. It does not give us this section to the right we want. It gave us everything else that we didn't want. So we were going from pi over 3 to 5 pi over 3, and that didn't work. Maybe what we want to do is go the other direction and get that other grouping. Well, we can't go from 5 pi over 3 to pi over 3. But what we can do is continue around the circle. And after 2 pi, the next top point, 6 pi over 3, 1 more pi over 3 is 7 pi over 3. Because remember, our trig formulas have an infinite number of solutions. The next point we could try is 7 pi over 3. And we're probably going to be between those values. So let's take a look at the graph and see if going from a window of 5 pi over 3 to the next lap around at 7 pi over 3, does that give me the graph I want? Hitting Graph, you see it does give us that half moon shape that we were looking for. So these now are our limits of integration for this problem. Now that we have our limits of integration, we're ready to use our formula that the area is 1/2 times the integral from 5 pi over 3 to 7 pi over 3 of the outside function, which was the blue one, the 4 cosine theta squared, makes it 16 cosine squared theta, minus the outside function that we crossed out, which is just 2. Squared becomes 4 d theta. And now we have the integral we need to solve to find the area between these two curves. Again, one thing I notice is all the terms are even. So I'm going to go ahead and distribute that 1/2 through. So we have the integral from 5 pi over 3 to 7 pi over 3 of 8 cosine squared theta minus 2 d theta. And it seems like the trig formula that we use the most anymore is that cosine squared or sine squared. So we're going to integrate from 5 pi over 3 to 7 pi over 3. Cosine squared gives us a 1/2, but when multiplied by 8, that leaves us with 4. Plus 1/2 times 8 is 4. Cosine of 2 theta minus the 2 still, d theta. Let's go ahead and combine the like terms of 4 minus 2. So we're integrating 5 pi over 3 to 7 pi over 3 of 2 plus 4 cosine of 2 theta d theta. And now we're ready to actually integrate. When we integrate, we get 2 theta plus the antiderivative of cosine is the sine of 2 theta. We have to divide by the 2, which just leaves us with 2 sine of 2 theta, integrated from 5 pi over 3 to 7 pi over 3. So when we plug that in, we get 2 times our theta, which is 7 pi over 3, plus 2 times the sine of 2 theta, which is 14 pi over 3, minus 2 times theta, which is 5 pi over 3, minus 2 times the sine of 2 theta, which is 10 pi over 3. Let's think about our unit circle to help us with those strange ones. We've got to figure out 14 pi over 3 and 10 pi over 3. That's going to loop us around the circle a couple times. So to help us out, I'm going to count in 3 pi's. So we've got 0, 3 pi over 3, 6 pi over 3, 9 pi over 3, and 12 pi over 3, looping us around the circle over and over again. That should help us see that 14 pi over 3 is right here. 14 pi over 3 is going to be the same as 2 pi over 3. So the coordinates there are negative 1/2 comma root 3 over 2. And later, when we get to the 10 pi over 3, 10 pi is a little more than 9, so it's going to be down here. 10 pi over 3 turns out to be the same as 4 pi over 3. So the coordinates there are negative 1/2 negative root 3 over 2. So when we simplify to bring it all together, we get 14 pi over 3 plus 2 times the sine of 14 pi over 3. Sine's the y coordinate, root 3 over 2, times 2 gives us just a root 3. Minus 2 times 5 is 10 pi over 3. Minus 2 times the sine of 10 pi over 3. Sine being the y coordinate is going to be a negative. Negative times a negative is a positive. Root 3 over 2 times 2 is just root 3. Combining like terms, 14 minus 10 is 4 pi over 3, plus root 3 and root 3 is 2 square roots of 3. Which means the area between these two circles is going to be 4 pi over 3 plus 2 square roots of 3. So now it's your turn to take a look at some of these on the homework assignment to practice them, get really good. The key formula here for the area, we've been using it all the way through, is that the area is 1/2 times the integral from a to b of the radius squared d theta. Try a few of these, and we'll look at them more in class. This video is going to start a chapter that goes a completely different direction than the sequences and series that we've been focusing on up to this point. We're going to start by looking at these things called conic sections, answering the question, what are conic sections?
And we're going to just barely touch the surface of what a conic section is. Each one of these different conic sections we could probably spend a whole day or more on, and instead we're going to do them all in one day. So we're just going to hit the highlights. There are several conic sections. The first one is the circle. And we actually have a very precise definition for the circle. It is all points that are equidistant from a point. So if I have a point here in the center, and I have some set distance, we'll call that distance r, no matter where that set distance goes, that distance is going to be the same. And if we collect all of the points that are exactly a distance of r away from that point, we should get a perfect circle with radius r. The equation that builds a circle like this is x minus h squared plus y minus k squared equals r squared, where the point h comma k is the center of the circle, and r is equal to the radius of the circle. So if I wanted to find the equation of a circle centered at 5, negative 2 with radius 3, we could build that knowing that the center is h comma k, and the radius is that radius of 3. So my equation becomes, open a parentheses, x minus h, which is the x-coordinate of the center, 5, squared, plus y minus k, which is the y-coordinate of the center. Subtracting a negative 2 is the same as adding 2, squared, equals the radius squared. The radius is 3. 3 squared is 9. And this gives us the equation of the circle centered at 5, negative 2 with a radius of 3. Now, a circle is the most basic of the conic sections, and we don't actually spend much time on it because of how basic it is. So let's go to the next most interesting conic section, and that is the parabola. A parabola has a very specific definition also that has to do with distance as well. A parabola is all the points with a distance from a point, and we call this other point the focus, equal to the distance from a line. And that line we call the directrix. So what this means is we've got this parabola. There is a focus inside the parabola, and there is a directrix outside of the parabola. And the idea of a parabola is if I take the distance from the focus to the line, let's call that a, it's going to be the same as from the parabola to the directrix. That distance is going to be the same. Now, it's going to be a different distance if I go maybe more diagonal and slightly to the right. We'll call that b. But then we'll get the same distance as you drop down to the directrix, b. So wherever this line is drawn, c, that length is the same as the length to the directrix, C. Those lengths are always the same. Now, this drawing's not to scale and not a perfect parabola, so those don't look quite the same. But if it were a perfect parabola, those distances from the focus to the graph would be the same as the distance from the graph to the directrix. For the equation of the parabola, it is based on the direction of the parabola. The most common type of parabola that we are familiar with is the parabola that opens upwards. The parabola that opens upward has a vertex. We'll call that vertex at the point h, k. And then up above the vertex is the focus. And then below it is the line that is the directrix. The equation of a parabola like this is y equals 1 over 4p times x minus h squared plus k, where h, k is that vertex point. Also, it's important to note that this letter p is the distance to either the directrix or focus, depending on which direction we're going, from the vertex. And we already said the vertex, h, k, is the vertex coordinates. And the equation y equals, since we drop from the vertex down to the directrix, we can take that k coordinate of the vertex and subtract the p to get the directrix. Also of note, just a little side note, if the parabola is upside down, the only difference is we make the whole thing negative. So we would have y equals negative 1 over 4p times x minus h squared plus k. Exactly the same, but the negative in front would make the parabola go the other direction. So that's the first direction of a parabola. The second direction we have a parabola actually goes the other direction. It goes opening to the right, with a vertex still at our point, h, k. But now the focus is off to the right, and the directrix is vertical. This equation is x equals 1 over 4p times y minus k squared plus h. And p on here is still the distance to either the directrix or the focus from the vertex. So again, that distance between them is p, just like it was before. And h, k is still the center. Notice the k is always with the y, so it's y minus k here. But that is the vertex. And the directrix equation, then, is an x equals equation. It's x equals h minus that p, that distance from the vertex to the directrix. And again, we have a little side note that if the parabola opens off to the right, that just means we have a negative in front of everything. So it's x equals negative 1 over 4p times x minus y minus k squared plus h. So with the parabola, the equation is based on the direction. So with this in mind, let's see if we can find some equations of parabola. First, let's say we want a parabola that has a focus at 3, 2 and directrix at y equals 8. I always try and draw a rough sketch of what's happening to help me decide what type of equation I'm using. If I look at the point 3, 2 for the focus, 3, 2 is the focus. And the directrix is a y equals equation, but it's y equals 8. Y equals is a horizontal line. The parabola, then, needs to go between them. And the only way we can get between them is to have our parabola come up kind of like this, with our vertex in the center. So the focus is at 3, 2. The directrix is at y equals 8. We need to know first, what is our p, that p distance that separates the focus from the vertex and the vertex from the directrix? Well, because we're going horizontally with our p distance, we look at the y values of 8 and 2. The distance from 8 to 2, 8 minus 2 is 6. And that covers, notice the p is there twice. So 6 is equal to 2p. We can see that p value is going to be equal to 3. So the vertex coordinate then, we're still going to the right the same 3, but now we're going to be off by a distance of p, which is 3. Well, the focus had a y-coordinate of 2. 3 more would give it a y-coordinate of 5. So the vertex has a coordinates of 3, 5. And we know the p is equal to 3. So we're ready to make our equation. It's a y equals equation because it's a vertical parabola. But it opens downwards, so we know it needs to be negative. Negative 1 over 4 times p, which we found out was 3, times x minus the x-coordinate of 3, squared, plus the y-coordinate, which we found out to be 5. A little simplifying in that denominator, we find out that y is equal to negative 112 times x minus 3 squared, plus 5. And so in this way, we can really use our sketch of the parabola. It doesn't have to be to scale or perfect, but our sketch really helps us build the pieces we need, the vertex and that distance p between the vertex and the focus, or the vertex and the directrix. Let's try one more example. Let's find the equation of the parabola that has a focus of negative 4, negative 1, and directrix of x equals negative 8. So this time, if we were to draw our rough sketch, the focus is at negative 4, negative 1. Oops, that's the focus. And the directrix is an x equals equation, which means it's a vertical line. X equals negative 8, which is even further to the left. So that tells us our parabola has to come in through the center. We need to find our vertex coordinates. The focus is negative 4, negative 1. The directrix is x equals negative 8. So as we go after our p-value, remember p is the distance between the vertex and the focus, or between the vertex and the directrix. So we have 2 p's of total distance between the vertex and the directrix. The directrix has an x of -8. The focus has an x of -4. If we subtract those, we find the distance between them is 4 units. So p here must be equal to 2. So if we have a distance of 2 between them, we know that the x-coordinate of the vertex is 2 away from our from our focus and the directrix. 2 away from -4 is -6, and we keep the same y-coordinate of -1, and we now know our vertex is at -6, -1. Well, since our parabola opens to the right, it's an x equals. It's positive because it's open the correct direction. 1 over 4p, which we found out was 2, times y minus the k, the y-coordinate of the vertex, which is -1, so plus 1 squared, plus the x-coordinate, which is -6. Cleaning up that denominator, we have x equals 1/8 times y plus 1 squared minus 6. And we now have the equation of our parabola. So the parabola is our second conic section. We've had circles and parabolas. Our third conic section is kind of a variation on the circle, and it is what is called the ellipse. The ellipse is also defined in terms of distance. The ellipse is all the points where the sum of the distance from any point to 2 foci, which is the plural of focus, is constant. An ellipse is traditionally called the oval shape. And the idea of the ellipse, if I had drawn it perfectly, is we have 2 foci in the ellipse. And if I were to pick any point on the ellipse and look at the distance to both foci, we'll call them maybe A1 and A2, and then I picked a different point on the ellipse and took its distance to the 2 foci, we'll call that B1 and B2. And it doesn't matter which points I pick. I could pick a point that's way off on the side, and I end up with C1 and C2 connecting to the 2 foci. What happens is the sum of the distances, A1 plus A2, is always constant. So from the point with the b's, B1 plus B2 is exactly the same distance. Same thing for the C1 plus C2. No matter what point I pick, if I go from that point to the 2 vertices, the total distance is always constant. That's what makes an ellipse. And we have 2 equations for ellipses. And it really depends on which direction the ellipse is going. The first is for the horizontal ellipse, where we have x minus h squared over a squared plus y minus k squared over b squared equals 1. Or if the ellipse opens vertically, we'll put the y's first. Y minus k squared over still a squared plus x minus h squared over b squared equals 1. Where the a is always bigger than the b. That's important. The a is always bigger than b. The first denominator is always the biggest. So whichever x or y has the bigger denominator, we have that one come first. And we have this other variable called c, where c squared is equal to a squared minus b squared. That's going to be an important relationship for us as we attempt to define some of the properties. First, the major axis which is the distance across. We'll call it the long distance across. Could be horizontal or vertical, depending on which way the ellipse opens up. But the major axis has a distance of 2a. And the minor axis, which is the other direction, depending on if it's vertical or horizontal, it's the shorter distance across the middle. That shorter distance is 2b. We also know the distance between the foci, plural of focus, is 2c. And that's where the c comes in, identifying those focus, or foci. And of course, we're getting used to seeing in all of these conic sections that the center is always the point h comma k. So if all this information is true about our ellipse, we should be able to find some equations. Let's find the equation of the ellipse that has endpoints of the major axes at -3, 5 and -3, -7. That also has the foci at -3, 1 and -3, -3. Notice the major axis and the foci all have an x-coordinate of -3. The endpoints, what moves is actually the y-coordinate. So that tells me the y-coordinate is where we get the tall and narrow shape, where we've got a center, which we don't know where the center is yet. But we've got two foci, one above and one below. The higher one has a higher y-coordinate, so the higher one must be -3, 1. The lower one must be -3, -3. And the endpoints of the major axes means if we draw the long line through the center, the major axis is the longest line possible. So the endpoints must be at -3, 5 and -3, -7. We need to find a, b, c, and the center h, k. Let's do the center first. That's probably the easiest to do. You can see all of these are in a line on -3 for the x-coordinate. The y-coordinate is going to be in the middle of the foci. So the foci go from 1 to -3. The distance between them, if we subtract 1 minus -3, is 4. So the distance between the foci, let's go ahead and label that. The distance between the foci is 4. And remember, that is equal to 2c. So we're also figuring out here at the same time that 2 equals c when we divide both sides by 2. So if the total distance is 4, half of that is 2. So to get to the center, from one of the foci, we'll either add or subtract 2 when we figure out the y-coordinate of the center right in the middle is at -1. So we've got our center. We also know that the distance between the endpoints of the major axes is 2a. The distance from 5 to -7, if we subtract, is a total distance of 12, which means if we divide by 2, a is equal to 6. We still need to figure out what b is, though. We don't know b from this drawing. But we do know that c squared is equal to a squared minus b squared. And c we know is 2. 2 squared is 4. Equals a we know is 6. 6 squared is 36 minus b squared. If I add b squared to both sides and subtract 4, I find out that b squared is 32. And that's actually all we need is b squared, because b squared is in the formula. Our formula then becomes, notice this opens vertically, so the y's come first. Y minus, the y-coordinate of the center is -1, so plus 1 squared, divided by a squared. 6 squared is 36, plus x minus the x-coordinate, which is -3 on the center, squared, divided by b squared, which we just found out was 32, equals 1. And this then is the equation of the ellipse that has endpoints of the major axis at -3, 5 and -3, 7. It also puts the foci at -3, 1 and -3, 3. Let's do one more ellipse. Let's see if I can leave that on the screen. Let's find the ellipse that has the endpoints of the minor axis. This is the smaller one, at 1, -2, and 1, -4. Also has foci at -2, -3, and 3, -3. Notice the foci, the y-coordinate is consistent, which means it must open up around the x's. So this is going to be a horizontal ellipse. We know the foci are at -2, -3, and 3, -3. We're going to need to find the center. We're also told the endpoints of the minor axes. And the minor axis goes the short distance through the center. The endpoints of the minor axes are at 1, -2, and 1, -4. Well, the center we know is right in the middle of those. So we obviously have a y-coordinate of 1. And right in the middle of -2 and -4, we see is -3. We also can use our distances to help us conclude a few things. The distance between the foci, we're looking at the x-coordinate here, from -2 to -3 is 5. And the distance between the foci is 2c, so c equals 5/2. We also know the distance between the minor axis. The minor axis gives us 2b's. The minor axis goes from -2 to -4. That's a total distance of 2, so b must be equal to 1. We can then find our c because c squared equals a squared minus b squared. Well, c is 5/2. That's 25/4. Is equal to a squared, we don't know, minus b squared, which is 1. Add 1 to both sides. That's 4/4, gives us 29/4 is equal to a squared. And we're ready to make our equation. Because this one opens up horizontally on the x's, we have the x's come first, x minus the x-coordinate of the center, which is -3 plus 3 squared, divided by a squared, which is 29/4, plus, now the y-coordinate, y minus the y-coordinate is 1 on the center, squared, divided by b squared, which is 1, equals 1. And even though it's a little ugly, this is probably the preferred format of the ellipse because it shows all of that information we want to see. It helps us identify how big the minor axis is, the major axis is, where the center is. So we'll go ahead and leave it in this form. And so that's our third conic section, the ellipse. There is one last conic section. Conic section number 4, we'll call it D here. It is called the hyperbola. And the hyperbola is defined really similar to how we define the ellipse. It is all points where, and the only difference is the ellipse was a sum, the hyperbola is the difference. Of the distance. From any point to the two foci is constant. And the idea here is a hyperbola is going to look something like this, where there's going to be two vertices. And we take a look at the distance. If I pick a point on one hyperbola, the two distances, the longer one we'll call the first point, the shorter one we'll call the second point. No matter what point I pick on whichever one, the longer one I'll call the first point, the shorter one the second point. No matter which points I pick, when I subtract the a1 minus a2, I'll get the exact same value as if I took the b1 minus the b2. Or wherever I want to draw these lines, the hyperbola has that distance constant. Just like with the ellipse, there are two equations that we use for the hyperbolas. The first equation is used if it opens kind of the traditional way off to the left and right. This is where x minus h squared over a squared minus y minus k squared over b squared equals 1. And here it doesn't matter which one's bigger, a or b. What's important here is the x is positive and the y squared is negative. Because if we switch that and we have the y minus k squared over a squared minus the x minus h squared over b squared equals 1, then the hyperbola is open vertically. We also still have this relationship with c. C squared this time is equal to the sum of a squared plus b squared. And with that, we end up with these important properties. The distance between the foci is 2c. And the distance between the vertices, that's the corners of the hyperbolas, is 2a. We still need to find b to figure out how wide everything's going to be. And then, of course, we still have our center at h, comma, k. So using this, let's see if we can find some equations. Starting with a hyperbola that has vertices at -4, 3 and 2, 3. And also has foci at -7, 3 and 5, 3. So again, I like to do a rough sketch just so I have an idea of what's happening. With this, I see the vertices, the x-coordinate is changing, and the y-coordinate is constant. So the x-coordinate is going to change left and right. Well, the y-coordinate is going to remain constant. So we have vertices at -4, 3 and 2, 3. We also have foci out here at -7, 3 and 5, 3. We need to know where the center is and also find our a, b, and c. Well, the center is going to be right in the middle of the vertices. Our vertices, the x's are changing from -4 to 2. And if we subtract, that's a total distance of 6. We know the distance between the vertices is 2a. So that tells us that a is equal to 3. The distance to the center is also equal to 3. So if we back up 3 or add 3, depending on which point we're going from, we'll end up with -1, 3 as the coordinates of our center point. We now have our h and k. We also have our a. The only other thing we can pull off of the graph is c, which we get from the distance between the foci. The foci go from x of -7 to 5. That's a total distance of 12, which we know is 2c. So c must be equal to 6. Now we can go after the b, because we know c squared is a squared plus b squared. C was 6, squared is 36. A was 3, squared is 9. And subtracting 9 from both sides, b squared is going to be equal to 27. So going to our equation then. The equation is, because it opens sideways, we start with the x. X minus h. H, it comes from the center, so 3. I'm sorry, -1. So we'll add 1 squared. Divided by our a squared. 3 squared is 9. Minus y minus the y-coordinate of the center, which is 3 squared. Divided by b squared, which we just found out is 27, equals 1. Let's try one last hyperbola before we step away from them. Let's find the hyperbola that has vertices at 2, 3 and 2, -1. It's also going to have foci at 2, 5 and 2, -3. This time I see the x's staying consistent, which means the hyperbola is going to go up and down around the y's. So the vertices are at 2, 3 and 2, -1. The foci are at 2, 5 and 2, -3. We need to find the center. and A, B, and C? Well, first we know that A comes from the distance between the vertices. The x's are the same, so we'll focus on the y's. The distance from 3 to -1 is 4, so 4 must equal 2a. Therefore, a equals 2. So the distance from the center to the edge is 2. X-coordinate stays the same. The y-coordinate is 2 off from the vertices. So 3 minus 2 is 1. The center must be at 2, 1. The vertices are 2c apart. So from 5 to -3 is 8. That's 2c's. So c must equal 4. And then we're ready to go after our b, because we know a squared plus b squared equals c squared. A is 2. 2 squared is 4. Plus b squared equals c, which is 4. Squared is 16. Subtract 4 from both sides, and b squared equals 12. Now we have all the pieces we need to build our equation. This one opens vertically, so it's going to be a y first. Y minus the y-coordinate of the center, which is 1 squared, over a squared. 2 squared is 4. Minus x minus, the x-coordinate is 2, squared, over b squared, which is 12, equals 1. And we have our hyperbola. So this video was a quick overview of all of the conic sections that we're going to work with in this course. We talked about hyperbolas. We talked about ellipses. We talked about parabolas. And we talked about circles. 4 common conic sections that we're going to talk about further in class. So take a look at the homework assignment. Try a few of these. There's a lot of pieces to keep track of, but they're not too hard as a whole. So take a look at them, and we will see you in class. This next chapter is going to take a look at vectors and how vectors can help us in calculus and in other contexts. So the question we're going to do as we set up this new study of vectors is, what exactly are they? What are vectors? And quite simply, a vector is a quantity with magnitude which is a fancy word for size, and direction. And an example of a vector, we might represent a vector from a point out to another point with direction. That would be a vector. We might label it vector v. And what's interesting about vectors is they're not necessarily unique. Let's say we've got a vector u, and we use the little kind of vector-looking symbol above it to let us know that's a vector. Vector u goes from the origin to the point 3, 2. And vector v goes from -3, -1 to 0, 1. I want to notice really quick a bit of notation. I have this little arrow-looking thing above the vector that I'm going to write to represent a vector. The textbook uses bold letters to represent vectors. It's really the same thing. It's just hard to type by handwriting a bold U and a bold V. So my notes are going to be slightly different than the textbook. But that line above means we're talking about a vector. So let's look at what these vectors look like. The first vector, it says, goes from the origin to the point 3, 2. So the vector goes from the origin to the point 3, 2. That's vector u. The second vector goes from -3, 1 to 0, 1. And you notice that both vectors are going the same direction. And both vectors are the same size. Because both vectors have the same magnitude and the same direction, we can say that those are equivalent vectors. They both represent the same vector, the same size, and the same direction. Now we need a good way to represent vectors. And one way we can represent vectors, it's what's called component form, which basically means it is the size and direction from the origin. And usually we represent the vector with square brackets, the x-coordinate and the y-coordinate from the origin. Now, vectors aren't always set up from the origin. So to find the component form, what we can do is we can subtract the terminal point minus the initial point. So for example, if we were asked to find the component form of a vector with initial point of -3, -1, and terminal point of -2, 3, we could do that by finding the x component and the y component by subtracting the terminal point minus the initial point. So the terminal point for x starts at -2 minus the initial point of -3. So -2 minus the -3 is going to equal 1. The x component is 1. For the y component, we take the terminal point of 3, and we subtract the -1, and we end up with 4. And we take the x and y components together to represent our vector v as the x component, comma, the y component. And this is our component form of the vector. Again, I want to make sure I emphasize that we use pointed brackets when talking about a vector, pointed brackets. And that vector of 1, 4 tells us that if this vector was centered at the origin, it would go to the point 1, 4 with that same magnitude and direction. Speaking of magnitude, quite often we're going to be interested in how exactly we can find that magnitude. And the way we represent the magnitude of a vector is it looks like our double absolute values. And if I think about a vector, if I want to know the total distance of that vector, the magnitude of the vector, we could look at it as set up with an x component and a y component. And you can see the Pythagorean theorem could be used to find the size of that vector. X squared plus y squared equals the magnitude squared. Or if we take the square root of both sides, the magnitude is the square root of the x component squared plus the y component squared. And this gives us a nice little formula to find the magnitude of any vector. So for example, if I wanted to find the magnitude of a vector v equal to -5, 4, we would say that the magnitude of the vector is equal to the square root of the x component squared, 5 squared is 25, plus the y component squared, 4 squared is 16. And 25 plus 16 is 41. And so the magnitude, the size of this vector, is the square root of 41. Let's try one more example. Let's find the magnitude of, let's do the vector w, is equal to 4/5, 3/5. Well, the magnitude of vector w is the square root of the x component squared, which is 16 over 25, plus the y component squared, 9 over 25, which is the square root of 25 over 25, or the square root of 1, which is just 1. And this is actually kind of interesting to us. Whenever a vector has magnitude of 1, we call that a unit vector. A unit vector has magnitude of 1. In fact, there are some special unit vectors that we are particularly interested in. We call these the standard unit vectors. There are two standard unit vectors that we're going to talk about in this video, and there's a third one that we're going to talk about in the next video. The first vector is vector I, which has an x component of 1, and the other component is 0. The other one is j. J has an x component of 0 and a y component of 1. Basically, I is a horizontal vector with magnitude of 1, and j is a vertical vector of magnitude of 1. And what's important is the vectors I and j meet at a 90-degree angle. Because we have these two special vectors I and j that are universally accepted, we can write our vectors, can be written as a linear combination of I and j vectors. Whatever I is multiplied by represents the x component, and whatever j is multiplied by represents the y component. So for example, we talked about this vector in an earlier example of -5, 4. This same vector could be expressed as standard unit vectors as -5 times the I vector, because -5 is the x component, plus 4 times the j vector, which represents the y component. Another example would be the vector 2, -1. Because 2 is the x component, we could write that as 2i, and -1 being the y component can be written as negative j. This even gives us a way to write vectors that have 0 for one of the components. Maybe 0, 3. There's 0 I components, but there are 3 j vectors combined together. Similarly, negative 2, 0 would just use the x component, so we have negative 2i. So in this way, every vector could actually be represented in 2 different ways. It can be represented as standard unit vectors, or it can be represented as a component vector. As we go through this video, we're going to express the vectors in both ways, so we can get used to seeing them both ways. But make sure as you're working on the assignments and ultimately quizzes and tests, you take the time to be aware of what format the question's asking you to express the answer in. All right, now that we've taken the time to define vectors, let's see if we can do a little bit of work with vectors. Working with vectors. It's really what we're going to do this entire chapter. But looking at some basic operations with vectors, one thing we can do with vectors is we can combine them together. We can combine vectors. Let's say vector v is equal to x1, y1, and vector w is equal to x2, y2. Two operations that are very common with vectors. One is called scalar multiplication. And this is the idea if k is just a number, and we wanted to multiply it times the vector v, what that really means is take vector v, which had an x component of x1, and multiply the x component by the k, and multiply the y component by the k. It kind of feels like we're distributing as we multiply by the scalar or multiply by the number k. Vectors can also be combined with other vectors, though, with what is called vector addition, where we end up with vector v plus vector w. And when we add vectors together, what that really means we want to do is add their components together. x1 plus x2 to get the new x component. y1 plus y2 to get the new y component. And similarly, using the idea of an inverse, we could also do vector subtraction, where we subtract the components. And so we end up with addition and subtraction of vectors, and also a multiplication by a scalar. In future videos, we'll take a look at how we can multiply a vector times a vector. There's actually 2 different ways to do that, depending on what we're looking for specifically. So for now, we'll stick with vector addition and scalar multiplication. So let's let the vector A be the vector 7, 1, and the vector B is going to have an initial point of 3, 2, and terminal point of -1, -1. I'm going to pause here because before we get too far, before we can do any linear combinations of vectors with each other, we need to know what vector b actually is in component form. So we already know vector A is 7, 1. To get vector b, we need to subtract the terminal point minus the initial point. So for the x component, -1 minus 3 is -4, comma, -1 minus 2 is -3. So we have these two vectors. First problem we're going to attempt to solve is figure out what -2 times vector A is. This is scalar multiplication because we're multiplying by a scalar or a constant. -2 times vector A, which is 7, 1. And similar to distributing, we end up with the vector -14, -2. Or if you prefer an ij form, -14i minus 2j. Let's look at vector A plus vector B. Here we're adding two vectors together. Vector A is 7, 1, plus vector B is -4, -3. And for vector addition, we just add the individual components together. 7 minus 4 is 3. And 1 plus -3 is -2. And in component form, our sum is 3, -2. With ij, we have 3i minus 2j. Let's subtract the vectors, A minus B. Well, vector A is 7, 1, minus vector B, which is -4, -3. Subtracting component by component, 7 minus a -4 becomes 11. 1 minus a -3 becomes 4. And we have our component form of A minus B, which is equal to 11i plus 4j. We want to make sure we always have that vector notation above I and j. One last one of these. Let's find 3a minus 4b. To do this, we have 3 times the a vector. The a vector is 7, 1, minus 4 times the b vector, -4, -3. Well, when we do that operation initially, we have scalar multiplication, which gives us 21, 3. Plus, I'm going to go ahead and take that negative in. -4 times -4 is 16. -4 times -3 is 12. And now we're ready to add these vectors together. 21 plus 16 is 37. 3 plus 12 is 15. And we have our component form solution, which is equal to 37i plus 15j. And in this way, you can see how we can do lots of different combinations of our A and B vectors. Another thing we can do with vectors is we can find a described vector using our trig properties. And to kind of set this up, we'll think about the fact that if I have a vector v, the x-coordinate off that vector, using trig, we're used to saying that x-coordinate is the cosine of the theta angle that is formed, and the y-coordinate is the sine of theta. But that comes off the unit circle. If the vector is not a unit vector, we need to multiply by the magnitude of the vector. So we have the magnitude of the vector times cosine gives the x component, and the magnitude of the vector times sine gives the y component. And in this way, we can now find the vector
with magnitude 10 that forms a 120-degree angle. Because the x component is the magnitude of 10 times the cosine of the angle, and the y component is the magnitude of 10 times the sine of the angle. Magnitude of 10, sorry. Well, we need to know what the sine and cosine of 120 is. So if we draw our little unit circle on here, 120-degree angle is right up here. It's the same as 2 pi over 3. So the x-coordinate is negative 1/2, and the y-coordinate's root 3 over 2. So 10 cosine of 120 would be 10 times the x-coordinate of negative 1/2. Our x component's negative 5. For the y-coordinate, the sine of 120 is the y-coordinate of root 3 over 2, which gives us 5 root 3. And so for our final vector that has a magnitude of 10 and is going to form a 120-degree angle, it's going to be negative 5 comma 5 root 3, or negative 5I plus 5 root 3 j. Let's try one more and do this next one in radians instead of degrees. Let's find a vector with magnitude 4 forming a 7 pi over 4 angle. If I think about my unit circle, 7 pi over 4 is down here with coordinates root 2 over 2 comma negative root 2 over 2. So when we want the x component, it's the magnitude of 4 times the cosine of 7 pi over 4, which is 4 times cosine, the x-coordinate, root 2 over 2, or 2 root 2. To get the y component, exactly the same. We're just going to take the sine instead of 7 pi over 4, which is 4 times negative root 2 over 2, which gives us negative 2 root 2. And so our vector with magnitude of 4 that forms a 7 pi over 4 angle is 2 root 2 comma negative 2 root 2 in component form. Or in terms of I and j, it's going to be 2 root 2i minus 2 root 2j. So trig can be very helpful as we work with vectors. We're going to do quite a bit of trig as we do different angles with vectors throughout this course. But I want to do one other thing with vectors as we finish out our introduction to vectors. And that is looking at this concept of finding unit vectors in the same direction. And the trick here to get a unit vector is we're going to use a scalar multiplication. Basically, we want to divide the vector down so it just has a magnitude of 1. So if its magnitude is currently 8, we need to divide by 8. If its magnitude is 12, we need to divide by 12. We're going to take 1 over the magnitude of the vector
times the vector to give us a unit vector in the same direction. So for example, let's say we've got the vector v is equal to 9, 2, and we want to find a unit vector in the same direction. Well, first we need to know the magnitude of the vector so we know how much we have to shrink it by. The magnitude is the square root of the x component plus the y component, squared each. So here we end up with the square root of 85 as the magnitude, which means we can take 1 over the square root of 85 times the vector, which will keep the vector going in the same direction, but it'll shrink its magnitude down, so it's a unit vector. This gives us our new vector of 9 over the square root of 85, 2 over the square root of 85. Or if you prefer, 9 over the square root of 85i plus 2 over the square root of 85j. That is a unit vector in the same direction as the original vector 9, 2 by multiplying by the reciprocal of the magnitude. One nice thing about knowing the unit vector is it makes it very easy to get a vector of any size in the same direction. To get a vector of magnitude k, in the same direction, we not only take 1 over the magnitude of the vector times the vector, but we're also going to multiply by our desired magnitude of k. So for example, if we want a vector, let's stick with 9, 2. We're going to find a vector in the same direction. But instead of a unit vector, we want it to be of magnitude 5. Well, we already found out in the previous example that the magnitude of the vector is equal to the square root of 85. We want to get a magnitude of 5, so we're not only going to divide by the square root of 85, but we're also going to multiply by 5. And we use that as our scalar times the vector 9, 2. And that gives us 45 over the square root of 85 for the x component, 10 over the square root of 85 for the y component. Or in terms of I and j, 45 over root 85i plus 10 over root 85j. And that now is a vector of the same direction, but now with magnitude 5. We haven't really done any calculus yet. We've just been kind of exploring with this concept of a vector using scalar multiplication, vector addition, ikj vectors, calculating the magnitude of a vector. So it's been a really brief overview of vectors in the plane, two-dimensional vectors. But it's really important we're comfortable with these before we get to too many complex topics that these are built on. So I want you to spend today practicing with these vectors on the homework assignment. We'll talk about them more in class and answer any questions that you may have. Now that we've taken a look at how vectors work in 2 space, we're ready to answer the question about how do vectors work in 3D, in 3 dimensions, in space. But before we do that, let's take a quick look at 3D graphing, because we do not have as much experience with 3D graphing as we do with 2D graphing. And we can think about 3D graphing as graphing in space, where it's kind of like the corner in a house, where one wall coming out becomes your x-axis, the other wall coming out becomes your y-axis, intersecting with the floor, and then coming up vertically is what we will call the z-axis. And in this way, we end up with our x, y, z space. And you can also go negative y and negative x and negative z. So we get the origin is just kind of a fixed point out in space. And so then if we were asked to actually sketch a point, let's sketch the point 1, 2, 3. This becomes quite a tricky task to do in 2 dimensions, but we'll do the best we can here. We'll have our z-axis, our y-axis, and the x-axis forming the corner of the house. And we can almost think about these as counting out on the y-axis, 1, 2, 3, counting out on the x-axis, 1, 2, 3, and on the z-axis, 1, 2, 3. And it might be easier to kind of visualize where the point 1, 2, 3 is if we graph a 3-dimensional box that sits in this corner, where the box has dimensions of 1 by 2 by 3. So the box is going to have a dimension of 1 down the x-axis, 2 across the y-axis. So we kind of end up with this shape. And then vertically, we're going to go up 3 units. And so you almost end up with this 3-dimensional box sitting in the corner. And that front corner closest to us becomes the point 1, 2, 3, because it goes a distance of 1 down the x-axis, a distance of 2 down the y-axis, and then vertically up a distance of 3. And so that's kind of how we can sketch a point in 3 dimensions. And where we're ultimately going is from the origin, we're going to have a vector that goes out to that point diagonally across the box. But before we can get to that idea of vectors, which have direction and magnitude, to calculate the magnitude, we need to know how distance works in 3 dimensions. Now, in 2 dimensions, we're familiar with the Pythagorean theorem, so we could take the x-coordinate squared plus the y-coordinate squared and take the square root to get that distance. Or the x distance squared plus the y distance squared. The square root of that equals the distance. We can extend that same logic out into 3 dimensions so that the distance is the square root of the x distance squared plus the y distance squared plus the z distance squared. So a really quick example of that would be to find the distance between the point 1, -5, 4, and the point 4, -1, -1. Well, if we look at our x's, the distance the x's travel from 1 to 4, that's a distance of 3 when we subtract them. When we look at our y's, the distance the y's travel from -5 to -1, that's a distance of 4. And the z's traveling from 4 to -1, they cover a distance of 5, when we subtract those points. So then using our distance formula, the distance between them is the square root of the x distance, 3 squared, plus the y distance squared, plus the z distance squared, which gives us the square root of 9 plus 16 plus 25, which is the square root of 50. And if we want to simplify that, that's 5 root 2. So distance, the Pythagorean theorem in 3 dimensions works very much the same as it does in 2 dimensions. We just add the extra z squared to our distance formula. All right, that was a very brief introduction to graphing in 3D, because our main interest is not graphing in 3D. Our main interest is in 3D vectors that go through the space. And basically, 3D vectors are very similar to 2D vectors. We just have to add the third component to get x, y, z. Or we could add a third unit vector, which is the vector k in our ijk vectors, where k is equal to the vector 0, 0, 1, giving us 1 unit in the z direction. So for example, we could have the vector v could be equal to 1, negative 2, 3. And in terms of ijk vectors, then that would be I minus 2, j plus 3, k. Or if I had the vector u equal to 0, 1, negative 2. Because 0 is the I vector, we don't really have an I, so we just have 1j minus 2k. And that tells us that this is a vector that goes from the origin diagonally to those points, either 1, negative 2, 3, or 0, 1, negative 2. Let's see if we can find a vector with initial point of 3, 8, 2 and terminal point of 2, negative 1, 3. Well, our vector, we know from two-dimensional vectors that we can take the terminal point and subtract the initial point, and that'll give us the distance that vector's traveling. So looking at the x component, 2 minus 3 gives us negative 1. Looking at the y component, negative 1 minus 8 gives us negative 9. And looking at the z components, 3 minus 2 is equal to a positive 1. Or if we prefer, we could say that's negative I minus 9j plus a single k. And this is that same vector. And what's nice about vectors in 3 space, once we're comfortable with vectors in 2 space, is that we can do all the same operations from those 2D vectors that we worked with in the prior video. So for example, if vector v is equal to negative 1, 4, 3, and vector w is equal to 2, 0, negative 3, we could do things like find 2v minus 3w.
scalar multiplication and vector addition or subtraction. 2 and 3 are scalars. That's just 2 times the v vector of -1, 4, 3. And then a -3 times the vector w of 2, 0, -3. So when we multiply those scalars through, because multiplication comes first in order of operations, we get -2, 8, 6. Plus, let's take the negative through, -6, 0, 9, when those are multiplied through. And finally, vector addition adds those together to get -2 plus -6 is -8, comma 8 plus 0, comma 15. Or if we do those as ijk's, we have -8i plus 8j plus 15k. Let's keep with these same two vectors, and let's find the magnitude of vector v. Well, magnitude is just the distance formula, where we take the square root of the x component squared plus the y component squared plus the z component squared. It's that Pythagorean theorem we saw earlier. So vector v, -1 squared is 1, plus 4 squared is 16, plus 3 squared is 9, and we end up with the square root of 26 is the magnitude or size of vector v. And once we know the magnitude, we're ready to find a unit vector in the direction of v. And just like with two-dimensional vectors, to make a vector into a unit vector in the same direction, we scalar multiply by the reciprocal, 1 over the square root of 26, the reciprocal of the magnitude, times the vector v, -1, 4, 3, which gives us the vector -1 over the square root of 26, 4 over the square root of 26, 3 over the square root of 26. Or if we prefer with ijk vectors, -1 over the square root of 26i plus 4 over the square root of 26j plus 3 over the square root of 26k. So as you can see, working with vectors in 3D is very similar to working with vectors in 2 dimensions. There's an extra component to work with, but we follow the exact same patterns. So I'll give you a chance to practice some of these on your own. Take a look at them, and we will answer any questions you have in class. Working with vectors, we discussed how we can add and subtract vectors together. We did a multiplication with vectors called scalar multiplication, where we multiplied a constant or a scalar by a vector. But we haven't talked about how we can multiply two vectors together. There's actually 2 different ways to multiply vectors together, and so we specify the difference by not calling it multiplication, but we call them a dot product and a cross product. The difference is one gives us a scalar as a product, and one gives us a vector as a product. And they both have different uses depending on what we're trying to accomplish. In this video, we're going to look at the dot product as we answer the question, how do we multiply vectors to get a scalar or a constant? In other words, when we multiply these vectors together using the dot product, the answer is going to be a scalar, not a vector. So let's define this dot product. Let's say we've got a vector u, and that vector u is x1, y1, z1. And there's another vector v that's going to be our second vector, so we'll call it x2, y2, z2 as its components. The way we define the product u dot v, the dot
product is we're going to multiply the components together and add the products. So we'll take the x coordinates and multiply them together, x1, x2, plus then we take the y components and multiply them together, y1 times y2, plus, and then we take the z components and multiply them together, z1 times z2. And when we add those together, we'll get some scalar. So this is just a new operation we really just need to do a little bit of practice with to learn, and then we'll talk about how it's useful to us when talking about vectors. So for an example here, we're going to do vector u is equal to 2, 9, negative 1. And vector v is equal to negative 3, 1, negative 4. And we're going to calculate u dot v. Well, to do u dot v, we're just going to multiply the common components together. We take the x's. 2 times negative 3 is negative 6. Then we take the y's. 9 times 1 is a positive 9. And then we take the z's. Negative 1 times negative 4 is a positive 4. And when we add those together, negative 6 plus 9 plus 4, we get 7. So our dot product of u and v is equal to 7. Let's try one more example. Let's say vector u is equal to 3i plus 5j plus 2k. And vector v is equal to negative I plus 3k. If we want the dot product u dot v, we'll start by multiplying the I components together. 3 times negative 1 is negative 3. The j components together, 5 times, and you notice there's no j component on v. Since there's no j component, that really means there's 0 j's. So 5 times 0 is plus 0. And finally, on the k's, 2 times 3 is a positive 6. And so when we add those together, we end up with 3. And that's the dot product. It's a very simple, straightforward multiplication of vectors where we multiply the components together and add the individual products. What is this useful for, though? Well, one common use of the dot product is the dot product can be used to tell us the angle between two vectors. We have an important formula that says that the cosine of the angle between the vectors is equal to u dot v divided by the magnitude of u times the magnitude of v. And this is going to be an important formula for us to know. You'll probably have it memorized by the time you finish the homework assignment, because we use it a lot as we try and find the angle between two vectors. So let's do some examples where we find the angle between two vectors. Let's start with the vector a is equal to 1, 2, 0. And b is the vector 2, 4, 1. I like to find the individual pieces of the formula before I plug them in. It just makes it a little more straightforward. So let's find the numerator first, the a dot b, which is going to be 1 times 2 is 2, plus 2 times 4 is 8, plus 0 times 1 is 0. So a dot b is 10.
Next, we need the magnitude of both vectors. So the magnitude of A is the square root of 1 squared plus 2 squared plus 0 squared, or the square root of 5. We also need to know the magnitude of vector B. Vector B is the square root of 2 squared plus 4 squared plus 1 squared, which is the square root of 21. Now we put it all together and know that the cosine of the angle between the vectors is the dot product 10 divided by the product of the magnitudes. And when we multiply square roots, we multiply underneath 5 times 21. Now we just go to our calculator to figure out what the cosine inverse of that fraction is, and we can type it in just like it is. Cosine inverse of 10 divided by the square root of 5 times 21. Make sure we close the parentheses on the cosine inverse. And this tells us that the angle is about 0.22 radians. So theta is equal to 0.22 radians. Let's do one more example. Finding the angle between, let's say A is equal to I minus 2j plus k, and B is the vector I plus j minus 2k. Again, I'm going to find the pieces of the formula first, and then we'll go to the formula. First, we need to know what A dot B is. 1 times 1 is 1. Negative 2 times 1 is negative 2. And 1 times negative 2 is negative 2. Gives us a total of negative 3 for the dot product. Then we need the magnitudes. The magnitude of A is the square root of 1 plus 4 plus 1, or the square root of 6. The magnitude of B is the square root of 1 plus 1 plus 4, which is also the square root of 6. And so when we put that all together, we know the cosine of theta is equal to the dot product, negative 3, over the square root of 6 times 6, which is actually 36. And the square root of 36 is 6, which means this reduces to negative 1/2. Well, here we don't have to go to the calculator because negative 1/2 is one of our key points on the unit circle. The x-coordinate is negative 1/2 at the point 2 pi over 3. So theta must equal 2 pi over 3. This is our angle between the vectors. As we're discussing the angle between vectors, one important relationship comes out of this. We'll go ahead and call this number 3. And it's this concept of what are called orthogonal vectors. And orthogonal is just a big fancy word that means perpendicular or right angles. Basically, two vectors that meet at a right angle. And to set this up, let's say if u dot v turned out to be 0. Then, as we're trying to find the angle between the vectors, we would say the cosine of theta is equal to the dot product divided by the magnitude of u times the magnitude of v. But 0 divided by anything is 0. And we know from our unit circle that the x-coordinate is 0 at pi over 2. So therefore, the angle theta
is pi over 2. We have a right angle formed between these two vectors. Those vectors are orthogonal if u dot v is equal to 0. The vectors are orthogonal. So that can save us a little bit of work if we end up with orthogonal vectors. If I asked you to find the angle between vector p, which is at 1, 0, 5, and vector q, which is at 10, 3, negative 2, we would start going through that same process that we had before. We would first find the dot product, p dot q, and then we'd find the magnitudes and set up our formula. But look what happens when we do p dot q. We end up with 10 plus 0 minus 10 to give us a dot product of 0. As soon as I see that dot product is 0, I know the vectors are orthogonal, which means the angle between them has to be pi over 2, and I can stop there. Saves us a little bit of time. In fact, we can even go a step further, and we can find components to make vectors orthogonal. We can find maybe an x, so that vector p equal to 2, 8, negative 1, and vector q equal to some missing component x, negative 1, 2, such that those two vectors are orthogonal. Well, if I want these vectors to be orthogonal, p dot q has to equal 0. So let's calculate p dot q. Multiplying the x components, we get 2x. The y components, negative 8. The z components, negative 2. And to be orthogonal, that has to equal 0. Well, this is a real simple algebra equation. By adding 10 to both sides and dividing by 2, we find out if that first coordinate is a 5, p and q will be orthogonal vectors. So in this video, we've taken a quick look at the dot product. The dot product is a way to multiply two vectors together to end up with a scalar. And that dot product is commonly used to find the angle between two vectors. Go ahead and take a look at the homework assignment to practice these. And then in our next video, we'll take a look at how we can multiply vectors together to get a vector. We'll see you in class. The second type of multiplying vectors is called the cross product. And the cross product has a very specific purpose. It's to answer the question, how do we find a vector orthogonal to two vectors? And as I said, the answer to this is the cross product. It's a product where we multiply two vectors together and end up with another vector that is orthogonal or perpendicular to the other two vectors. In fact, let's write that down. Always orthogonal to the other two vectors. And unlike the dot product, the cross product only works in 3 dimensions. So let's say I've got a vector u that has component form of a, b, c, and another vector v that has component form d, e, f. If I want to calculate the cross product of u crossed with v, the way we calculate that is we take bf minus ce to get the x component, cd minus af to get the y component, and ae minus bd to get the z component. Now, while this technically is the formula for the cross product, and if you really like memorizing formulas, you can memorize this formula, I find it very difficult to memorize the cross product formula. So instead, I look at a thing that comes from linear algebra that's quite simple called the determinant. And here we're not going to go into detail with the determinant. We're just going to look at how a determinant works with what's called the 2x2 matrix. If I want the determinant of a, b, c, d, the way the determinant is calculated is we take the first diagonal, AD, and we subtract the second diagonal, CB. Or actually, let's put it alphabetically. Let's call it BC. And if I can remember this pattern of multiplying one diagonal and subtracting the other diagonal, it's actually really easy to find the cross product. The cross product is the determinant of the other rows. Actually, we'll call them other columns. With a little caveat that the middle component we do backwards. Here's what I mean by that. Let's say we'll take the same u and v vectors and put them on top of each other. U is a, b, c. And v, we said was d, e, f. To combine these to get u crossed with v, first we look at the x component. When we do the x component, we ignore the x column and find the determinant of what's left, which is bf minus the other diagonal, ce. Then when we do the middle component, we ignore the middle column, and the middle works backwards. So we're going to do the backwards diagonal first. So we're going to diagonal and do cd minus the af diagonal. Then for our third component, we can ignore the third column, and we've got ae minus bd. And you notice that gives us the exact same formula we had up above that I highlighted in yellow. But by using this determinant strategy, we don't really have to memorize the formula. We just have to remember, ignore the column we're working on, find the determinant, and the middle works backwards. So let's try a few examples. Let's say vector p is equal to 5, 1, 2, and vector q is equal to -2, 3, 1. If I want to do p crossed with q, we can take the 5, 1, 2 above and the -2, 3, 1 below, and we can cross them For the first component, we ignore the first column, and we find the determinant. 1 times 1 is 1, minus 2 times 3 is 6. For the second component, we'll ignore the second column, but we have to work backwards. 2 times negative 2 is negative 4. 5 times 1 is 5, and we subtract, so minus 5. And then for the third component, we ignore the third column. 5 times 3 is 15. Minus 1 times negative 2 is negative 2, so it becomes a plus 2. And when we put that all together, we get our cross product, which is negative 5, negative 9, 17. And what we've done is we have found a vector that is perpendicular, orthogonal to both p and q vectors. Now here's an interesting question, though. With multiplication, including the dot product, order does not matter. Does order matter with the cross product? Let's take a look at it. Let's do b here. And we're going to cross them in the opposite order. We're going to do q crossed with p. And when we do that, now we've got the q vector first. Negative 2, 3, 1. And the p vector second. 5, 1, 2. And when we cross those, let's see what we get. Ignoring the first column, 3 times 2 is 6, minus 1 times 1 is 1, comma. Ignoring the second column and working backwards in the middle, 1 times 5 is 5, minus negative 2 times 2 is negative 4, so plus 4, comma. Ignoring the third column, negative 2 times 1 is negative 2, minus 3 times 5 is 15. And now what we end up with is 5, 9, and negative 17. How does that compare with the answer we got before when we did p.q? Notice every positive is negative and every negative is positive. They are not the same, but they're very similar because they're both perpendicular to our vectors. They just need to go in opposite directions. Which kind of starts to lead to some properties of our cross product. P cross q and q cross p are very similar. They're just opposite directions. Let's list some properties of the cross product. So first, we'll do some general properties. And we'll start with the one we just talked about. That if we do u cross v, that's going to be the opposite of v cross u. Another interesting thing about our properties is if you have a constant or a scalar that's multiplied by a vector, it doesn't matter when or where you multiply that scalar. You can take that scalar times the cross product of uv, or we can do the scalar times u and then cross it with v. Or we can do the u crossed with the scalar times the v. It doesn't matter where that scalar appears, with the u, with the v, or in front of the cross product. You'll get the same result either way. Another interesting result is if we take a vector and we cross it with the 0 vector, 0, 0, 0, you can imagine the multiplication working out there. You're ultimately doing a lot of multiplying by 0. You end up with the 0 vector. The 0 vector is just a vector filled with zeros. And if we took a vector and we crossed it with itself, if you imagine what's happening there is when we do that determinant step, you're going to be subtracting the same thing that you multiplied. And so you'll also end up with the 0 vector. So those are some general properties of the cross product. Some specific properties, though, with our ikj vectors that are interesting. If I is crossed with j, we end up with k. And if j is crossed with k, we end up with I. And if k is crossed with I, we end up with j. So it kind of looks like if we cross, we just end up with the other vector. But one thing we have to be careful of is with cross product, the order matters. That means if we were to actually calculate j crossed with I, we can't just say it's the missing k. It's actually the opposite of k. And k crossed with j is the opposite of I. And I crossed with k is the opposite of j. So the order does matter there with those properties. So let's see if we can use some of these properties to help us simplify some of our cross products. Let's leave those ijk properties on the screen as we go to number 3, using the properties. Let's take a look at doing 2i crossed with 3j, and the answer crossed with j. Well, one thing we know about scalars is we can pull those scalars out front, and we still get the same result. So what we're really talking about is 6 times I crossed with j crossed with j. Well, we know that ij crosses to k. So we have 6k crossed with j. We also know that k crossed with j, notice that's backwards. So we're going to get a negative out of it, negative 6i. And so we end up with our final solution using the properties of negative 6i. Let's do another one. Let's do I crossed with k, cross that with k, crossed with j. Well, ik crosses to j, and kj, actually ik crosses to negative j because the order is backwards. Kj crossed to negative I. Well, we know these scalars, these negative scalars, can pull out front. So negative 1 times negative 1 is a positive 1. We're really just doing j crossed with I. And j crossed with I, we know, is negative k. And so in this way, we can simplify using some of our cross product properties rather than having to go through all the work of the determinant to find our final cross product. That's what we're looking at today, though, is the cross product. You can either memorize the formula or remember the cross product pattern. Remember, the center is the opposite order, but the other two follow that determinant pattern. We'll take a look at these in class, practice some of these on the homework, and we'll answer your questions when we see you. Vectors provide us a great transition into talking about equations of surfaces in three-dimensional space. We're going to start here in this section talking specifically about lines and planes. So we're going to answer the question, how do we find equations of lines and planes in space, in 3D graphing? And we'll start with the first one being the equation of a line. And similar to how we do equations of lines in 2 space, y equals mx plus b, in 3 space, we also get a slope-intercept field to a formula. But we're going to set it up with vectors. We're going to let r0 be a vector. We're going to call it x0, y0, z0. Be a vector to a point on the line. We're going to let v, which is going to be represented with ABC, be a parallel vector to the line. In other words, vector v is going in the same direction. Then, actually, let's look at a visual of what we have here. So we've got our three-dimensional space. And let's say there's some line floating out here in three-dimensional space. We're going to take a point on the line. And that point we're going to call x0, y0, z0. And so the vector that points at that is going to be vector r0. And then we're going to have another vector that's parallel to the blue line. We're going to call that vector v. So that's kind of visually what the pieces are. If we combine those pieces together, the line is the vector r equal to the r0 vector plus the parallel vector times t, which is going to create a parametric equation in terms of t. So the line is the vector r0 plus the vector times t, where we kind of have a slope-intercept feel where we've got a slope of the vector, which is parallel, and the intercept or a starting point is that r0 point. So it kind of feels like that y equals mx plus b format. Now we can break this vector out. R is the vector xyz. Is equal to the r0, which is the x0, y0, z0, plus the parallel vector, which is a, b, c, times the parametric variable t. This is the vector equation of the line. And then if we take that vector equation of the line and simplify, to get a parametric equation. Where the vector x, y, z, you can see if we multiply the scalar t through the ABC, we get AT, BT, CT, and then we add the components together, and we get x naught plus AT, comma y naught plus BT, comma z naught plus CT. And if we take this apart component by component, we end up with the parametric equations. X is equal to the x component, x naught plus AT. Y is equal to the y components, y naught plus BT. And z is equal to the z components, z naught plus CT. And this becomes the parametric equation for a line where x naught, y naught, z naught are on the line, and ABC is a parallel vector. And in fact, we can go one step further and solve each of these equations for t to get what we call the symmetric equation for a line. Solving the first equation, we would subtract x naught and divide by a. That equals t. But also the second equation is y minus y naught over b is equal to t. And z minus z naught over c is equal to t. And these become the symmetric equations for the line. So if these are the equations for a line, let's see if we can make one. Let's do an example where we find the equation of a line through 2 points. We're going to find the equation of the line through the points 1, -3, 2, and 5, -2, 8. Any 2 points in space can be connected with a line, and we can find that line. First, we need to know a parallel vector and a point on the line. So for the parallel vector, that's just going to be the vector that connects these 2 points together. Let's take the 1, -3, 2 as the initial point, and the 5, -2, 8 as the final or terminal point. Let's call that t for terminal point. And we know to get the vector that connects them, we subtract the coordinates. 5 minus 1 is 4. -2 minus -3 is +1. And 8 minus 2 is 6. So now we know 4, 1, 6 is a parallel vector in the same direction as this line. We can use either one of these points. So let's see, we've got our parallel vector. Let's do our r naught vector being just the first point. We could have picked either point, but 1, -3, 2. And from this, we should be able to get a vector equation for the line. And the vector equation for the line is x, y, z is equal to the initial vector, 1, -3, 2, plus the parallel vector, 4, 1, 6, times t. And once I have the vector equation, we can find the parametric equations for the line by simplifying. The x coordinate is equal to a 1 plus 4t The y component is equal to the y's, which is -3 plus 1t. And the z component is equal to the z's, which is 2 plus 6t. And this becomes the parametric equations that will build this three-dimensional line that connects the 2 points. We can then solve each of these equations for t to find the symmetric equation form of each of these lines. When we do that, we get x minus 1 over 4 equals t is equal to y plus 3 over 1, which we don't need to do the divide 1, which is equal to z minus 2 over 6, which are all equal to t. So we have 3 different ways to represent this same line, either in vector form, parametric form, or symmetric form. But this gives us the equation of the line that connects the 2 points. Any 2 points, we can find a line that connects them. If we have 3 points, though, 3 points can be used to define what's called a plane. Let's look at finding the equation of a plane. And a plane is just a big, flat surface, kind of like a piece of paper or your screen. But it goes on forever, just like a line goes on forever, but it's incredibly thin. The flat surface is this big flat space that spreads out forever. And we're going to set this up in a similar but slightly different way than we set up the line. We're going to let r0 be a vector to a point on the plane. And just like before, we can represent r0 as x0, y0, z0. And we're going to have another vector. We called it the vector v before because it was parallel. But this time we need a normal vector or an orthogonal vector that's perpendicular. So because it's normal, we're going to call it vector n, be a normal, which means perpendicular, or orthogonal vector to the plane. So visually what we have, if I were to draw a picture, somewhere out here is this big flat space that goes on forever. And we've got a point on the plane. That's our point, x0, y0, z0. The vector that goes to it, that's our r0. And then there's this other vector that's going to come straight out of it. It's going to be perpendicular to the plane. That is our normal vector. What we know about vectors that are normal or orthogonal is the dot product of the vectors must equal 0. So if I pick any random point on here, we'll call that vector r. And I look at the vector that connects r to r0, it's going to be perpendicular to vector n. Well, the vector that connects r to r0 is the vector r minus r0. And if I dot that vector with something that's normal to it, or orthogonal to it, we know orthogonal vectors have a dot product of 0. So we can say that the plane is the product. The normal vector dotted with r minus r0. Similar to before, that normal vector we said, let's call that normal vector, just like before, is going to be the vector ABC. So the vector ABC is dotted with the difference between our general vector at any x, y, z point minus the specific point on the plane x naught, y naught, z naught. We know that product is going to be 0, which means if we simplify, we've got A, B, C dotted with x minus x naught, y minus y naught, and z minus z naught equals 0. Which means if I keep going, this simplifies to what we call the scalar equation of a plane. The dot product says we multiply the components. A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And remember, a, b, c is the components of the normal vector. And x naught, y naught, z naught are the coordinates of a point on the plane. This is the scalar equation of a plane. Good one to know. Now, I could go through a step further, and I could distribute and combine like terms to get rid of the parentheses. This gives what we call the general form of a plane. And so when we distribute, we get an AX, we get a BY, we get a CZ, and then we get a lot of constants that we're going to say all those constants are going to add together to a D equals 0. And that becomes the general form of a plane. So we looked at an example where we connected 2 points to get a line. Let's do an example where we connect 3 points, which always define a plane. I guess there's one exception. If those 3 points are linear, they don't define a plane. But let's say these 3 points are not collinear. Let's say our points are 3, -1, 2. Q is the point 4, -2, 1. And R is the point -5, 3, -1. Well, the first thing we need to find the plane that connects these 3 points is we need the normal vector. A plane is built with a normal vector and any point. So we need a normal vector. And the best way to get a normal vector or an orthogonal vector is to use a cross product of 2 vectors on the plane. So we can connect P, Q, and R in any 2 ways. There's 3 or 6, if you count backwards, ways to connect these. We need to connect 2 of them. Let's connect P and Q in a vector, which is going to be the vector 4 minus 3 is 1. -2 minus -1 is -1. And 1 minus 2 is -1. Then let's connect the vectors P and R together. I could have done Q and R. We'd get the same final result, any 2. But P to R, -5 minus 3 is -8. 3 minus a negative 1 is 4. And negative 1 minus 2 is negative 3. To get a vector that's normal to both of these, because both these vectors actually lie on the plane, connecting points that are on the plane, we want a normal vector. We're going to cross them. And when we cross, ignoring the first column, negative 1 times negative 3 is 3. Minus 4 times negative 1 is negative 4, so 3 plus 4. Comma, ignoring the middle column, going backwards, negative 1 times negative 8 is 8. Minus 1 times negative 3 is positive 3. Comma, ignoring the third column, 1 times 4 is 4. Minus negative 1 times negative 8 is positive 8. And so our normal vector then is equal to 7, 11, negative 4. We can pick any point on the plane, a vector that points to any point. So let's just use the first point. It doesn't matter which one we use. 3, negative 1, 2. And now that we have a normal vector and a point, we should be able to build the scalar equation. And you recall the scalar equation is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, and c come off the normal vector. So a is 7 times x minus the x point, which is 3, plus b, which is 11, times y minus the y point, which is negative 1, plus c, which is negative 4, times z minus 2 equals 0. This then is the scalar equation form of the plane that connects the 3 points. We can do a little algebra to get the general equation form of the plane. And we can get that general equation by distributing 7x minus 21 plus 11y plus 11 minus 4z plus 8 equals 0. Combining like terms, we get 7x plus 11y minus 4z. And then we combine the negative 21 plus 11 plus 8 to get negative 2 equals 0. What I've done here is tried to give you a visual of what we just graphed, the 7x plus 11y minus 4z minus 2. And as you can see, we end up with this flat plane that we can see from all angles in 3 dimensions. And if we were to try and find the point on here of negative, or of positive 3 on the x, negative 1 on the y, it should also put us at about z of 2. And this graph doesn't quite get us there exactly, but it should be around here. You can see 4 on x, negative 2 on y. It's approximately a z of 1. Again, the graph doesn't quite hit it perfectly because it's in between these points. And you can also see negative 5 on x, 3 on the y. It's going to be approximately negative 1 on the z if I could get in there perfectly. But this graph only lets me hit on the grids, which are off slightly. But you can see we've made this plane that connects our 3 points using our vectors. So that's what we're looking at today. The equation of a plane is found by using a normal vector and a point on the plane. The equation of the line is found using a parallel vector and a point on the line. Take a look at the homework assignment to practice some of these, and we will see you to work on these further in class. Now that we've taken a look at the graphs of lines and planes in 3D, we're ready to extend that conversation as we ask, how do we graph other shapes or other curves or surfaces in space. And we're going to start with kind of the basic graph, and that is going to be the graph of a cylinder. And a cylinder in 3-space graphing is not what we think of with a normal cylinder. Normally, we think of a cylinder like a soup can. But actually, a cylinder is going to be defined here as any 3D shape made of parallel curves. And the most basic form of that, and there are others, but the most basic form of that is when one variable is missing from the equation. What we'll do in that case is we will graph in the other planes and copy down the missing variable. In other words, if x is missing, we'll graph it in 2 dimensions on the yz plane. And then we'll copy that yz graph all the way up and down the x graph. Let's take a look at some examples so we can see that happen. First graph we're going to do is z equals x cubed. First thing I'll observe with z equals x cubed is that the y variable is missing. So if the y variable is missing, we're going to graph it on the xz plane. So we'll graph it 2-dimensionally, but we'll graph it on xz. And we know that the graph of anything cubed is going to be this graph that comes up from the negative, levels off at 0, and then kind of takes off after that. That graph on the xz plane, then, is going to be copied down the y-axis. So now we try and transition that 2-dimensional graph into a 3-dimensional graph where we've got x, y, and z. And we've already graphed on the xz plane. Let's go ahead and draw the negatives also on this coordinate system, so we can kind of see in 3 dimensions there. So the xz plane, we've already got this graph that comes up on the xz, levels off, and then takes off, where kind of y is 0. But that same graph is going to be able to slide up and down the y-axis. And so we'll see it levels off at 0 and takes off, or back down the y-axis, where it comes up, levels off, and takes off. And so what we end up with is this kind of 3-dimensional sheet with a little bit of a curve to it. Maybe emphasize that the peaks and the valleys line up here. This 3-dimensional sheet, it's a cylinder of all of these parallel graphs, these parallel lines made of z equals x cubed, all the way up and down the line. Let's take a look at another example. Let's graph z equals y squared. Because we just have z and y, we're going to graph it on the yz plane. So we'll start with our 2-dimensional graph, so we know what that looks like on the yz plane. And we know that the squared variable gives us that parabola graph. And so we're going to copy that graph down the other variable, down the x-axis. So let's see if we can do that. We've got x, y, and z. Let's include the negatives, even though we don't really need them in this graph. What do we do on the x? And now with the ZY plane, that's almost the actual two-dimensional plane that we're used to here. The ZY plane is this parabola. And that parabola is going to go all the way down the x-axis. And all the way down the x-axis the other direction. And so you can see we kind of end up with this three-dimensional curve. It's a parabola going all the way down the x-axis. And this then becomes our three-dimensional graph of z equals y squared. Now, this idea of graphing a two-dimensional version of the graph and then seeing how it stretches along the graph, there's actually a name for that two-dimensional version for the graph. So let's go ahead and formally define that here. We call it a trace, or a cross-section that is created when a surface intersects a plane parallel to a coordinate plane. We've been focusing thus far when one of the variables is 0. So we've got either the xy plane, the yz plane, or maybe the xz plane. We're on that center point. But it doesn't have to be on that center point. It could be anywhere. So let's say we've got, your typical cosine graph. And let's see if I can make it 3D by drawing another cosine graph back here. There's your three-dimensional graph. It's a cylinder because it's that same graph stretched all the way through. And the idea is if we were to cut it in the middle, what you end up with is a nice little cosine graph cut in the middle. It's that two-dimensional representation when it's sliced down. And then that two-dimensional is stretched throughout the rest of the graph to give you the 3D version of it. These traces become very helpful when we try to graph other shapes that aren't just this cylinder shape that stretches throughout the whole graph, but it changes as you go through the graph. We talked about lines and planes. The next level up, lines and planes are made with x, y, and z. The next level up are made with x squared, y squared, and z squared. These graphs are called quartic surfaces. And now, in general, a quartic surface is of the form ax squared plus by squared plus cz squared. And then we've also got combinations of the x's and y's. So we've got dxy plus eyz plus fxz. And then we've got x's and y's that could appear by themselves. Gx plus hy plus, we have to skip I because that's the square root of -1. So we'll jump to jz. Or there's also possibly having a constant k equal to 0. Some combination of x squared, y squared, z squared, x, y's, and z's, combinations thereof. We call those the quartic surfaces. This is the three-dimensional version of our parabolas, ellipses, hyperbolas, circles, the conic sections, now in 3D. Let's look at trying to graph one of these quartic surfaces. Let's try and sketch x squared over 4 plus y squared over 9 plus z squared over 25 equals 1. One thing you might notice is this kind of has the feel of an ellipse. But we're going to see if the traces can confirm that suspicion. What we can do with traces is we're going to take a trace in each direction. First, we're going to do a trace on the xy plane, which means we don't want any z's. We can make z equal to any convenient number we want. The easiest one's probably going to be 0. If that didn't work, we'd have to pick another number. Sometimes if z is 0, everything goes to 0 and it's useless to us. But in this case, it doesn't. We end up with x squared over 4 plus y squared over 9 plus 0 equals 1. And we recognize this graph as an ellipse on the xy plane. In the x direction, we're going to go 2 each direction. In the y direction, it goes 3 each direction. And so we end up with this nice little ellipse in the xy direction. We need to know what's happening in all the directions, so we're also going to draw a trace in the xz direction. When we do this, y is equal to 0. So we end up with x squared over 4 plus z squared over 25 equals 1. All right, in the xz direction, the x's, because the denominator is 4, the square root is 2 each direction. The z's go each direction 5 units. And so on this xz graph, we end up with this tall, skinny ellipse. And I'm not going to quite fit it all on one screen. But we do need to also do a trace in the yz direction, which means our x is equal to 0. When x is equal to 0, the equation becomes y squared over 9 plus z squared over 25 equals 1. And so if we were to try and draw that, we end up with the y's. Got our yz axis. The y's are going 3 each direction, so it's a little wider than the green one. The z's still going 5 each direction. And we end up with this slightly fatter ellipse. And now what we're going to try and do is put these 3 graphs together in one. What we see is in the yz direction, we get a fat, tall ellipse. In the xz direction, it's a skinnier ellipse. In the xy direction, it's really a small ellipse. And so when we put it all together, into a 3D graph, what we end up with is the short, skinny one, one direction, tall and skinny another direction, and fatter and skinnier, fatter and a little wider the other direction. We end up with this 3-dimensional, what we call an ellipsoid. So that's how we can use the surfaces to kind of combine them each together to end up with our 3-dimensional ellipsoid. What I've done here is I've drawn on a online calculator the 3D ellipsoid. And what you can see is if we look at the top, we see that ellipse that goes from 2 to 3. If I look from one side, we see the ellipse that goes from 2 to -2 one direction and 5 to -5 another direction. And if we look at the other side, we see the slightly fatter 3 to -3 and 5 to -5. And this 3D shape is our ellipsoid we've been trying to draw. Now, there are some common quadric surfaces that we're going to work to get familiar with in this section. And your book has a really nice introduction to them on page 221 through 222. And so I want to hop over to a picture from the book of those shapes, just so that we can talk about some characteristics really quick about each of these. We've already talked about the ellipsoid. The ellipsoid is similar to the ellipse. We've got an x squared over something plus y squared over something plus a z squared over something. What really makes an ellipsoid defined is you notice that x squared, y squared, and z squared are all positive. And they're not going to equal 0. They're going to equal a number. That's going to create the ellipsoid. And if A, B, and C all are equal, we actually end up with a perfect sphere because all of those major and minor axes are going to be equivalent. And just like we saw before, the traces were all ellipses in the various directions. Now, if we make a minor change and we make one of them negative, so we've got a positive, and you see that we've got that negative z squared. If one of them is negative, we end up with what's called a hyperboloid of one sheet. So with two of the variables positive coefficient, one with a negative coefficient. And then the way we know which direction this hyperboloid is pointing is that the axis corresponds with the negative coefficient. So in this case, the z squared was negative, and so you see the graph here goes around the z-axis. If the y squared was the negative one, it would turn sideways and go around the y-axis. Now, if two of the terms are negative, here we've got two variables with negative coefficients and one with a positive coefficient, a positive, a negative, and a negative. We end up with what's called a hyperboloid of two sheets. The hyperbola with two sheets doesn't connect in the middle. And what we also notice is that the axis of the surface corresponds to the variable with a positive coefficient. So here, the z squared was positive, and that's why it goes around the z-axis. If the y squared was positive, it would go around the y-axis. If the x squared was positive, it would go around the x-axis. Now, each of these have been equal to a number, but sometimes our equations are equal to 0, which changes things slightly. One example here is the elliptical cone. With the elliptical cone, we've got two positives and one negative, but this time it equals 0. If it equals 0, then the axis of the surface will correspond to the variable with the negative coefficient. So again, here the z is negative. That's why the cone goes around the z-axis. We end up with an elliptical paraboloid if we have a constant term, z. And the x and y terms are each squared. That constant term is called the linear term, and the axis will correspond with the linear variable, which is why this graph goes around the z-axis. Finally, the last one we're going to look at for our purposes is the hyperbolic paraboloid. The hyperbolic paraboloid is really interesting because in one plane you have a hyperbola, in the other planes you have parabolas, and the way we get that, very similar to our last example, except we've got the middle term is negative. Or there's a negative in between the x squared and y squared, still equal to a linear term. And that linear term that it's equal to is going to be the axis of the surface that it's all built around. Also interesting is it's going to wrap around the positive variable. So these 6 shapes, you can see them in your book. It also lists all the traces that you're going to get from each of these x, y, z directions. There's going to be some problems on the assignment where it's going to ask you to identify what shape you're dealing with. And the way we can do that is by paying attention to what's positive, what's negative, and what does it equal. So let's see if those are our common quadric surfaces. Let's see if we can identify some quartic surfaces. Let's say we're given the surface 16x squared plus 9y squared plus 16z squared equals 144. What I would notice on here is looking at the squared terms, x squared, y squared, and z squared, all the squares are positive. We've got a positive 16x squared, a positive 9y squared, a positive 16y squared. It also does not equal 0. So if I were to go through and divide the whole thing by 144, it would be equal to 1, which is exactly the form of the ellipsoid. Let's take a look and see what this graph looks like in the 3D graphing calculator. So here's our 3D graph. Just as we expected, it's an ellipsoid. All the traces are ellipses, just like we predicted. So we're doing good on that one. Let's try another example. Let's see if we can identify the shape of 9x squared minus 18x plus 4y squared plus 16y minus 36z plus 25 equals 0. Well, what are we going to note about this shape? I do see that there's an x and a y term, but those could be paired with the x squared and the y squared. And through a process of completing the square, we could make that x or y plus or minus some number, the whole thing squared. So those kind of come in groups. But I do notice that the z is a linear term. So we have x squared and y squared are positive. And the z is linear. Going back to our graph, we saw x squared and y squared positive, and the z linear with the elliptic paraboloid. And it could be either variable linear. What we have is two squared variables and one linear variable. And the linear variable is going to tell us which axis this graph is going to wrap around. So we end up with an elliptic paraboloid here. And if we go to the graphing calculator, let's see if our guess was correct. And here is our shape graphed. What you see is it does have that bowl shape that we were expecting from the elliptic paraboloid. It's an ellipse from one angle and a parabola from the two other angles. We have an elliptic paraboloid. Let's do one last example of identifying our shape. We're going to do 9x squared plus y squared minus z squared plus 2z minus 10 equals 0. And let's see what we can note about this shape. Again, we've got a z linear term, but it can be paired with the z squared through a process of completing the squared. So we have x squared and y squared are positive. But you notice that z squared is negative. So we have two positive squares and one negative square. And that plus 10 can bump to the other side, so it's not going to actually be equal to 0. Which one did that? Two positive squares and one negative square. That's going to be a hyperboloid of one sheet. It is a hyperboloid. of one sheet. Let's look at this example on the graphing calculator. Here's our hyperboloid of one sheet on the graphing calculator. You notice one direction it's a hyperbola, other direction it's an ellipse, and the other direction it's a skinnier hyperbola. We've got our hyperboloid of one sheet because it's going to go through the origin. The hyperbolas connect in the middle. If we had two negatives, then they wouldn't connect in the middle, but it is hollow in the center. So today, that's what we're taking a look at, three-dimensional shapes, whether they're cylinders or quadric surfaces. Hopefully, you can get some familiarity with the different shapes as you work through the homework assignment. And in class, we'll discuss them further and answer any questions that you may have. As we wrap up Chapter 2 and our discussion about graphing in 3D and how vectors can help us with that, I want to address another question that asks, what other coordinate systems do we have for graphing in space? Just like with the rectangular coordinate system in 2D, we had the xy coordinates, but we also had polar coordinates that used a radius and an angle theta with the x-axis. Sometimes the polar system was easier for graphing equations and interpreting situations, and sometimes the rectangular was better. Do we have the same situation with three-dimensional graphing? And the answer is yes. We've got two other coordinate systems that we can use. The first of the two are called cylindrical coordinates. And cylindrical coordinates are kind of like polar coordinates in 3D. With polar coordinates, we had a radius and an angle theta. To make it in 3D, we're just going to add an extra coordinate z that tells us how far vertically the graph point is in that z direction. So let's formalize that here. Let's say it is similar to polar coordinates. Which have r theta, a radius and an angle theta. And angle with the x-axis. We're just adding this z, which is the vertical distance. In the plane. Or in space. So visually, what we're talking about here is we've got our x, y, z axis from rectangular. And instead, what we're going to do is we're going to have some radius that makes some angle theta to a point. And then we go vertically to some point, some distance z. And that vertical z makes a right angle with the radius r. So if we've got this cylindrical coordinate system, let's talk about how we can make conversions between the rectangular system and the cylindrical system. Very similar to polar coordinates, x is equal to r cosine theta, and y is equal to r sine theta. We just have this new coordinate z, which is just the vertical distance, which works the exact same way in both systems. And similarly, if we're going the other way, we know that r squared is equal to x squared plus y squared from the Pythagorean theorem, and that the tangent of theta is equal to the y distance over the x distance. And again, the z coordinate is just the z coordinate. Now there is one thing we got to be careful of in 3 space. With the tangent of theta, we want to make sure that we check the domain as we take the tangent inverse, because on our calculators, tangent inverse is always between pi over 2 and negative pi over 2. And sometimes we want to be in the opposite half of the grid. So we have to really think about where our point is. And we'll look at an example of that right now. Let's do some examples where we can use these conversions. Let's say we have the cylindrical point (5 pi over 6, 4), and we're going to convert it to a rectangular point. Well, very similar to what we did with polar coordinates, x is equal to the radius of 5. Let's go ahead and label 5. So the radius, pi over 6 is the theta, and 4 is the z. So x is equal to the radius of 5 times the cosine of the angle pi over 6. Y then is the radius of 5 times the sine of the angle pi over 6. And the z-coordinate is just what the z-coordinate is, which is 4. Simplifying our x and y then, cosine of pi over 6 is root 3 over 2. So we end up with 5 root 3 over 2 for the x-coordinate. The sine of pi over 6 is 1/2. So we end up with 5/2 for the y-coordinate. And so our cylindrical point changed to rectangular xyz becomes 5 root 3 over 2, comma 5/2, comma 4. And we have our rectangular point that is equivalent to the cylindrical point, 5 pi over 6, 4. We can also go the opposite direction. We can take a rectangular point and convert it into a cylindrical. Let's take the rectangular point, -8, 5, -7, and convert it to a cylindrical point. For the cylindrical point, we now have x, y, and z that we're converting to in r, a theta, and a z. Well, our formula says that r squared is equal to x squared, 64, plus y squared, 25, which is equal to 89. Taking the square root of both sides, the radius must be equal to the square root of 89. Theta comes from the tangent. The tangent of theta is y over x. So we're going to take the tangent inverse of y over x, 5 over -8, which is equal to negative, doing it on our calculator, it'll give you negative 0.5586. But here's where we have to be careful with the tangent inverse. If I think about just the xy plane, z, it's going to be vertically or below this. Looking at the xy, x is -8, y is 5. Our point is going to be above some point in the second quadrant. However, a theta of negative 0.55 is a negative angle. Negative 0.5586 goes the wrong direction. We need to move it so it goes to the correct direction. Well, the distance that we need to move it is halfway around the unit circle. We need to add pi to get to the correct spot. So when we do negative 0.5586 plus pi on our calculator, we'll get approximately 2.583. And that's going to be the number of radians that we want it to open up to get us in the correct quadrant. So again, we want to make sure we're careful. Tangent inverse on our calculator will always stick us on the right half of our xy graph. which means if your point ends up in the left half, you have to add a pi to it to get to the correct place. And a quick sketch can help you see what's happening there. Now with z straightforward with these cylindrical points. Z is just the z, so -7. So we end up with our cylindrical point of the square root of 89 for the radius, 2.583 radians for the angle, and -7 for the z value. We've got our rectangular point. We can even switch between equations in rectangular and equations in cylindrical. Let's say we've got the equation that r is equal to 3 sine of theta. And we want to convert that equation to a rectangular equation. Well, we know that r sine theta is equal to something. So if we multiply both sides by r, we end up with r squared equals 3r sine theta. And we know from our formulas that r squared is x squared plus y squared. 3 is just a constant. We know that r sine theta is equal to the y coordinate. And so we've converted this to a rectangular equation. X squared plus y squared equals 3y. Represents the same equation in cylindrical as r equals 3 sine theta. So that's cylindrical coordinates. Very, very similar to polar coordinates, which we're already familiar with. But there is a second three-dimensional graphing system that I want to talk about called spherical coordinates. And with spherical coordinates, we end up with 3 Greek letters for our coordinates: rho, theta, and phi. Rho, theta, and phi. Rho is the distance from the origin to the point. And I want to be careful not to confuse that with the r from the cylindrical coordinates. R was the radius in the xy plane, and then we moved vertically up. Rho is going to be the diagonal distance from the origin to the point, almost like a vector that goes diagonally through space. It's the actual distance to the point, not just in the xy plane, but through space. Theta is the angle with the x-axis. Just like we did before. It's the same theta that we saw in the cylindrical coordinates, also from polar coordinates. Theta is the angle with the x-axis. And phi, our new Greek letter, phi is going to be the angle with the z-axis. So visually, what we're talking about here is there's some distance diagonally through space, rho, that comes off of a projection, if it makes a right angle. It comes off of an angle theta that's made with the x-axis, and an angle phi made with the z-axis. So we end up with 2 angles and a distance that give us the coordinates to the point. So then the next logical question is, how do we do conversions between the rectangular system that we're more familiar with and this new system, the spherical coordinates? Well, our x-coordinate is equal to rho times the cosine of theta times the sine of phi. Notice the first part looks very similar to what we had with polar coordinates and cylindrical coordinates, the distance times the cosine of the angle. We're just also multiplying by the sine of the the last angle. Y is going to be rho sine theta sine phi. And z is rho times the cosine of phi. If we're going the other direction, from the Pythagorean theorem, rho squared is equal to x squared plus y squared plus z squared. The Pythagorean theorem in 3 dimensions, because this time we're going straight to the point instead of just the xy plane. Because theta is the same theta we saw before, it's still tangent of theta is y over x. Just make sure that you check the domain again. And finally, to find phi, we solve the last equation here for phi. Z equals rho cosine of phi. Dividing both sides by rho, we get that the cosine of phi is equal to z divided by rho. That's usually going to be easier to solve, but it does require us to know rho first. So if we don't know rho, we basically just calculate it. It's the square root of x squared plus y squared plus z squared. But it'll be usually quicker just to do z divided by rho. All right, let's see if we can do some examples where we make these exact conversions. Let's start with taking a spherical point. Let's take 2, negative 5 pi over 6, comma pi over 6, and convert that to a rectangular point. Well, we need to know what x, y, and z are in rectangular points. And our conversion formulas say it's going to be rho, which is 2. Let's go ahead and label these as rho, theta, and phi, times the cosine of the first angle, negative 5 pi over 6, times the sine of the second angle, pi over 6. Y is 2 sine of negative 5 pi over 6 times the sine of pi over 6. And z is equal to rho 2 times the cosine of the last angle, just pi over 6. Simplifying these will give us our rectangular point that's equivalent to the spherical point. So we've got 2 times the cosine of negative 5 pi over 6 is negative root 3 over 2. And the sine of pi over 6 is 1/2. And that gives us negative root 3 over 2. For the y-coordinate, we have 2 times the sine of negative 5 pi over 6. That's in the third quadrant, so it's negative 1/2. Sine of pi over 6 is still 1/2, and so we end up with negative 1/2 for our y-coordinate. And finally, with z, we have 2 times the cosine of pi over 6, which is root 3 over 2, which is just the square root of 3. So our spherical point of 2, negative 5 pi over 6, pi over 6, is the same as the rectangular point, negative root 3 over 2, negative 1/2, square root of 3. Let's try going the other direction. Let's look at the rectangular point of negative 1, 1, square root of 6. And we're going to convert that to a spherical point. Well, to get spherical, we need to know what rho, theta, and phi are going to equal from our x, y, and z. Well, our rho formula actually says rho squared is equal to the sum of all the squares. So negative 1 squared is 1, plus 1 squared is 1, plus the square root of 6 squared is 6. And so that gives us rho squared is equal to 8. Taking the square root of both sides, rho is equal to the square root of 8, which simplifies to 2 root 2. With theta, theta is equal to the tangent of y over x. So if we do a tangent inverse of y over x, 1 over negative 1, or the tangent inverse of negative 1, negative 1 tangent inverse is going to be negative pi over 4. But again, we need to take a quick look at where this point is going to be. It's a rectangular point of negative 1 comma positive 1. And negative pi over 4 sticks us in the wrong quadrant. So we need to add pi to it. And when we add pi to a negative pi over 4, we're adding 4 pi over 4. We end up with 3 pi over 4 is the actual point. For phi, the cosine of phi is equal to z over rho. Z is the square root of 6 divided by rho, which we just found out was 2 root 2. And when we simplify that, we're actually doing the cosine inverse dividing by the square root of 2. We get root 3 over 2. And we know the cosine inverse of root 3 over 2 is pi over 6. And so we've ended up with a spherical point that is equal to the rectangular point of negative 1, 1 root 6. That point is 2 root 2, 3 pi over 4, pi over 6. Similar to what we did with the cylindrical coordinates, spherical coordinates can also be expressed as equations, or surfaces can be expressed as equations. Let's do rho equals 5 cosine of phi. We can manipulate these equations to try and convert them into the other form, into rectangular form. And you can see on this one, similar to the other example, if we multiply both sides by rho, we end up with rho squared equals 5 rho cosine of phi. And rho squared, we know from our formulas, is x squared plus y squared plus z squared equals the constant of 5. And then rho cosine of phi, that is directly equal to z. And so we end up with the equation x squared plus y squared plus z squared equals 5z as being the equivalent equation in spherical coordinates as rho equals 5 cosine of phi. So those are our two new systems we're looking at, spherical coordinates and cylindrical coordinates. Sometimes we might want to make a conversion, though, between these two new systems. And it is a lot of work to have to go to rectangular in the middle. So let's take a look at how we can make a direct translation between the two, how we can convert between our new systems, between spherical and cylindrical coordinates. Well, just as before, we have some conversions. Remember that spherical we just did is expressed as rho theta phi. And cylindrical is what we started with, is expressed as a radius theta times a z distance. So if we want to change spherical into cylindrical, our conversion for r is that r is equal to rho times the sine of phi. Theta, I mentioned earlier, is the same theta between both systems, so there's really no conversion needed for that center coordinate. And z is going to be rho times the cosine of phi. If we're going the other direction, we have cylindrical and we want the spherical. Rho squared from the Pythagorean theorem is the radius squared plus z squared. Again, theta is the same theta, so there's no work to do there. We just need to get after the phi, which if we take the z equals equation that we just had and divide both sides by rho, we end up with the cosine of phi is equal to z over rho, which usually by this point we will have already calculated rho, so that's easier. But if we haven't calculated rho, we just use our rho equation, and rho is the square root of r squared plus z squared. So let's see if we can do some examples where we convert directly between these new systems of graphing in space, between spherical and cylindrical. Let's do a few examples. Let's take the spherical point first. The spherical point 2, negative 5 pi over 6, and pi over 6. We're going to convert that to cylindrical. Well, for cylindrical, we need to know the radius, the angle theta, and the vertical distance z. The radius is equal to rho 2 times the sine of the angle pi over 6, the phi, the last angle. Theta is just theta of negative 5 pi over 6. And z is rho 2 times the cosine of phi times the cosine of pi over 6. Simplifying, the sine of pi over 6 is 1/2. So we end up with a radius of 1. The cosine of pi over 6 is the square root of 3 over 2, which gives us square root of 3. And so we now have our cylindrical point of 1, negative 5 pi over 6, square root of 3, which is equivalent to the spherical point of 2, negative 5 pi over 6, comma pi over 6. Let's do one more example where we go the other direction. Let's take the cylindrical point of the square root of 2, 3 pi over 4, square root of 6, and we're going to convert that to spherical. So because it's a cylindrical point, we've got a radius, a theta, and a z. I didn't label on the spherical. Back then we had the rho, the theta, and the phi. So for finding the spherical point, we need to know what rho is, what theta is, and what phi is. Our rho equation says that rho squared is equal to the r squared plus the z squared. R squared is 2 plus the z squared is 6, which means rho squared is equal to 8. Taking the square root, rho is the square root of 8, or 2 root 2. Theta is the same in both graphing systems. So we have 3 pi over 4. And for phi, we know the cosine of phi is equal to z over the rho. So we'll do the cosine inverse of z, the square root of 6, over the rho, 2 root 2. And I think we simplified this one before. We have the cosine inverse dividing out the square root of 2 of root 3 over 2. Cosine inverse of root 3 over 2 is pi over 6. And so we've taken our cylindrical point of square root of 2, 3 pi over 4, square root of 6, and we've ended up with the spherical point, 2 root 2, 3 pi over 4, and pi over 6. So that's what we're focusing on today with these new coordinate systems, spherical graphing and cylindrical graphing. Can we convert between all three systems, spherical, cylindrical, and rectangular? I want to wrap up really quick by summarizing the three graphing systems visually in 3 dimensions. So we'll make our little coordinate plane here. And normally we label them x, y, and z. But just to make it really clear, I'm going to call this I, j, and k as vectors in the x, y, z direction. When we're graphing with the rectangular system, we go a distance x, and then we go a distance y, and then we can vertically go a distance z to our point that is x, y, z. And each turn makes a right angle. That's the rectangular coordinate system. When we do cylindrical, we say instead what we're going to do is we're going to take a radius that stretches out to where we go vertically at z. And that radius is going to make an angle theta with the x-axis. And when we do, we end up with a point that is the radius theta z. With the spherical coordinates, instead what we're going to do with spherical coordinates is we're going to go directly from the origin to the point, and we're going to call that distance rho. And that rho is going to be formed with an angle of theta with the x-axis. It's the same theta as we had with the cylindrical coordinates, but also with an angle phi from the z-axis. And in that way, we end up with our point rho theta phi. So we now have 3 ways to represent that same point in space. And depending on the context, sometimes one context is much easier to work with than the other context. But for now, we're focusing our energy on learning about the 3 systems, converting between the 3 systems, and interpreting where those points will be. So take a look at the homework assignment, practice some of those, and we will discuss them more in class. Our next chapter is going to focus exclusively on these things called vectored valued functions. So this first lesson, we're going to answer the question, what are vector valued functions? And put quite simply, a vector valued function can be defined in 2D as r of t, the vector valued function, is going to be some function of t times the I vector plus some function g of t times the j vector, or in component form, f of t comma g of t. And similarly, it can be defined in 3D as the vector value function r of t is equal to some function of t times the I plus some function of g times the j and some function of t times the k, or in component form, f of t comma g of t comma h of t. Basically, it's a vector made up of functions. In fact, we've seen this type of a function before, noting that this is really just a parametric equation, or a parametric function, in vector form. When we had parametric equations or parametric functions from a previous chapter, we said x was equal to some function f of t, y is equal to a g of t, and z is equal to some h of t. And as t changed, it gave us our entire graph, our function. Now, we're just expressing those three functions as one function, as a vector. So now if I was asked to evaluate some vector valued functions, for example, let's say we have the vector r of t is equal to t squared minus 3t I plus 4t plus 1 j. And we were asked to find the vectored value function when time is -4. All that really means is we're going to plug -4 into our vectored valued function. And so we have -4 squared minus 3 times -4 times the I component plus 4 times -4 plus 1 times the j component. And simplifying, 16 plus 12 is 28i plus, actually we're going to make it minus because we have -16 plus 1 is -15j. And we've evaluated the vector valued function at time of -4. Let's try one more. Let's find the vector valued function r of t is equal to the cosine of t to sine of t and the natural log of 1 minus t. And we're going to find the vector function at pi over 6. Well, that means we're just going to plug pi over 6 into each component. So we have the cosine of pi over 6, comma 2 sine pi over 6, comma the natural log of 1 minus pi over 6. And when we simplify, we know the cosine of pi over 6 is root 3 over 2. The sine of pi over 6 is 1/2 times 2 is 1. And then we're left with the natural log of, getting a common denominator, that's going to be 6 minus pi over 6. And we've evaluated the vectored valued function at pi over 6. Now, as with any case, since a function is just a mapping from the domain to the range, we can talk about what exactly is the domain of our vectored valued function. And similar to functions that you've seen in the past, for example, we can't have 0 in the denominator, we can't have negatives under the square roots or in a natural log. Similar to those, we can apply those concepts of a domain to our vectored value function. The only rule that we have to add is our domain must work for all components of the vectored valued function. So if r of t is the function 3 over the square root of t plus 1, comma the natural log of t minus 5, comma secant of 3t, we can go piece by piece to start building a domain that works for the entire vectored valued function. One thing we see is t plus 1 is under a square root, so we know t plus 1 must be greater than 0, or equal to 0. Subtracting 1, we find out t is greater than or equal to -1. Another thing we see is we've got a denominator, and we know denominators cannot be equal to 0. Squaring both sides and subtracting 1, t cannot be equal to -1. which then, if we combine that with the first conclusion, now we're saying t is just strictly greater than -1. It cannot be equal to -1 because of our work there in the green. Continuing on, we see a t minus 5 inside a natural log. Well, natural logs must always be greater than 0. So we can say t is greater than 5, which already is greater than -1. So we kind of have built this new domain. T greater than 5 is the more restrictive domain. So we're going to stick with that for now. But we still have to deal with the secant. Because the secant, we can take the secant of anything. But secant is the reciprocal of the cosine. And we can't have 0 in the denominator. So cosine of 3t cannot be equal to 0. Well, if we do the cosine inverse, then we get that 3t cannot be equal to, cosine is 0 at pi over 2. And then, again, it's 0 at 3 pi over 2, 5 pi over 2, 7 pi over 2, basically every plus n pi, where n is the natural numbers. To get the t alone, then, we just have to divide both sides by 3. And we get t is equal to pi over 6 plus n pi over 3. And let's get a common denominator by multiplying the second one by 2. So we have pi plus 2n pi over 6. And that's actually not equals 2, because that'll make the secant undefined at all of those points. And so we can combine all of this together and say our domain is all t greater than 5, where t is not equal to pi plus 2n pi over 6. And that covers all of the components of this vectored valued function. Now, since ultimately we're interested in doing calculus with these vectored valued functions, let's talk about the first step of calculus, and that's finding the limit of a vectored valued function. And we'll start with a definition, which might be exactly what you expect, that the limit as time goes to any value, we'll call it a, of the vectored valued function r of t, is really asking us to just take the limit of each component. The limit as t goes to a of the first function, comma, the limit as t goes to a of the second function, and if it's in 3 space, the limit as t goes to a of the last function. So doing a couple quick examples. If we're trying to find the limit as t goes to -2 of the vectored valued function, the square root of t squared minus 3t minus 1 times I, plus 4t plus 3 times j, plus the sine of t plus 1 times pi over 2. Okay. Well, basically, we're just going to take the limit of this vectored valued function component-wise. So we're going to plug -2 in for all of the t's, as long as it doesn't make anything undefined. So we get the square root of -2 squared minus 3 times -2 minus 1i, plus 4 times negative 2 plus 3j plus the sine of negative 2 plus 1 pi over 2 k. Simplifying, negative 2 squared is 4. 4 plus 6 is 10. Minus 1 is 9. Square root of 9 gives us 3i. 4 times negative 2 is negative 8 plus 3. Negative 8 plus 3 is a negative 5. J. And then when we do negative 2 plus 1, we get negative 1/2, or negative pi over 2. The sine of negative pi over 2, drawing a quick unit circle, negative pi over 2 is straight down at the point 0, negative 1. Sine being the y-coordinates, so we get negative 1, or negative k. And so this vectored valued function is approaching 3i minus 5j minus k as time is approaching negative 2. Let's do one that's a little more involved than just plugging in values for the limit. We're going to find the limit as t goes to 0 of 3t squared minus 5t all over 6t squared plus t, comma, the cosine of t minus 1 over t squared. And to make this a little more straightforward, I'm going to look at it one component at a time. First, looking at the I component, or the x component, depending on how you want to look at it. If we were to plug 0 in, we'd end up with 0 in the denominator of this fraction, and that is not acceptable. So instead, what I'm going to do is I'm going to factor a t out, leaving behind 3t minus 5, and a t out of the denominator, leaving behind 6t plus 1. And that allows the t's to divide out. So now we can take the limit as t goes to 0 by plugging 0 in for the t's, which will leave us with negative 5 over 1, which equals negative 5, because we've removed that discontinuity. If we look at the j component, what we find is plugging 0 in for cosine, we end up with 1 minus 1, or 0, over 0 squared, which is 0. And so this is an indeterminate form of 0 over 0. So what we're going to do is use our old friend L'Hopital and take the limit as t goes to 0 of the derivative of cosine is negative sine of t. The derivative of t squared is 2t. But now if we plug 0 in, the sine of 0 is 0, and the 2 times 0 is 0. We're still going to 0 over 0. So we'll use L'Hopital one more time to take the limit as t goes to 0 of negative cosine of t over 2. And now when we plug the 0 in, cosine of 0 gives us 1, so we are left with negative 1 over 2. Which means the limit as t goes to 0 of our vectored valued function is going to be negative 5, comma, negative 1/2. Taking the limit component-wise of each part. Speaking of limits, and I've kind of alluded to it with this idea of continuity, to remove the discontinuity in order to find the limit, let's talk about when a vectored valued function is continuous. A continuous vectored valued function. A vector valued function is continuous if and only if the limit as time approaches a of the vectored valued function r of t is exactly the same as the vectored valued function evaluated at that value a. The limit is the same as the value, which means the limit has to exist and the value has to exist. They have to both be defined. And quite often, instead of determining where something's continuous, as we found in Calc 1, it's easier to describe when it's discontinuous, when the limit is not equal to the value at the function, when we have a gap, a jump, or an infinite discontinuity. So let's say we have the vector valued function r of t is equal to e to the t I plus the sine of t j. What we know about the part e to the t is continuous for all values. We never have to lift our pencil as we graph it. Similar with sine of t. Sine of t is continuous for all values. There's no gaps, no jumps, no asymptotes, vertical asymptotes. It's actually defined for all real numbers, and the limit is also defined for all real numbers. So this is continuous for all real numbers. So let's do an example that might be a little more exciting. Let's take the vectored valued function r of t is equal to the vector 1 over x, comma, tangent inverse of x. Well, looking at the first component, 1 over x is undefined at 0, which means while the limit exists at 0, the function does not. And so we're going to say it's not continuous at 0 because we have an asymptote. We're also not continuous when tangent inverse is undefined. We know tangent inverse is undefined. Tangent is y over x, so it's undefined whenever the x-coordinate of the unit circle is 0. That happens at pi over 2 and every n pi after that. So we have 2 points of discontinuity, one from each component. So this video is a real brief introduction to these things called vectored valued function. Really, it's just a fancy way to take a parametric equation and put it into a vector form so it's one single function. We'll be using these vectored valued functions to do a lot of modeling of different situations, do a lot of different calculus tricks. But for now, we're going to do some homework problems, get comfortable with vectored valued functions in general, and we'll see you in class to answer any questions you may have. Now that we've taken a look at what vector valued functions are, we're ready to answer the question that we really care about, because this is a calculus class. How do we do calculus of vectored valued functions? And let's start with the first part of calculus, Calc 1, where we took derivatives. And quite simply, to take the derivative of a vectored valued function, we're going to take the derivative of each component. So let's do some examples where we do just that. First, let's take the vectored valued function r of t is 6t plus 8I plus 4t squared plus 2t minus 3j. The derivative of the vectored valued function, which will denote r prime of t, is simply the derivative of each component. The derivative of 6t plus 8 is just 6i's, plus the derivative of the polynomial is 8t plus 2 times the j vector. And there is our derivative. Let's try and make them a little more interesting. Let's say the vectored valued function r of t is e to the t sine t times I plus e to the t cosine t j minus e to the 2t k. And we're going to find the derivative of our vectored valued function, r prime of t. Well, our first derivative is a product, so we remember we have to use the product rule, which is the derivative of the first part, e to the t, times the second, sine of t, plus the derivative of the second part, which is cosine of t, times the first, e to the t, times the I component. Plus, again, using our product rule, the derivative of the first times the second, plus the derivative of the second, which is going to give us negative sine, times the first, which is e to the t, times the j component, minus the derivative of e to the 2t is e to the 2t, using the chain rule, times the derivative of the inside is 2, times the k component. And now we've got our derivative. Let's try r of t is equal to t natural log of ti plus 5 e to the tj plus the cosine of t minus the sine of t k. And so our derivative, r prime of t, again, we've got a product rule. So we take the derivative of the first, which is 1, times the natural log of t, plus the derivative of the second, which is 1 over t, times the first, which is t, all times I, plus 5e to the tj, that's a pretty straightforward derivative, plus derivative of cosine is negative sine, the derivative of sine is cosine, times the k. A little bit of simplifying, just simplifying that t over t is 1. So we find out our derivative of the vector valued function is the natural log of t plus 1 times I plus 5e to the t times j plus negative sine of t minus the cosine of t k. And we have our derivative of the vector valued function. One of the most common and useful purposes for the derivative of vectored valued functions is to find what are called tangent vectors. And similar to a tangent line being tangent to the curve at a point, being the first derivative, it works exactly the same with vectors. We're going to find the tangent at a point. Let's say the vector r of t is equal to the cosine of t times I plus the sine of t times j. And we're going to find the tangent vector at the point t equals pi over 6. Well, the derivative is just component-wise, gives us the negative sine of t times I plus the cosine of t times j. And we're being asked to find the tangent vector specifically at the point pi over 6. Negative sine of pi over 6i plus the cosine of pi over 6j. Which, if we simplify, the sine of pi over 6, pi over 6 is at root 3 over 2 comma 1/2. Sine being the y-coordinate gives us the 1/2, so we have negative 1/2 I plus the cosine of pi over 6 is root 3 over 2 j. This vector, then, can be positioned so it's tangent to the point at time equals pi over 6. Visually, what we're looking at, if you remember from parametric equations, graphing x equals cosine, y equals sine, that's actually just the unit circle going around counterclockwise. And we're specifically interested at when time is pi over 6. And if we were to draw a tangent vector right there, it could be written in component form as negative 1/2 I plus root 3 over 2 j. And that would be the same as the component vector coming out of the origin. It's going in the same direction. Because remember, vectors don't have a location. They just have a direction and magnitude. Speaking of magnitude, there's no rule by just taking the derivative that really dictates the magnitude of that tangent vector. And so usually we like to standardize how we think about tangent vectors by saying we're going to be particularly interested in the unit tangent vector. That way, no matter how you get your tangent vector, it's always going to be the exact same length. The unit tangent vector is a very special vector that we're going to use throughout this chapter. We're going to call it capital T of t. And it is simply just the derivative of the basic vector, r of t, divided by the magnitude of that derivative. So first, we're going to find the tangent vector, and then we'll make it a unit vector by dividing by its magnitude. So let's try an example where we do just that. Let's say the vector r of t is equal to t squared minus 3i plus 2t plus 1 j plus t minus 2 k. And we want the unit tangent vector to this vector. We're going to do this generally, not at any specific point. We're going to do it generally for any point t. We could find it at a specific point if we had a t value we were particularly interested in. But for this example, let's just do it generally. So first, we need to know the derivative of our vector valued function r, which is 2ti plus 2j plus 1k. But that is not a unit vector, so to get our special vector, our unit tangent vector, we're going to find the magnitude of the derivative. And we remember the magnitude is the square root of the square of the components. 2t squared plus 2 squared plus 1 squared, which gives us the square root of 4t squared plus 4 plus 1, which is 5. That tells us then that the unit tangent vector, that special vector t of t, is 1 over the square root of 4t squared plus 5 times the derivative, which is 2t, comma 2, comma 1 in component form. If we wanted to, we could distribute that divide by the square root, giving us just the vector 2t over the square root of 4t squared plus 5, comma 2 over the square root of 4t squared plus 5, comma 1 over the square root of 4t squared plus 5. And now we have a vector of unit length. It's always going to have a length of 1 that will always be tangent to the vector r of t. We're going to come back to unit tangent vectors in our future sections and explain why they're so important and helpful to us as we're working with vectored valued functions. But for now, we're just going to find them generally like we did in this example, or we could find them specifically at a point. If I knew t was equal to 7 seconds, we could evaluate that. But for now, let's step away from derivatives. We still have to look at the second half of calculus, which is integration. And just like derivatives, we can take the derivative component at a time. We can take the antiderivative of each component but just like before in Calc 2, when we took an integral, we would always have plus a constant. We need to reflect that here also, but we need to express that constant is a vector. So we're going to say it's plus a constant vector, which we will represent with a c, with the vector symbol above it, representing some vector made up of 3 constants: constant 1, constant 2, constant 3. So for example, if we're being asked to find the integral of 2t plus 4 I plus 3t squared minus 4t j dt, we can integrate this one component at a time. Integrating the I component, we end up with t squared plus 4t times the I, plus the j component becomes t cubed minus 2t squared times the j component. But because this is not a definite integral, we need to also add a constant vector to our final solution. And so we're integrating one component at a time to get our final solution. Let's do one last example. Let's do a definite integral this time. Let's go from 0 to pi over 3 of the vectored valued function sine of 2t I plus the tangent of t j plus e to the negative 2t k dt. Evaluating one component at a time, the antiderivative of sine is the cosine of 2t, actually the negative cosine. To account for the times 2, we need a 1/2 out front times the I component plus the antiderivative of tangent, you might remember, is negative natural log of the cosine of t j. Remember, that comes from writing tangent as sine over cosine and then using substitution to integrate. Plus antiderivative of e to the negative 2t is e to the negative 2t, but we have to multiply by a negative 1/2 to account for that. 2 times the k component, and we're just going to integrate this entire thing from 0 to pi over 3. And we'll do that substitution one component again at a time. So first with the I, we have negative 1/2 cosine of 2t, or 2 pi over 3, plus 1/2 cosine of 2 times 0 is 0 times I, plus plugging pi over 3 into the natural log, we get negative natural log of the cosine of pi over 3 plus the natural log of the cosine of 0. All of that's your j component, plus negative 1/2 e to the negative 2 pi over 3 plus 1/2 e to the 0, all that times the k component. Simplifying, let's see what we have left. Cosine of 2 pi over 3 is going to be 2 pi over 3 is over here on the unit circle. So that's going to be negative 1/2 comma root 3 over 2. So the x-coordinate's the negative 1/2. So negative 1/2 times negative 1/2 plus 1/2 times the cosine of 0 is 1, I, plus the negative natural log of the cosine of pi over 3, 1 pi over 3, is a positive 1/2 root 3 over 2. So the natural log of 1/2 plus the natural log of cosine of 0 is 1. That's going to be nice because the natural log of 1 is 0, times the j component, plus not much simplifying that we're left with on this last part. I'm going to put the positive 1/2 in front just because it makes it pretty. Minus 1/2 e to the negative 2 pi over 3 times the k component. And so one time through, left to simplify, we end up with 1/4 plus 1/2 is 3/4 I minus the natural log of 1/2 j plus 1/2 minus 1/2 e to the negative 2 pi over 3 k. And now we found the antiderivative of our vectored valued function from 0 to pi over 3. So calculus with vectored valued functions, not too difficult. It's just basically extending what we saw in Calc 1 and Calc 2 with derivatives and integrals, just doing it with every single component all the way through. We also introduced this idea of the unit tangent vector. That's going to be very important to us as this chapter progresses. So take a look at a few of these on the practice assignment. We will see you in class to answer any questions you may have. Today's video is going to look at answering the question of how do we measure arc length and curvature. And we'll talk about curvature a little more when we get to it. But first, we're going to address the question of arc length for our vectored valued functions. And we're going to build this based on what we know from parametric curves. When we did parametric curves, we said arc length s is equal to the integral from a to b, where a and b were the edges of the curve, of the square root of x of t prime squared plus y prime of t squared dt. Well, similarly, if the vectored valued function r of t is equal to the component form f of t, g of t, h of t, then we have arc length is equal to the integral from a to b of the square root of the first component's derivative squared plus the second component's derivative squared plus the third component's derivative squared dt. And really, actually, finding the square root of all the components squared, we've seen that formula before. This is the formula for the magnitude of the vector. So instead, we can simplify our arc length formula to the integral from a to b of the magnitude of the derivative of the vector. And that becomes our formula for arc length. We take the derivative of the vector, we find its magnitude, and then we integrate it over its range. So let's do an example using this new formula. Let's say r of t, the vector valued function, is equal to 2t squared plus 1, comma 2t squared minus 1, comma t cubed. And we're going to find the arc length as time goes from 0 to 3. Well, first we need to find the derivative of our vectored valued function, which is going to be 4t, comma 4t, comma 3t squared. Next, the formula says we need to know the magnitude of the derivative of the vector valued function. And magnitude we know is the square root of the square of its components, 16t squared plus 16t squared plus 9t to the fourth, which simplifies to the square root of 32t squared plus 9t to the fourth. And actually, if we factor out a t squared, we get the square root of t squared times 32 plus 9t squared. And we can take the square root of the t squared to get our total magnitude is t times the square root of 32 plus 9t squared. Now we're ready to go to our formula, which says that the arc length is equal to the integral. We're going from 0 to 3 of the magnitude of the derivative of our vectored valued function, which we just found out was t times the square root of 32 plus 9t squared dt. We can take this integral quite quickly using u substitution, where u is 32 plus 9t squared. That makes du equal to 18t dt. So we'll multiply by 18 inside and 1 over 18 outside to get 1 over 18 times the integral. Plugging 0 and 3 into the u equals equation, we get 32 plus 0. And plugging the 3 in, 3 squared is 9. 9 times 9 is 81. 81 plus 32 is 113. The 18t dt becomes our du, and the square root becomes u to the 1/2, which we know is u to the 3/2 times 2/3 with the 1 over 18 on the outside, integrated from 32 to 113. 2 over 18 is going to reduce to 9, so we're going to have 1 over 27 times, and I don't think this is going to simplify, so we'll leave it as 113 to the 3/2 minus 32 to the 3/2. And that's an ugly decimal, so we'll call that good for the arc length of our vectored valued function. So using our formula, arc length is simply the integral of the magnitude of the derivative of the original vectored valued function. Really, we've done arc length before when we worked with parametric curves. So we're going to move to the next topic, which is curvature. And curvature is an important concept to us as we look at a curve. Curvature measures how sharply a smooth curve turns. If it's got a real sharp, tight curve, then you'll get a larger curvature. If it's a nearly flat, wide curve, you're going to get a much smaller curvature. Curvature measures how sharply the curve turns. Similar to slope or the derivative, measuring how fast the curve changes, curvature measures how sharply the curve turns. And there's a couple formulas for curvature depending on the context that we're working in. We use, it looks like a K, it's kind of a cursive K for our curvature symbol. Curvature is equal to the magnitude of the unit tangent vector derivative divided by the magnitude of the regular vector's derivative. This function works best in 2D. So if we have a two-dimensional vector, we'll find the unit tangent vector and the magnitude of its derivative, divide by the magnitude of the derivative of the vector-valued function. However, if we're in 3 dimensions, there's a quicker formula that can help us because we can use the cross product in 3 dimensions. In 3 dimensions, we'll take the derivative of the vector-valued function, and we'll cross it with the second derivative of the vector-valued function, find its magnitude, and divide by the magnitude of the derivative raised to the 3rd power. That formula is going to be best when we're working in 3-dimensional vector space. Now, this can be simplified using functions to show that this is the absolute value of the second derivative of y divided by 1 plus the first derivative of y squared raised to the 3/2 power. And this function, this equation, is the one we'll use best with y as a function of x. So if we just have a function y equals, we'll use the last equation. If we have a 2-dimensional vectored valued function, we'll use the first equation. If we have a 3-dimensional vectored valued function, we'll use that center equation. So let's take an example where we use each of these equations to measure the curvature, or how sharply the graph curves. These 3 equations are going to be really key to this section. So let's highlight them as we go into our first example. Let's say we have the function r of t is equal to 5 cosine of t I plus 5 sine of t j. Since we're just working with I and j, we have a vectored valued function in the plane in 2 dimensions. So we're going to use that first equation, the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector valued function. Probably easier just to start finding all the pieces and then dividing at the end. So first, the derivative of the vector valued function, r of t, is negative 5 sine of t I plus 5 cosine of t j. Well, for the denominator, we need to know the magnitude of that. So the magnitude of the derivative of the vector valued function is the square root of the component squared, which is 25 sine squared of t, plus 25 cosine squared of t, which is really nice because if we factor out the 25, we get the square root of 25 times sine squared of t plus cosine squared of t. And we know sine squared plus cosine squared is 1, so this is just going to be the square root of 25, or 5. Which means it should be really easy to find the unit tangent vector. We know the unit tangent vector is the derivative vector divided by its magnitude. So 1/5 dividing by the magnitude times 5 sine of ti plus, I'm sorry, it's negative 5 sine of ti plus 5 cosine of tj. Distributing the 1/5 through, making it a unit tangent vector, it becomes negative sine of ti plus the cosine of tj. The numerator is the derivative of the unit tangent vector. So we'll take this unit tangent vector that we just found, negative sine of ti plus the cosine of tj, and find its derivative, which gives us negative cosine of ti minus the sine of tj. Well, the numerator is the magnitude of this vector, the magnitude of the unit tangent vector, which in this case is really nice because it's the square root of the components, which is cosine squared of t plus the sine squared of t. And we know sine squared plus cosine squared is 1. And so now we're ready to go to our formula for curvature in 3D. In 3D, the curvature is the magnitude of the unit tangent vector's derivative divided by the magnitude of the vectored valued function's derivative. Well, the tangent derivative's magnitude we found out was 1. The magnitude of the derivative of the vector we found out was 5. And so we have a curvature of 1/5. Turns out in this case that the curvature is constant because this entire shape is a circle. It's a circle of radius 5, and so it curves at a rate of 1/5 all the way around the entire graph. But that's just a 2D example. Let's take a look at an example in 3D. Let's take the vector valued function r of t is equal to 4 cosine of t, 4 sine of t, and 3t. Now, it's off my screen, so I'm just going to copy again that curvature in 3D is going to be the magnitude of r prime of t crossed with r prime prime of t divided by the magnitude of r prime of t cubed. It's just to remember the formula, which is off my screen. So we just need to start finding these pieces. So let's start with finding r prime of t. R prime of t is negative 4 sine of t, comma 4 cosine of t, comma 3. We also need to know r prime prime of t, which is negative 4 cosine of t, negative 4 sine of t, and 0. To make the numerator, we need to cross those two vectors. So r prime of t crossed with r prime prime of t. And when we cross these, we get 0 minus a negative 12, so positive 12 sine of t, comma, 3 times negative 4 is negative 12 cosine of t minus 0, comma, 16 sine squared of t minus a negative, so plus 16 cosine squared of t. Which, if you factor on that k component, factor out a 16, we have sine squared plus cosine squared. So that's actually going to simplify just to 16. So let's rewrite this vector simplified with 16 in the k component. The numerator of the curvature is the magnitude of r prime crossed with r prime prime of t. So let's find the magnitude of this vector, which is the square root of 144 sine squared of t plus 144 cosine squared of t plus 16 squared, which is 256. Factoring out the 144, we're left with cosine squared plus sine squared, which is 1. So we're left with 144 plus 256, which is the square root of 400, which is 20. So our numerator for the curvature is 20. The denominator is the magnitude of r prime of t cubed. Well, we found r prime of t already in our first step up above in blue, so let's just run the magnitude formula, which is the square root of the components, 16 sine squared of t plus 16 cosine squared of t plus 9. Again, if you pull the 16 out of the first two terms, you're left with 16 times sine squared plus cosine squared, which is 1, plus 9. We get the square root of 25, which is just 5. And so finally, we're ready to calculate the curvature of our vectored valued function. Curvature, we said, using the formula in the top right here, is the numerator is the magnitude of the cross product, we found out was 20, divided by the magnitude of the derivative, which is 5 cubed, which is 20 over 125, which dividing by 5 will give us 4 over 25 as our final curvature. Curvature in 3 dimensions, measuring how sharply a corner is turning. We had a third formula, though, for curvature, so let's take a look at it. The third formula is used best when we have a function written out like f of x equals x squared. How sharp is this function turning? How is the curvature measured? Well, again, it's off my screen, but you have it on your notes up above, that the curvature when we have a function is the absolute value of the second derivative divided by 1 plus the first derivative squared raised to the 3/2 power. So let's find all those pieces. First derivative is 2x. The second derivative is just 2. And so if we plug into our curvature function, we get the absolute value of the second derivative, which is 2, divided by 1 plus the first derivative, which is 2x squared, all raised to the 3/2 power. Cleaning up a little bit, the absolute value of 2 is just 2 over 1 plus 4x squared raised to the 3/2 power. And this time our curvature is not a constant, but it depends on how big x is. And that makes sense because we know x squared starts out with a real sharp curve in the center, but on the outsides it's becoming more and more flat. In fact, let's take a look at what the graphs of x squared looks like compared to the graph of its curvature. So here I've graphed the graph of x squared. And now I'm going to graph its curvature, which we said was 2 over 1 plus 4x squared raised to the 3/2 power. And what we see is the curvature is at its largest value, its steepest point, at 0. But as it gets out further and further and further, the curvature gets less and less and less. And so we see the curvature increases as the curve sharpness increases. And that's what we're measuring with curvature. How sharply, how fast is this smooth curve turning? So we've got 3 formulas for curvature. One formula that helps in 2 dimensions, one in 3 dimensions, and one when we have y as a function of x instead of a vectored valued function. Take a look at the homework assignment, also doing some arc length problems to see if you can get comfortable with them. Come to class with questions, and we will see you then. Now that we've gotten comfortable working with these vectored valued functions, we're ready to address the question, how do we model motion in space over time? And the idea is very similar to when we were working with derivatives and integrals. We can talk about the position of a particle. We can talk about its velocity. And we can talk about its acceleration. In fact, there's one more thing we can talk about too now that we have vectors, and that's the idea of speed. But we'll get to that in just a minute. And what's nice with vectored valued functions is now we can extend those ideas of position, velocity, and acceleration into 3 dimensions. The vector valued function r of t can represent the position of a particle at time t in each direction. So the I component can represent how far it's moving horizontally over time. The j component represents vertically over time. And the k component can represent the 3rd dimension over time. And so with each component, we can represent motion in each of the directions. Then we can come up with a velocity vector, which is equal to, as you might expect from Calculus 1, the derivative of the position vector. And this represents the velocity at time t in each direction. So it might be moving faster vertically than it is horizontally. Maybe if you shoot a cannon vertically up, it's moving vertically really fast and maybe horizontally just a little bit. The vector v of t can show that velocity in each direction. And then, as you might expect, the acceleration vector a of t is the derivative of the velocity vector, or the 2nd derivative of the position vector, representing the acceleration at time t in each direction. And we're going to introduce a fourth thing to this discussion, and that's going to be what we call v of t. And notice this is not marked as a vector. This is a function that's not a vector, but it's going to have a scalar solution. And the reason for that is the v of t is going to represent the speed. And the way we calculate that is we take the magnitude of the velocity vector. So we want to be very careful that if it's a vector, it represents the velocity. If it's a scalar, it represents the speed. Another way we could say that, because the velocity is the derivative of the position, we could say that's the magnitude of the position vector. This represents speed. Not in any particular direction, but the overall speed of the particle. So let's do some examples where we look at these concepts. Let's say we've got the position vector r of t is equal to t squared I plus the square root of 5 minus t squared j. If we wanted to find the velocity vector with respect to time, then, we just take the derivative of the position vector. Taking the derivative of each component, we get 2t times I plus square roots of 1/2 power. So we have 1/2 times 5 minus t squared to the negative 1/2 times the derivative of the inside, which is going to be negative 2t, times our j. Cleaning that up a little bit, we've just got 2ti dividing out the 2's minus a t times 5 minus t squared to the negative 1/2 j. This then is our velocity vector at time t in the direction of I and j. If I wanted to find the acceleration vector at time t, we just take the derivative of the velocity. So on the I component, we just have 2i minus, on the j component, we've got a product rule. The derivative of t is 1 times 5 minus t squared to the negative 1/2 plus the derivative of the negative 1/2 power is negative 1/2 times 5 minus t squared to the negative 3/2 times the derivative of the inside, which is negative 2t. And then we have to also multiply by the first factor, which is t, all that times j. Well, let's clean that up a little bit. So our final acceleration vector is 2i minus 5 minus t squared to the negative 1/2. The 2's divide out, and the negative times the negative is a positive. So we're going to have plus t times t is t squared times 5 minus t squared to the negative 3/2. All that times our j. It's a little bit more complex, but that is our acceleration vector. We can also find our speed. Speed is v of t. It's the magnitude of the velocity vector. So magnitude is the square root of each component squared. So we take the 2t squared is 4t squared. Plus, we have a t squared. And then the 5 minus t squared to the negative 1, because when we square 1/2, the negative 1/2, the 2's divide out. And that does not look like it's going to simplify at all. So that represents the speed of our particle, represented by the vector r of t. Let's try one more example to make sure we can do velocity, acceleration, and speed. Let's say we've got a vector r of t, which is equal to, let's do component form this time, t squared minus 3t, 2t minus 4, and t plus 2. The velocity vector, then, is the derivative of that, which is 2t minus 3, 2, and 1. The acceleration vector is the derivative of that vector, derivative of the velocity, which is 2, 0, 0. So it's only accelerating, it turns out, in the x direction, or towards the I vector. Every other vector, the acceleration is not changing. It's a constant velocity of 2 or 1. If we just want v of t, remember that's the magnitude of the velocity vector. So we take the square root of each component squared, which becomes, squaring 2t minus 3, we get 4t squared minus 12t plus 9. Plus 2 squared is 4, plus 1 squared is 1. And so for our speed, it's going to be the square root of 4t squared minus 12 plus 14. And so we have our acceleration, velocity, and speed values. One nice application of these vector-valued functions with velocity, acceleration, position is this idea of projectile motion. Projectile motion is when an object is moving through space, and the only force acting on it is gravity. And in 2 dimensions, projectile motion can be represented with the vector valued function s of t, the initial velocity times time, times the cosine of the angle that it begins moving at, times the I vector, plus the initial velocity times time, times the sine of the angle. But since the second component represents the vertical distance, we also have to subtract the force of gravity, which is 1/2 times gravity times time squared, times the j vector. This formula can be used to model projectile motion into space. So let's see if we can do an example where we use that formula. Let's say a cannonball is fired from a cannon on a cliff towards water. The cannon is aimed at a 30-degree angle, or pi over 6, above the horizon, which just means above the flat line. And the initial speed of the cannonball is 600 feet per second. We also know that the cliff is 100 feet above the water. So if we were to draw a picture, we've got a cliff with a little cannon. And it's all above water. And the idea is we're going to shoot this cannonball, and it's going to go up and ultimately land in the water. We know the cannon makes a 30-degree angle with the horizon. We know the initial speed coming out is 600 feet per second. We know the cliff is 100 feet above the water. And the first thing we're going to do is model this situation with a vector valued function. And as a hint, since we're in feet, we're going to do the English version of gravity, which is 32 feet per second squared. Well, using our model up above, the vector s of t is equal to the initial velocity, which is 600, times time, times the cosine of my angle I, plus 600 times time, times the sine of my angle, minus 1/2 of gravity. And since we're in the English system, we're going to use 32 feet per second, times time squared, times the j component. We can do a little bit of cleanup. That our vector s of t is equal to the cosine of 30. A 30-degree angle is at the point √3/2, 1/2. So the cosine of 30 is going to be √3/2. And the divide by 2 will reduce with the 600, leaving behind 300 √3. Actually, let's put the t in there. 300t √3 times the I vector, plus the sine of 30 is going to be 1/2. So half of 600 is 300. T minus half of 32 is 16 t squared times the j vector. This vector valued function, then, is going to represent both the horizontal motion over time in the I component and the vertical motion over time with the j component. So now that we have our equation, we can answer questions, such as finding the maximum height. If I'm interested in the maximum height, all I really care about is the component that describes the height. And that height is going to be at its maximum point when the velocity is 0. Or, as we know in terms, first let's put in velocity equals 0. Or in terms of what we talked about in Calc 1, the maximum height is when the first derivative, s prime of t, is equal to 0. And we particularly only care about the y component because we just want to know how far vertically it is. So we're going to look just at the 300t minus 16t squared. And we're going to take its derivative, which is 300 minus 32t, and set that equal to 0. which is a quick solve. 300 equals 32t. And dividing by 32, t is equal to about 9.375. So at 9.375 seconds, this cannonball has reached its maximum height. But the question wanted us to actually find the maximum height, not just the time when it occurs. So what we need to do is plug that time in to the position vector to see how high it actually is. So we've got 300 times 9.375 minus 16 times 9.375 squared. And if I work that out on my calculator, we should get 1406.25 feet. So it shoots from 100 feet up another 1,400 feet into the air at its maximum height after 9.375 seconds. If I was also interested in how far horizontally this reaches over the water, we could plug that 9.375 into the x component or the I component to see how far horizontally over the water we are. But the question didn't ask about that, so let's move on to question C. Question C, I want to know how long until it hits the water. Well, going back to my picture, the cannonball hits the water all the way out on the right side here. What we know there is the y component, the vertical distance, is not 0 because 0 is when it hits the same level as the original cannon. We've got to drop another 100 feet down. So we actually are asking, when does the vertical component equal negative 100 feet below the cliff? And we know that the vertical component is 300t minus 16t squared. So we want to know when that equals negative 100. Well, putting things in order and moving the 100 to the other side, actually, let's make everything positive. Let's move everything to the right side. When we do, we get 0 equals 16t squared minus 300t minus 100. And we know we can solve this using the quadratic formula. T is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2 times a. Although we know that we want time to be a positive number, so we're probably not going to need to worry about the subtraction. That's probably going to give us a negative number. And so when I put this in my calculator, we get 19.08 seconds. Which means, putting our answers together, after 9 seconds and change, the cannonball reaches its maximum height. And then after 19 seconds and change, the cannonball has crash landed into the water. Well, if it crash lands into the water, what I might be interested in as a military personnel is how far out to sea will the cannonball travel. In other words, what is my range with my cannonball on shore here? Well, we just found out in part C that it hits the bottom, or hits the water at 19.08 seconds. And we're asking, how far out does the cannonball travel horizontally? That's going to be the x component. This time we're going to be interested in the 300t divided by times the square root of x. So 19.08 seconds in the x component, or the I component. So the I component then is 600 times time, and we just found out time was 19.08 seconds, times the square root of 3. Plugging that in the calculator, we end up with 9,914.26 feet. The cannonball can travel just shy of 10,000 feet in those 19 seconds when it crashes into the water. So today we're looking at an application of these vector-valued functions, motion in space. We're basically taking our vectors, which represent the position, velocity, and acceleration in each direction, knowing that the velocity is the derivative of the position, the accelerations, the derivative of the velocity, and if we're also interested in general speed, that's not a vector, it's a scalar. It's the magnitude of the velocity vector. Take a look at the assignment, practice a few of these, and we will see you in class to discuss them further.